Hello, hello. Good morning, everyone. Today we'll be starting with day 5, session 11, observation campaign for understanding processes associated with extreme precipitations event session. And I invite Dr. Thara Prabhakaran as chair and Dr. G. Pandithurai as co-chair and repo chair Mrs. Manogranti. So I would like to request co-chair and chair to kindly lead the session. Thank you.
Hello, good morning, everyone. This is a wonderful morning with lots of monsoon is coming. So you all feel so elated, I think. So the session today, are you able to hear me properly? Yeah. Okay, session today is observation campaign for understanding processes associated with extreme precipitation events. And first talk is by an eminent speaker, Dr. W.K. Tao. He is from GSFC, NASA, and he will be talking about developing, improving, and applying cloud resolving models. And as you know, nowadays, the cloud resolving models are becoming very popular even in global modeling. So I think let us invite him. He's giving the talk online. And let us invite him to give this talk. Thank you. Okay. Huh? Hello. Hello, Professor Tao.
Can you hear me?
Yeah, we can hear you.
Yeah, I have problem to uploading the talk, but I give the copy to Dr. Putsa.
Is it? Is it? Have you? Has he given the talk? Where is it? I actually we don't have your presentation. Is it okay that you can share the presentation?
Okay, let me try that. Okay.
Yeah.
I really have problem.
No problem. If it is actually he has sent it. Yeah. We have your presentation. It is now being shared.
Okay.
Yeah. Thank you, Professor Tao. And I think we are set now. Are you able to see the presentation? You will need to share the presentation. Share the screen. Satish is not there. Ask for help. Just a minute, Professor Tao. We are about to share it.
Yeah, I have lost everything.
Oh,
can you still hear me?
we are able to hear you.
You have my talk, or you don't have my talk?
We have your talk and it is projected, but we are trying to share it. Huh? Share kiya. Yeah, we have already shared the talk with you. Are you able to see the first slide?
Okay, let me.
You might have to go
Okay,
to.
let me say. Okay, let me start it.
You might need to go to that Teams page.
Okay, you have my talk, right?
Zoom page. Yeah, sorry.
Okay.
Zoom. Yeah. Are
Okay,
you able?
thank you. And the first one showing the outline. I will talk about numerical model.
Yes.
Field
Yes.
campaign. And I will also discuss with you on we are using two different types from field campaign. And I will talk about model validation, field campaign, and also discuss a little bit on how the model and the satellite program working together. Next one. It is showing how we use the numerical model and the field campaign, and hopefully we can improve the large scale model, the moist processes. I think from the right, we have the two different models, GC and NASA Unified Wall, and through we can simulate different type of convective system, and then through the satellite simulator or ground-based simulator, remote sensor simulator, we can get the compare with the high resolution NASA satellite data and also ground-based campaign data. And if a model result not good, then we can enhance the model performance. And also we can identify what the process need to be improved. So the key thing is for the high resolution model is we really need to drop site distribution, and also we like to have 3D liquid and ice water content, number concentration, and also the ice habit. And the other thing I want to emphasize here, we need a life cycle of the cloud and the cloud system, because most of the cumulus parameterization scheme, they don't have a life cycle. Next one. And I see you're looking at the literature these days. You probably can read the different name on the cloud model. Okay, sometimes they call it cloud ensemble model, cloud resolving model, cloud system resolving model, or cloud convective permitting model. But this model have very similar characteristic. So you have to be non-hydrostatic and have to run resolution very fine, 1 kilometer or even less. And the other unique on the cloud model is they have sophisticated cloud and the microphysics. They can deal with the phase change to the liquid and the solid from the water vapor. And had to be a larger domain because most MCS is large. Another good thing about the high resolution cloud resolving models, when you interact with the radiation, you don't need to have a cloud overlap assumption. Okay, so either the grid point is 100% cloudless or cloud free. And also recently, people using cloud resolving model to look into an indirect and direct effect aerosol. Next one. So this is the first model, and we call the GC model, and it started almost 40 years. And typically they have a three-dimensional wind, temperature, water vapor, and also different the hydromedium. They interact with the microphysics and long wave and short wave radiation and surface process and turbulence. So this is most of the model. Okay, most of the cloud resolving model have this kind of feature, except some models have different dynamic vertical coordinate. Yes.
Are you able to hear us? Can you please hold on 2 minutes? There is some technical issue. They are trying to. Are you able to see the slide in your screen? whatever
Straight.
shade.
Now it's number 4. You want to go back straight?
Yeah, I think 4 is fine, I think. 4. Yeah, right.
Oh, okay.
Are you able to change the slide or you want us to change?
Yeah, you change it. I asked you to change. I have problem to share the talk.
Okay, thank you. Please go ahead.
Okay, so the number 4 is the GC model, and I think already talked about, and just different model at different the physics, microphysics, radiative transfer, and the turbulence. And most of the time, these GC models focus on the precipitation process. And because I mentioned satellites, so the GP train, the GPN rainfall, and the latent heating retrieval algorithm is based on some of the GC models, the output. Next one. This is a NASA Unified World. We started almost 10 years ago, and you're looking at the right-hand side is almost the same as the previous one. You have the microphysics, radiation, and the dynamic. And we also have the Gauda land information system, and also the Gauda temperature and aerosol radiative transfer, the model GoCard. So basically, there's 4 major components, okay? The microphysics, radiation, land, and the temperature will be replaced, okay, on the warp, either their option. And we have used the NASA Unified World for real-time forecast and to support the GPN ground validation field campaign. I will show one example later. And also, I think the precipitation process started to support the satellite mission GPN and also the new mission AOS. I will also mention that later. And next one, please. So the first, probably that's the first international field campaign is GATE, 1974. And my master's degree and also my PhD funding is from the GATE. Next one. So this is showing some of the geographic location on the field campaign used since 1980 to provide the data and to drive and evaluate GC models. So you can see the cover a lot of places, but they still have some issue. We don't have a lot of field campaign over the ocean and also the mid and the high latitude. There's 2 specific cases. Okay, I will talk about that later. One is MC3E, that's in the Oklahoma region, and I-flood is Iowa. So I will talk about some of the result and how we do that. Next one. Okay, this is just show you what's the name and the location, time period, and references of the field campaign. The red color, that's the GPN field campaign. So basically, this campaign is funded by GPN or partially funded by GPN. And we use that for GPN, the validation and the algorithm validation along. Next one, and we're using GC model, but we're using the observed large-scale advective tendency of potential temperature, water vapor, and horizontal momentum are used as the main large-scale forcing in the GC model. So you're looking at the equation Q1 equal partial Z, partial T, and horizontal and vertical advection term. This can be derived from the field campaign sounding network. So we're using this forcing from the sounding. And so you can see the partial theta bar, okay, bar turn on the potential temperature and the QV, that's from the sounding network. So we'll provide that as additional forcing into the equation on temperature and water vapor. On the other hand, the cloud resolving model can estimate the vertical eddy transfer by convective core and also by the phase change on the water vapor, condensation, evaporation, freezing, melting, deposition, and sublimation. So if you take the radiation on the other side, so the model also can estimate Q1. So the sounding can estimate Q1, co-resolving model can also estimate Q1, but however, the term is not the same. Next one, so let's see the result, okay? So the first one is showing 1 month, the top one is showing 1 month, the surface rainfall, and compare with the sounding estimate. So it's clearly the model doing pretty well, capture the temperature variation on precipitation, surface precipitation, and especially the larger surface rainfall rate, the model even doing much better. And the bottom two showing the observed and the model simulated Q1. Okay, this is the time, this is horizontal domain mean. Okay, and again, the model doing pretty well and capture most of the observed Q1. Especially if you look in the temperature and the forcing and also surface rainfall, you can see the larger forcing on Q1, you also produce a larger rainfall. Okay, so this is 3 or 4 major the convective period. So you do see the 4 different forcing and also the surface precipitations. Next one. And I'm sorry. This one is showing some of the microphysical term, and we also try to understand how those process, okay, whether that's in updraft or downdraft, whether they're in the stronger or moderate the updraft. Like the updraft, we can also look in the vertical velocity greater than 1 meter per second or 2 meters per second. So it clearly, okay, the condensation, deposition, and the freezing that occur in the updraft. And even it's the more than the 66%, 58% condensation happen to be in the stronger vertical velocity. That's the vertical velocity greater than 2 meters per second. And however, you're looking at downdraft, now is the evaporation, there's not much condensation, okay, deposition, even freezing, but the major term is evaporation and the sublimation. However, you're looking at the vertical velocity less than 1 meter per second, only about 1/3 evaporation taking place there, and the quarter sublimation is there. Next one. So we also want to see how those the updraft, okay, active updraft or active downdraft, what's their area coverage, okay? So clearly the area coverage for this active updraft or downdraft is very small, okay, 2% sometimes. And the downdraft area is about twice as much as the updraft. I think if someone asked the question in someday, I will answer that in next one. And I think based on the previous one and this one, we can conclude that condensation, deposition, and the freezing mainly occur in the active updraft core. However, the evaporation, sublimation, melting may be more widely scattered and compared with the active updraft region. So next one. So someone asked the question, why we have the more downdraft and twice more downdraft area compared with the updraft area. I think if you look in this is my explanation. If you look in the Bob House, idealized MCS, and you can see the convective region is relatively smaller, but the stress from rain is larger. That's mostly in a downward motion below the melting. So that might be the one explanation, and why the downdraft have the twice more area compared with the updraft. Now let's talk about the other model, the NASA Unified World. I think for GPN and numerical, the new, we do have some specific objective. We want to use a measurement from GV and MC3E, iFlood, for example, and other to evaluate performance of NASA core resolving model. And we also want to conduct a real-time forecast to support the field campaign, and also doing the post-mission simulation, okay? And evaluate gather microphysical scheme, and also provide models simulate cloud and precipitation data for GPN latent heating algorithm development. Next one. So this is the model configuration, and we run in the different the gray size and also vertical layers between the MC3E and the iFlood. Okay, and because the iFlood, they want the 1 kilometer grid. I just want to emphasize here, and we need to dedicate more than 2,000 CPU, okay, for doing the real time, the simulation for GPN, the GV site, and it takes 7 hours to produce 48-hour forecast. Next one, and this one I just because most of the microphysics is only have the straight ice, okay, either cloud ice, snow, and gravel, or you have a cloud ice, snow, and hail. So this one I just want to emphasize the importance of hail. So both the straight ice, hail, and the gravel, they produce very similar. The cloud, okay, the lenient cloud, and from the southwest and to the northeast over the U.S. continent. However, you're looking the leading edge of the convective, the observation, and the straight ice skin hail, definitely the hail is doing much better, produce much large the compensated DBZ along the leading edge of the system. The gravel case is just 2 weeks. So I think because the both hail and the gravel can occur in the real weather events simultaneously, I think that was the reason we developed full ice skin. So you don't have to worry whether before you run the model, you want to decide it. You want to have straight ice hail or straight ice gravel. Next one, please. So let's see the result on MC3E, and again, the top showing the 4 different panel, and clearly the full ice skin doing much better compared with straight ice skin, either gravel or hail. In the convective region and the leading edge of the system, the updraft penetrate much higher compared with straight ice with gravel, and also much weaker compared with straight ice with hail. The other good thing about the full ice skin, you do see it very nice uniform, the stratiform ring behind the convective system. So based on this, we believe full ice skin doing much better. Then we also look in the PDF rainfall intensity, and so we have 4 rounds, and the black is observation, the brown is the straight icing with the gravel. Clearly, the gravel cannot produce heavy rain rate. With the hail including, definitely we can produce much heavy rain rate, and more comparable with the observation. Next one, and again, MC3E, we are working with Colorado State University, and they do have the polarimetric hydromedium identification retrieval. So we run the GC model, I'm sorry, we run the WARP, but with spectrum being microphysics. That's very expensive, but more detailed. And the model clearly generate 9 different type. The cloud species, okay, on that's showing the figure on the low panel. There's 9 different types of cloud. So for example, the last 2 is hail, and that's red. The brown is a big raindrop, and rhyming particles. So the model definitely captured that. The other thing is the model results somehow very sensitive on the ice nuclei. So we can doing some sensitivity test by increase the eigen by 100 and even reduce that by 0.1%. So you do see especially the green, that's a large grapple, and also some the aggregated grapple. They are very sensitive. There's the green and also the pink. They are somehow sensitive on the eigen. Next one. So that's how about IFLOW. IFLOW will be in the real-time forecast, and from May 1st to June 15th, that's 1.5 months. So the model, again, doing the forecast, not that bad. Okay, you do see some temporary variation on the rainfall and over the 1.5 months, the period. But overall, the new work have overestimated rainfall. Okay, and the name is the Onset model, but they're running 12 kilometer grid size, so they probably underestimate, and they do have some issue from the May 25th and June 3rd. They somehow their rainfall temporary variation is very, very different from the observation. I also want to mention another thing. We do have the couple land. So you have the two different the new work model simulation. CP, that's the couple with the list, and the work is standard around. So we're using the stage 4 and also MS as the validation tools for validation. So same thing for IFLOW, and the top one is the 1.5 months, the mean, and clear over Iowa region, you have more rainfall compared with other states. The same is from the state 4, the observation. And from the PDF, the rainfall and I think the new work both, okay, underestimate heavy rainfall and overestimate like medium rainfall. And I also want to mention that somehow the couple with land surface model doesn't see the improvement for the real-time forecast. Next one. So I think it is something we learn, and but I just want to say a few words here, and it's the very limited computing resources. And the person running the model have the wake up in the morning and try to make sure the model does not have some issue. And the other one is the good thing is when we run the model, we can also try to fix some problem in the new world. And again, we are doing intensive the test and the current the new world improvement, like the MC3E cases, for example. Next one. Okay, this is 3-sided program and related on precipitation, and the trend is 1997, and the GPN is February 2014, and all modeling mission is most support these two mission, okay? And also we're using the cloud set, data set. Next one. This is the upcoming, the NASA satellite mission. The first one is the INCAS investigation of the convective object mission and launched in 2026. And this is a constellation. So they have launched several small satellite, and then they try to using this constellation to estimate the vertical velocity. AOS is the atmosphere observation system that will be launched in 28 and 29. This mission and have the Doppler radar on board, so they can also estimate vertical velocity. These two missions the vertical velocity is their main goal, and they want to use this vertical velocity, try to relate to the cloud and precipitation processes. Again, they rely on the cloud resolving model to provide the information. They relate the vertical velocity with the cloud and microphysics. And also AOS, also looking at some of the aerosol impact on the precipitation and the cloud. So this is my last one, and just give you some idea. The top one is all the field campaign we are using. And for GC model I mentioned, we use something estimated large-scale advective forcing to drive the model. And for New Wolf, we're using large-scale analysis or reanalysis. And these two models have same microphysics and same radiation and the same land surface model. So if you find something not great on not perfect and the microphysics, we can modify from the model, the other model very easily. Okay, same physics basically. And refine the microphysics model simulation. So then the bottom one is showing the ground-based aircraft and satellite observation. And the model also can produce, model and satellite can produce this cloud precipitation, property latent heating, the moisture profile, ice phase, and ice characteristic. And so these two from the model and from observation can produce very similar. We can look into how different between the model and observation, so we can refine the model simulation. So once the model simulation we feel is good enough, then we can provide the data set for the GPN and the trend latent heating and the rainfall and snow for algorithm development and improvement. And thank you. And I'm sorry, I had problem with the Zoom.
Thank you,
That's
Professor.
it. And thank you.
Thank you, Professor Bill Tao. Now we can take some questions from.
Professor Tao, this is Tara. I have a question to you. You have done a lot of studies with the observations and numerical modeling, including the bin microphysics to derive various cloud microphysics and related improvements in the cloud resolving models. So what do you think, what kind of observations are lacking to improve the model? What do you should focus?
You're looking at the second one?
Yeah, my question.
Second slice.
Yeah, in general, what are the observations lacking to improve the models?
I think that you have to, okay, for example, we like using polarimetric radar hydrometeor identification. However, you don't have a lot of the polarimetric data, especially in the early field campaign. Okay.
Yeah.
So it's still difficult, but I think my suggestion is to try to get as much of the data and you can have. Okay, and either doing some composite study, you have the drop site distribution for one case, or usually drop site distribution also very limited. They cannot cover the life cycles. So you have to find a certain way, okay, and to do that. And the spectrum beam microphysics also very good. The microphysics we like to use. The problem is it's very, very expensive. 200, even sometimes 400 times. 400 times compared with a simple box scheme.
Yeah. Thank you. Thank you.
I have one question, Professor Tao. You mentioned about the INCUS, the small satellite constellation. So So what are the instruments planned there? Is it precipitation radar?
I think it also have microwave and I think it's microwave, but I'm not sure at this time. I can send you the if you're interested. Send me email, I can answer you probably next day.
Okay, thank you very much. Thank you, Professor Tao, for excellent talk. Thank you very much for your time. So next, we'll move on to the next talk by Professor Zubin Zheng, University of Arizona. So he'll be talking on GPEX. It's a global precipitation experiment and organized convection. Professor Zubin.
Work? Yeah, okay. Not easy to start. Okay. First, I want to thank the organizers for the opportunity to give this presentation and learn more about troposphere, stratosphere interaction and monsoon weather extremes. This also gives me the opportunity to visit IITM and India for the first time. Thank you. Today, I'm going to talk about GPEX and organized convection. GPEX means Global Precipitation Experiment. Is really exciting new 10-year WCRP lighthouse activity. And of course, WCRP means World Climate Research Program. This is the primary international research program focusing on science. It has 6 core long-term projects, including GPEX, Global Energy and Water Experiments, and APAC. And then there is another one, is CNIVA, International Monsoon Panel Office, is hosted by IITM, and the Monsoon Panel reports to GPEX and CNIVA. WCRP also has 6 lighthouse, essentially 5 to 10-year projects. One of them is GPEX. Just give you an example of the flavor of WCP programs. GPEX has been a WCRP core project for more than 30 years. We are currently organizing more than 30 different international projects under GPEX through 4 panels: the global atmosphere, the gas panel, land surface, glass panel, regional hydroclimate, GHP, and the global and regional data analysis, GDAP. In contrast, GPEX was just launched last October as a brand new lighthouse activity by WCRP. Today, I'm going to give you a brief overview of GPEX. Because I'm still doing science full-time, I still want to take this opportunity to briefly overview some of our own work on 2 storm types. The primary motivation for GPEX is that despite the progress in the past few decades, the progress in understanding and predicting precipitation remains too slow relative to the societal relevance and impacts. As an example, this figure shows the US 2023 $1 billion weather and climate disasters. 26 of the 28 disasters were associated with precipitation or extreme precipitation. And the remaining 2 were due to a lack of precipitation leading to droughts and wildfires. And these extreme precipitation events are often associated with organized convection. And GPEX is well represented by different projects in the world. Just give you some flavor. On the APAC project is represented by Takeshi. And the Monsoon panel represented by Annalisa. And actually, we also have a specific scientist, AP Dimri, from India, to give you a flavor of international and balanced representation when we develop the science plan. We have just published the science plan in the Bulletin of American Meteorological Society. You can read the article there to get more information about GPEX. Overall, GPEX will address the 4 science questions related to the 4 key points in the 4 boxes, including reducing precipitation product uncertainties, improve understanding of precipitation and related processes, improve precipitation prediction and projection, and enhance regional and local capacity. We will address these 4 questions through 4 activities or 4 working groups, WG1 to WG4. In particular, WG1 will focus on WCRP years of precipitation by doing globally coordinated field campaigns on 4 storm types, as represented by the 4 icons within the circle. And then our strategy is to combine surface-based, airborne, and satellite observations, computer models, and artificial intelligence, most importantly, human creativity, as indicated by the 5 icons outside the circle. To provide a little bit more details, WG1 is about WCRP years of precipitation. We will coordinate global field campaigns with in situ, airborne, and satellite measurements of the atmosphere, land, and ocean, focusing on different storm types: atmospheric rivers, mesoscale convective systems, monsoons, and tropical cyclones. We recognize these storms occur over different seasons and between seasons over different regions. Our most important task at this time is to engage scientists and funding agencies to identify potential anchor projects for each storm type. We have made some good progress, but we are still not there yet. This is the high-risk part because of all the moving pieces. We are still looking for those anchor projects from multi-nation efforts. If you have something just from one nation, that's not good enough as our anchor project, because we are going to build internationally coordinated field campaigns around the anchor projects. What we want is ambitious and also high risk. We want to do something that has never been done in our profession. We have done measurements in the atmosphere just like the Gates, best known, 50 years ago. We have done air-sea interaction. A good example is Toga Core. We have done extensive field campaigns for land atmosphere interaction. What we want is land, atmosphere, ocean, and ice all together. It's exciting, but also makes us very nervous. WG2 will focus on precipitation relevant databases. There are multiple tasks. For example, we will work with other projects to develop global and regional gridded precipitation relevant databases with high temporal and spatial resolutions. This will include the rescue of historic data that might disappear. We hope to rescue them before they disappear. We also want to work with other projects to set up a baseline surface precipitation network over lands. There are already such network for radiation measurements, very well known. There are also such network for greenhouse gases. But precipitation is much more challenging because you cannot just throw out a rain gauge claim you have a baseline. It's much more complicated because of the nature of precipitation. We need to measure the amount and also the type and also size distribution and the phase. WG3 is about precipitation modeling, precipitation, and process understanding. For example, we are going to coordinate multi-scale analysis and precipitation forecasts and support the establishment of multi-model databases. The key is to reach out to forecasting centers and the major modeling centers. Ask them to work with us, set up the requirements, then provide those outputs for the international community to use, and then using the new and historical data to evaluate those products and hence help improving the model so that it's mutually beneficial. We have already identified the representative from ECMWF and NCEP, including Fanny Yang from NCEP in the audience here. And we are going to reach out to other major forecasting and modeling centers to see if they are interested in working with us. WG4 is about capacity development. What we want to emphasize is to train early career scientists, particularly those from the global south, through doing science. Because there are many other projects doing other capacity development, we feel the best way to do the training is through doing the science. The planning is we're going to take 1 to 3 years for the pre-YOP phase to finish our YOP planning and seek and encourage large GPEX endorsed anchor projects for the global field campaigns. Then we do the YOP, to 1 to 3 years, then for post-YOP activities for another 2 to 3 years. And the planning is we finish GPEX activity on time, then transition into WCRP core projects in 2 to 3 years. After YOP, this would happen in 8 to 10 years. So we envision a 10-year-long GPEX program. And I already list quite a few bullets or activities. They are not going to be done by GPEX. The precipitation is the focus of GPEX, but it's also the focus, essentially, of most of the other international projects. So our strategy for GPEX is to focus on very few activities, but do them very well with strong partnership. And then what do we need from you? First, we are still seeking leadership to coordinate field campaigns on each storm type, development of precipitation-related data sets, and the modeling and precipitation experiments. We have issued a call for SSG members, working group members, and co-chairs. We have already identified the candidates for SSG, submitted the list for WCRP approval. After that, we are going to appoint the co-chairs. For the members, we are not going to appoint all the members because we want to reserve rooms for the appointment of those leaders who will lead specific activities. That means we are going to issue additional call for membership. So far, we have received more than 100 applications and nominations. So it's quite competitive and also show the community's strong interest in GPEX. And we are also seeking information about major field campaigns for the next 5 years for coordination. And of course, if you have any other new ideas, please let us know. Now, let me switch the gear to share some of our own work on two storm types. And my group's own research style is to look look for problems we have ideas rather than focus on specific area. That's why we work on different topics. Today, I just give you a flavor of our research on two storm types. One is about tropic cyclones. Of course, for US, we use hurricanes, and we have been doing seasonal hurricane forecasting for 10 years. We issue our forecasting in early June and also early April, and we have been doing pretty well. And in particular, 2017 has been a special year for our forecasting. It's a real forecasting. Our operational center in the US and other centers and groups predicted the average hurricane season with 6 to 7 hurricanes and 2 to 3 major hurricanes. Those are categories 3 to 5. In contrast, we predicted in early June a super active hurricane season with 11 hurricanes and 6 major hurricanes. We were very nervous because we were outside the 2 sigma of all other centers. But we hung there, we did not change. In the end, we were very happy because in the end, from observations, 6 major hurricanes and 10 total hurricanes, very substantial damages. We lost more than 3,000 people and causing nearly $300 billion economic loss. And one major hurricane was Hurricane Harvey, making the landfall in Texas. We also use that case to try to understand what's the impact of soil moisture on hurricane forecasting. In general, there are hundreds of papers published about the local effect of soil moisture on local precipitation, and also the soil moisture effect on downstream precipitation. One of the best work was done in the 90s by European Center scientists. Those are well known, but here we talk about the potential new finding, the upstream effect. To make sure we have the confidence of the model results, we have to make sure the control simulation using OFF can do a decent job. The model domain is shown in the left panel, and the right panel shows the forecasted track of Hurricane Harvey in pink and observation in black line. You can see the model did a fairly good job simulating the landfall in Texas, then back off to the ocean, making landfall again in Louisiana. So this gives us some confidence in our sensitivity tests. And for the top right panel, we simply replace the soil moisture by saturated value. Results are very similar to the control simulation. In contrast, if the initial soil moisture is very dry, situation is very different. We see the track is drifted westwards after the landfall in Texas and stays there and die out. And then the issue is why soil moisture can have such a powerful impact. Through additional analysis, what we have found is if you have very dry soil, you would generate a warmer and a deeper boundary layer. This would generate an anticyclonic perturbation as indicated by the schematic streamline perturbation in the bottom panel. And this would kick the track of Hurricane Harvey westwards. Then after landfall, the more powerful force is the interaction between hurricane and the mid-latitude circulation, leading to the eventual die-off of Hurricane Harvey for that case in Texas. Now let me switch the gear to monsoons, and we have heard about the excitement, even last night's performance about monsoons. We have evaluated the CMIP model simulation of North American monsoon. And here we share one result. We compare the model simulation of the monsoon seasonal cycle for the core monsoon region. The core monsoon region is indicated by the small box here. Results are shown in the bottom panel. Solid line, observation, dashed line, multi-model ensemble, and the shade indicating the spread. You can see the multi-model mean can simulate the onset, the peak very well. But most of the models have trouble simulating the ending of the monsoon. Actually, many of the models never have the ending of the monsoon. Then we did the additional analysis to understand why that's the case. And as an example, results are shown in the right figure. Here, we are showing the precipitation in colors, the 850 hectopascal winds in vectors, and 850 hectopascal height in contours. Observation top panel, best models that can simulate the ending of monsoon, middle panel, and the worst models that cannot simulate the ending in the bottom panel. The key difference between worst model and observation is the two tropical highs, subtropical highs, are pushed westwards with weaker strength. And the consequence is the moisture from the tropics can keep moving up to the core monsoon region. And hence, monsoon never ends in those worst models. And for this study, and for many other studies, we need to define monsoons. Remember, even this week, people are talking about, is this a pre-monsoon rainfall or is this monsoon rainfall? So this definition is important. And you can use precipitation and the wind and other quantities for the definition. Mostly worldwide, people try to use precipitation, but there are issues with precipitation data over sparsely populated regions and over global ocean. The daily precipitation data from satellites have higher uncertainties. And also for North American monsoon, even over the different areas, the people use different criteria of precipitation to define monsoon onset and retreats. And then the question we want to raise is, can we have a globally unified monsoon onset and retreat index without any tunable parameters for all regions? And our starting point, we realize a good idea is to use water vapor, because from data, water vapor, here we use a vertically integrated water vapor or precipitable water or PW is one of the most reliable measurements you can make from space. So the data quality is better. And then water vapor is smoother than precipitation. And here as an example, we show two sites, one Mumbai, one my own backyard in southern Arizona. And I'm so happy because this is from 20 years ago. Now I'm standing here not too far away from Mumbai. At least I made the right choice in terms of those two sites, particularly for this meeting. You see the seasonal cycle of water vapor quite different, obviously. For global applications, we must normalize the index as defined there. And then we simply define our monsoon onset or retreat dates for a particular 1 degree by 1 degree grid G as the first day when NWPI is greater or less than the golden ratio. For 3 consecutive days, in 7 of the 9 grids centered at this particular grid in 3 days. And the normalized values are shown in the bottom panel. If you just use this very simple universal criteria, you can define the onset for Mumbai climatology is about the 10th of June. And so today when you issue, it starts officially. That means this year's monsoon season for this region is normal. In contrast, for my own backyard, the normal monsoon onset date would be 4th of July. And now we can show the global results. Why do we even do this? Because I feel monsoon is a global phenomenon. It's not really just regional, it's global to start with. Here you can see clearly the global progression from north to south over different regions with different regional characteristics. For example, you can see for India, the interval between contours is not uniform. That means the progression of monsoon has intermittency and jump in the movement. In contrast, for Africa, the intervals are fairly uniform, meaning there is not as much jump and intermittency. And the other finding is the starting date of monsoon is earlier, around the June day 120 for Asia and also for Africa, but much later for North America. We also pick up a few points for comparison. I mean, for example, India is indicated, hopefully I don't mess up here. That's Mumbai. And so we provide our own median value using globally unified criteria. With the only tunable parameter is golden ratio. We didn't tune because my own perception is monsoon is the beauty of nature and the golden ratio is linked to beauty. And it turns out this artistic interpretation is consistent with the artistic interpretation of performers last night. And of course, when I try to add this point in my paper, reviewers did not like that and force us to delete the linkage to art. And they say, you know, just not right between science and art. But for me, that's a higher level to have the unification between science and art, but that's a different story. You can see our climatology of monsoon onset agree very well of the reported value in the literature based on local criteria. And we can talk about similar conclusions for the global monsoon retreats. An interesting thing is here we found for North Pacific. Let me see, make sure I see it correctly. It's here. Our own retreat dates is June day 312, and from literature is 333. Some of you might tell me which one is more appropriate. And then, essentially, I never regarded myself as a monsoon group, but we were really surprised by the good results. So we ask ourselves, why results are so good using water vapor? So we did the further analysis, published another paper. And one result is shown here. We simply compute the correlation between daily precipitation and PW over US. Now you can see clearly, only over a monsoon region, there is a very strong correlation between P and PW. For non-monsoon regions, correlation very weak, and it can be even negative. That explains our results, why PW is so good for monsoon onset and retreat over monsoon regions, but they are not good enough by themselves to indicate monsoon regions. Here are the conclusions I'm not going to read. The bottom line is for GPEX. This is the right time to get involved in different capacities, not only for GPEX, also for GWEX and APAC and other international projects. And I have also shared some of our own research for your entertainment. Thank you.
Thank you very much, Professor Zheng. It has been an excellent talk, and you explained us the journey through GPEX and your publications. And we will invite questions now from audience. Yeah. Dr. Krishna.
Thank you, Gupin. It was an excellent talk. You showed the last the correlation between precipitation and precipitable water. So you see negative values in the western side, northwest side. So why is that? So there is no monsoon precipitation there.
Well, of course, we have done additional analysis. Essentially, this pattern represents three climate regimes of the climate over US. And it's interesting, for example, for the southeastern US, precipitation is always there, but you have a strong seasonal cycle of PW because there is a water vapor capacity dependence on temperature. In contrast, only over monsoon region, both the precipitation occurs in summer and also PW also increase along with the increase of temperature.
Thank you. Are there more questions?
Thank you for the very informative presentation. It's really good to see the GPEX is organizing WCRP year of precipitation. But can you say when it will be? Are you planning that one within next few years, or is that long-term plan?
Well, this is the most important part. So there is no simple answer. Our first step is to find anchor projects. Once we find one or two for the given storm type, we will initiate the additional planning involving scientists from different countries. Essentially, we would tell all the people who want to participate, say, we have decided what periods would be part of WCRP years of precipitation, how exciting it is. You can bring our science plan and the science excitement to your managers, get them excited, give you money. Then you can participate, not only addressing issues of your own interests for your country and also for our whole profession. By sharing data and doing all analysis together, we all benefit. But everybody owns me, saying, Shuben, this could take up to 5 years. My response is that we already know some of the big things are in the planning stage. We are not doing this starting today. I have been doing this almost 2 years ago. So we do have some momentum, but we don't know which season, which year, or this time. One thing for sure, one international team wants to push for taking this year because they are doing some large-scale field campaign, and I told them it's too soon. Other countries cannot have enough time to participate. So we know not going to be this year. Next year, the chance is not very high if starting from early next year, but if very late next year, it's possible.
Yeah. Regarding the precipitable water index for onset and withdrawal. So how many grid points you are considering for computing the minimum, maximum?
There we use 10 years of data for that for this paper at that time. And if we redo this 20 years ago, now there would be 30 years of data, and also resolution would be greater than 1 degree. And keep in mind, we use 3 by 3 grids because monsoon onset is not a single point. Instead, it's a large scale. So you want to have 3 degree by 3 degree to provide some large scale context. And part of the reason is the difficulty of separating pre-monsoon activities versus actual activities after the monsoon onset. So that's part of the strategy. If we use higher spatial resolution data, then we need to use more grid boxes to make sure we are talking about the large scale monsoon onset rather than pixel level monsoon onset.
Thank you.
Are there more questions? I just have one question. Actually, you talked about observations. Are there also joint model intercomparison or model experiments that are planned under GPEX?
Yes. So one major thing is working with major modeling forecasting centers. So that's part we are guaranteed to do, and we are already moving in that direction. The other things I already list a few bullets there, but we do recognize there are many other international projects doing modeling. So we will still do some modeling if we have something very special. For example, one idea we are thinking about is WCRP has digital Earth. That's a high resolution global modeling and regional modeling. And then one idea could be multi-scale modeling. Then with the goal to use the high resolution modeling to help understanding coarse resolution modeling results and model parameterization, and also use coarse resolution modeling provide some insights for the improvement of high resolution modeling, because the real challenge of kilometer scale modeling is the data volume. When you have a coarse resolution, you do detailed analysis because data volume you can handle. Once you go to kilometer scale modeling with high frequency model outputs, for most of the scientists, you cannot handle data anymore. So what do? You show pretty figures. You show the animation from model and satellite saying, hey, they look great. But that's not the understanding. Have that understanding has been challenging. And who knows? So that's just one idea. Essentially, we do not have to do that. But if we do, we need to have a good leader with innovative ideas. Then we're going to check with other existing projects. Are we stepping on your toes? Or you feel that's a good idea? In this way, we can have more synergy rather than repetition of each other's work.
Thank you. Thank you very much for this exciting talk. Yeah, our next talk is by Professor Toru Tarao. He's from Kagawa University, Japan. And he's going to talk about the Asian summer monsoon circulation and precipitation in view of high moist static energy air mass. Welcome, Professor Toru Tarao. Thank you.
You know. Yes, maybe now. Okay, thank you very much. I'm sorry, my voice is very bad now, and so I got some cold, and so yesterday I couldn't talk. Totally, I couldn't talk, but today I can talk somewhat like this voice, very hard-boiled voice, and I can enjoy here to show you some result of my research. And also, yeah, just now, Shubin-san talked about GPEX. So I'm also leading one project, AsiaPEX. AsiaPEX is ASEAN Precipitation Experiment. It is very related with the GPEX also. So, and also we are making coordination about that the ASEAN countries for that research of that ASEAN precipitation. ASEAN precipitation also very much difficult to understand. So as you know, it is very big source of uncertainty of climate model output. Anyway, but today I talk somewhat more not freely about my own research and also my group research. And so I try to talk about that ASEAN monsoon circulation and precipitation in view of high moist static energy areas. So the lower tropospheric air is very important for the how such a high big convections making that ASEAN monsoon circulation. So the lower tropospheric high moist static energy is very important for me. So I'm talking this, and today I cannot talk so much maybe. So this part maybe most of this will be skipped, but we have many languages in northeastern part of Indian subcontinent, including Bangladesh and Assam and Meghalaya Plateau. And so we are doing some research there. And so we are focusing on some rainfall observations. So we had 40 languages and maintaining from the 2004 up to now. So still now it is going on. So using them, we can validate that the premium observation, and also we got a very good result. So that the rainfall in the Meghalaya Plateau, it is very important place for us because it has much biggest rainfall in annual rainfall in the world over the land region. and it has very big underestimation like this. So it is less than half. So it is very big underestimation can be found from that trim PR. So such observation is done that it should be merged with the GPEX. But anyway, today, somewhat talking about some different topic. So for understanding that the monsoon circulation, so that the heating of the atmosphere is essential anyway. And the most biggest heating is found in around this region also, but this I painted here, but here also has to painted maybe for fairness. But the monsoon region is characterized by very high heating, including this region and also the Tibetan Plateau region. Because of that, because of this very high latitude heating, that the median temperature is totally reversed. The median temperature gradient reverse occurring in this very high, big regions in the Asian continent. Such a big reverse is very difficult to find in any different regions, including southern hemisphere and northern hemisphere. So this is very important. So we are usually using the Q1, Q2 perspective. It was very important, and maybe there's no need to explain you here about this. So I skip this. And Q1, Q2 is defined like this. It is a non-conservative part of heating and also non-conservative part of the moisture. So it can explain the heating so much. Very clearly, you can explain that. Okay. Thank you very much. And so this is some result. So as you know, that very big Q1, Q2 can be found in some regions. For example, the monsoon onset phase, Luan found a very big Q1 and Q2 here. So it indicates a very big heating by the strong convection in the Bay of Bengal or such a Bengal Plain regions here. So this tool is very important, very informative. So I want to use, sometimes I can use it for some diagnosing that here that the important heating occurring. What is the mechanism of that? And it is used for the global level also, so that Q1, Q2 can be explained that why that median temperature gradient occurring in this region. It's very clear. But at the same time, I like to explain another view of that explaining the heating. So I call it the high moisture static energy AMS and high dry static energy AMS view. So this is some old result of my research. It's in 1999. So it is a mass amount, mass density of that specific isentropic layer. At that time, I used 355 Kelvin layer. And it is a pre-monsoon season, so from up to April. Maybe pre-monsoon season. At that time, we cannot find any accumulation of the TMS at 355 hectopascal Kelvin. But after May, so we found some accumulation begin in the May to June, so from very center point of that monsoon region. And after that, it is spread over a very big region. So this is very clearly showing that the Asian monsoon anticyclone, so what we call, sometimes we call it the Tibetan high. So this structure is very prominent, and so such a very high accumulation cannot be found in different regions, different seasons. And after monsoon withdrawal, it is diminishing and so finished. So such a high concentration of the highly heated air is very much characterizing that the structure of monsoon circulation. If we think about the vertical cutting and section of this region, and we can vertical section, and it is the Hofmeier diagram. It is from it is from June to September in 1983. It is one snapshot, 1983. we can find such a high accumulation of air mass can be found. This is the pressure coordinate. So it is just representing how much amount of it is mass of the air is accumulated in each isentropic surfaces or layers. So we can find that the air mass between 350 to 360 kelvins is increasing and decreasing this way. Clearly, it is increasing and decreasing. And it coincided with that the lowering, so subsiding some such isentropic tropes in the upper middle troposphere. So it indicates, almost just indicates that the temperature of this region. And so after monsoon onset, anyway, so this shaded region increased very rapidly. After that, after monsoon onset, it is diminishes very clearly. And also it undergo several times of interseasonal variability, and it is increasing, decreasing. And it is clearly related with that lower tropospheric westerly, and also that the meridional temperature gradient also clearly it is related with each other. So this accumulation of high potential temperature air mass in the upper troposphere have to be very essential for this mechanism. So we did some analysis, and so here we have greater high here. So it is clearly dropping much air mass inside this region. And this is the rotational part. This is the divergent part of that air movement. So clearly, this is very small and this is very big. So that the air mass is circulating in this area very long time, and after that, sometimes going out here or here. So this is some trajectory. So many trajectory is confined in this Asian monsoon region, and it is circulating this region. So, and this is a vertical structure of the equivalent potential temperature in this region. And we can see that in the lower troposphere, we have high equivalent potential temperature air mass. And the upper troposphere, we have high potential temperature air mass. It's almost equivalent to potential temperature in the upper troposphere because of lacking of the moisture. So the lower troposphere accumulation of high potential temperature air mass, and it should be transported by the big convection to the upper troposphere. It makes upper tropospheric potential temperature, high potential temperature air mass. So such a relationship has to be very important. So we set this setting as view, and we begin some analysis. And at that time, it was 1999 when I wrote this paper. At that time, so it was very difficult to get because that the analysis very almost twice a day only. That and so also the very resolution very low. But now that the data is available, so we can do some analysis using the ERA fiber or MERA 2 or something. So we can develop this view analysis from now. And so this is this time. So this is really happy to me because we can communicate with the people, the atmospheric chemical history this time. So they have a very important analysis from that very long time ago. And so they accumulated many results about the accumulation of chemical tracers in the upper troposphere. So it should be very much related with our work. And so using this data, ERA5 this time, and this is very huge data, so I couldn't make so long analysis. So I began from 2017, one case study. And we used all the data, and also globally, I use data for January and July. And in other region, I use from data from March to October now. And so this is very nice because the 0.25 degree resolution, and also 1,000 to 78 Pascal data available up to ground surface. And using many parameters, we can estimate how the potential temperature in the lower troposphere or the moisture energy in the lower troposphere. And so using this, we made analysis. And also, we did some analysis using GS map. It is a TRIM and also GPM research team is doing this product, making this products. And this way, it gives us very clear view about where the rainfall in each hour and each location. So by 0.1 and 0.1 degree, very high so spatial resolution. And this is our framework. So it is a part of high static energy air mass. A part of high static energy air mass can be found in the troposphere. UTHCC can be found. So it is clearly it should follow that the mass continuous law. It is clearly we should do that. And so it is the conservation term around here, but residual. Anytime we have residual. Residual can be divided into three parts. One is radiative, another one is convective, and another the other things. The other may be small, or some erroneous term may be coming here. And also the radiation and cloud is some different time scales and the magnitude they have. So we will divide into these three parts. And if you think about that, the radiation term is only radiation term is available there. On the if that no convection, it means if no rain is there at that time, this almost equivalent to this. So we can evaluate that the radiative forcing through this term. So using this, if we can think about like this, then we can model this by Newtonian cooling for this term. So such a way, we are dividing and we are analyzing some result. So and some result. So it is in the January. So it is the northern hemisphere winter. So in southern hemisphere, we have this monsoon. So the Australian monsoon. So Australian region have also the producing the very big amount of the high dry static energy mass in the troposphere, making anticyclonic circulation in the southern hemisphere. It's very high. But in the Asian monsoon season, it is much more high, very strong anticyclone developing and very big amount of atmosphere that the air mass is accumulated in the troposphere. And if we make it the vertical section, it is accumulated in this region before monsoon onset like this, but it is like inflating in this region, and it pushes down the isentrops, and it makes a very big heating or temperature rise in this region. It makes temperature gradient reversal in this Asian region. And in the lower troposphere, we cannot find such a very high equivalent potential temperature air mass before the monsoon onset. But after the monsoon onset season, we can find very high equivalent potential temperature air mass in the Asian region, especially in the northeastern part of India first phase. And so it is a very big amount. Sometimes it may go up to this region to make this accumulation. So it is our idea. And so it is a global view of the such a high potential equivalent potential temperature air mass in the lower troposphere. And we can find in the other season and the other region, we cannot find out so much accumulation of that high equivalent potential temperature air larger than this 360 Kelvin used for this. And so this is very specific to the Asian monsoon region in the summer season. And this is it global accumulated amount of such a high potential temperature air mass larger than 360 hectopascals. And usually almost no accumulation. But after the Asian monsoon onset, just before the onset, this amount getting very high, and so it is continuous high, and after the monsoon onset, it is reduced. So this can be found only in this region, and in other region we cannot find it. And so it is a high moisture taking the air mass, how it is behavior of this region. And it is May. I think it is one of the most onset in this region, 2017 occur. And it is the 11 to 15 May. It is 27 pentat data. And this is shows how much mass, kilograms of air mass can be found for each square meters for these regions density. And so this is the most biggest region is surrounded here. It is just north of the Bay of Bengal, and the Bengal Plain region is surrounded by this big high amount of the high precipitation air mass. And it can be a source of the troposphere heating. And after that, it spread over the Tibet to Bay of Bengal region. Bay of Bengal is very important for this part. So up to 20 May, 28 pentat, that region, very important, is confined to the Bay of Bengal and Bengal Plain region here. And other region, some there, but not so much important. But after that, such a high equivalent potential temperature was spreading over another regions. And so after this, どっか行ったかなちょっとない。そうか。I forget getting at the July and August. Sorry. Under July and August, at that time, this region and also especially the northern part of India become very important. And in this region, so high accumulation can be found. Much larger than this. It's very high accumulation can be found northern part of India after that. And this is, if we think about upper tropospheric high potential temperature air mass, high dry static energy air mass, then at that time we can think about such a mass continuous equation. We can find that the unconservative term and how much amount of air is created or appear there inconservatively. So we can estimate this using this equation, and we can find this region. This region is very important for all that the April to September time span. And so this region could be very important for the injection of the high potential temperature air mass into the upper troposphere in 2017. And time series also can be evaluated. And we can find 3 times of increase of upper tropospheric high dry static energy increase. So inconservative increase 3 times like this. And we divided this into several regions, and we can find that the region in this region is very important factor for this 3 increase timings. And here we can find this blue curve is very much explaining the 3 times increase of the tropospheric high potential temperature air mass. So from this we can think about that for the onset phase from the middle of May to early June, this region can be very important and leading role is played by this region. But after that, it becomes very, many regions can produce such a very high potential temperature air mass. And here is a very complicated. Sometimes the Tibetan Plateau also play important role sometimes. And we checked that how is it lower tropospheric accumulated high potential temperature air mass in this region, using the radio zone in the Guwahati and also Dhaka from Wyoming I get. And so we evaluated, and we can find very big underestimation in this region and very big some overestimation in Dhaka region. And sometimes these changes not matching each other. So we are now thinking about some observation for this region, and we can estimate how is that the accumulation can be created in the lower troposphere. And this is another thing. So for that clear sky region, So no rainfall. We can evaluate it using that the GS map. So apparently no rain for that days and that time. How is that the relationship between the accumulation and its dissipation? And we can find very clear relationship, and it can indicate that the Newtonian cooling occurring in the upper atmosphere. So it is just that subsidence due to that too much accumulation of the high potential temperature mass in the upper atmosphere. And so our GPEX is a part of GPEX activity now. And so it is now gathering many people from the many countries in Asia. And now we want to be a kind of umbrella of the people in the ASEAN climate researchers. And we will do some field campaign in 2020s, in the later half of the 2020s, and 2 or 3 years, maybe 2 years, maybe. And so we may make big coordinating field campaign. And so one of these maybe our observation in the northeastern part of Indian subcontinent, we putting some the region we put automatic user stations, and also that the GNSS to measure that the upper tropospheric accumulated precipitable water. And also we are doing 4 times daily observation in some convective days, such observation now beginning. And this year, this May, we did one field campaign there, and so we can get some radios on there, and also GPS receiver also will be easy suited. We get much data about these surface observation also, so we can use this, and so we can think about how our result shows that the mechanism of the accumulation of our atmospheric high potential temperature mass. Yes, this is summary. So maybe time. So. Thank you. That's all. Thank you very much.
Thank you very much, Professor Teru Tarao. We can take up some questions.
Oh, thank you so much for a very informative presentation. I'm very interested in Asia PAX. So can you show us your slide once again about Asia PAX? Oh, the next slide, yeah. I mean, diagram. Yeah, that one. So based on this diagram, I assume you guys are planning field campaign in the year of 2025.
In this period, 2 years maybe. So maybe so 25, maybe somewhat difficult. But yeah, but maybe during this period we will conduct that field campaign anyway. So it's very much.
Yeah, if that plan is not fixed yet, presumably Korean Met Office, KMA, may want to join this field camp.
Yeah, thank you very much. It's very much helpful. And also we should coordinate with GPEX and also Indian people some thinking about how some field campaigns. So such a way we should negotiate and decide which timing is the best. Thank you very much.
Yeah. Thank you for the very insightful talks. It has bring out the very important. It gives an important concept how the air mass is injection to the means at a higher level. This moist static, the high air mass is connection with the higher level. It's most important. That has been seen from your presentation. So I have some clarification. So when I've seen in your presentation, this is more inclined towards the Bay of Bengal, the high air mass. So, but if you see the upper level, the anticyclone circulation, it is also has been a large variabilities. It's not only for the Bay of Bengal, it also covering the northern part of Indian region, and it's extending right over the different modes also there. How this air mass, this variability, this moist static high energy of air mass, and that the variability is also correlated directly, or like it behaves different?
Yes, so we are calculating. This is the very much July average, but we can calculate this much more high time resolution, and we can find how such a air mass is moving it is sometimes it makes some different shapes, and it sometimes coming this portion and sometimes going this way, and so it is making some wave type structure. So it varies very much, and month to month. So in August, it's somewhat going much more northern part. So such a variability is also very important. They're very interesting, and not so much research about that, but it should be very important. So maybe we can collaborate about that. And also, but we somewhat checked some the amount of this accumulation and the lower tropospheric westerly jet and the median temperature gradient. All three are very nicely coincide each other. So it indicates such a interseasonal variability clearly. Yes. Thank you very much.
Yeah, one very quick query on the same previous slide, like you mentioned about the observation during the campaign. So I saw this, there is some plan for the radar also, apart from the radiation data. So for radar, whether do you have any plan for the Northeast Indian region, or because there are two radars are already operational in Calcutta and the Guwahati. So are there?
I see. Yeah, so there are some collaboration with ISRO, and also from our not as GPEX, but the SOMO project. Our some regional project has some collaboration with them, and ISRO has one very nice radar in Cherrapunji. They sometimes they supply some data, and we do some collaborative analysis. So it's the beginning. And also, I heard some plan is there in IMD also to install some more in this region. So such a data has to be very important. So for specifically for this campaign, I made some the MOU with the IMD, and so we get some data exchange for this period in this year. So such a way we may collaborate with them, and we can distribute data from them to some community. So it's mine. Thank you.
Thank you, Professor Tarao. Thanks for interesting talk. So next I'll invite the next speaker, Harshad Hanmante, a PhD student from IITM Pune. He is talking about the rain type classification and convective clustering in heavy rain events, radar observations, and numerical simulations. Harshad.
Hello. Good morning, all. My name is Harshad Hanmante. First of all, I thanks STIPMEX organization for giving me this opportunity to present my PhD work. My name is Harshad Hanmante, and my topic for today's presentation is rain type classification and convective clustering in high rain events for radar observation and numerical simulations. My outline for today's presentation is: first, convective organization and its importance; second, methods for rain type classification and convective aggregation; third, radar observation features of heavy rain events during JJS 2022. And lastly, initial results from high resolution model simulation and its comparison with observation for extreme heavy rain event. So what is convective organization? In tropics, convection exhibits a hierarchy of scale ranging from few kilometers and hours associated with individual cloud system to the mesoscale of squall lines and cloud clusters to the synoptic scale of tropical cyclone. Atmospheric precipitation falls from a spectrum of cloud types that are convective and stratiform. These categories imply the nature of vertical air motion producing precipitation along with the divergence and latent heating profiles. Deep convection in the tropics is sometimes scattered throughout the domain, or sometimes it's spatially clustered in one region. This variable spatial distribution of convection is known as organization, and it is related with severe weather such as floods and hail. Tan et al. Showed the most of the observed regional increase in the tropic precipitation are associated with an increase in frequency of organized convection. Therefore, the quantification of convective organization becomes important. Importance of monsoon zone. During Indian summer monsoon, mean rainfall is characterized by three strong convection areas. Those are monsoon core zone, Western Ghats, and Northeast India. Over monsoon zones, synoptic systems such as monsoon lows and depressions are often passed during monsoon. As a result, deep moist convection is frequent and which produces widespread and a very heavy rain over monsoon zone. Hence, proper depiction of convection features such as spatial cluster structure, diurnal cycle, lifetime evolution, precipitation, and large-scale environments is crucial to know the features of precipitating cloud population and its organization. Data methodology and rain type classification for convective aggregation. On the left panel, we can see Seapole Radar IITM at Atmospheric Research Test Bell site in monsoon core zone. This mesoscale coverage of Seapole Radar has 300 km by 300 kilometers range, allows us to capture large convective systems for characterizing convective activity and organization. High resolution Seapole radar data, 6-minute and 1 kilometer resolution, is used to stratify radar echoes into different rain types such as convective, stratiform, mixed, isolated convective core, isolated convective fringe, and weak echoes. Rain type classification is based on the intensity and the horizontal structures of reflectivity. Cluster metrics are applied to the radar identified convective echoes to measure the degree of convective organization and their spatial distribution in radar domain. Here we can see, if we consider one organization index like simple cloud aggregation index, what it says, if there is a less clustered and small size, we can say that there is a large SCI values which shows less aggregated, whereas more clustered and large size has smaller SCI values that indicates more aggregation. Thus, this radar-based convective clustering is used as an observational basis for quantitative comparison of convective organization in the numerical model. This slide shows the time series of observed rainfall, and radar-derived rain types during JJS. We have taken observations of daily rainfall from disdrometer situated in Silkheda, whereas the bottom panel shows the Seapole radar derived from rain types. Here we can see number of occurrence of aerial dominance of stratium type is more as compared to other rains. Thus, during a more convective active days, the peak stratiform occurrence resembles a peak in daily contribution to the volumetric rain, whereas most of the precipitation that occurs in convective suppressed periods such as late July, late August to the early September few with isolated convective core entities. We identified heavy rain events during JJS 2022 as per described by IMD. There are 4 events in which event 3 is very extremely rainfall of around 293 mm. This slide is the composite showing the spatial distribution of rain types during heavy rain episodes. Here we can see the mean stratiform occurrence is around 62%, followed by the mixed 24%, isolated convective fringe, that is 10%, convective 3%, and isolated convective core 1%. There is a southwest quadrant of radar shows a highest occurrence of broad stratiform regions of the rain. Composite diurnal cycle. Here, the diagonal cycle of the rain shows two peaks at around 14 hours and early morning. Here, the peak of convective objects is at 13 hours, shown in figure C, could be associated with the afternoon rain peak maxima, whereas the stratiform clouds peak during the midnight or early morning in the rain. Now, this is the case we are going to be used. The figure B shows the animation plot with the interval of 13 minutes, satellite data, infrared, brightness temperature less than 241. It shows the last case features where the westward to northeast propagation of cold cloud systems is seen. Whereas on the right panel, we can see animation plot of 6-minute radar reflectivity and rain types at 2 km. Here we can see the mesoscale features, which shows the deep and intense convection, of brightness temperature less than 225 and reflectivity greater than 40 dBz. These are the families of convective cell organized in time and space, resulting a spatial extensive convective system. For this case, convective permitting WRF simulation is made. This is my model experiment. We have used WRF version 3.9. We have 3 domains, where the domain 1 has a resolution of 25 km, domain 2 5 km, and domain 3 1 km, which we are comparing with our radar observations. Here, similar methods are applied to the radar observation to compare the model simulated data, that is the radar reflectivity, over the domain 3. As a result, rain types and convective clustering are similarly identified in radar observations and model simulations, making it possible for their comparison. The results. These are the examples of radar convection, where we can see they have scenes such as isolated shallow cells, some small cluster of convection with limited stratiform, squall lines associated with stratiform area, and widespread stratiform. The top panel shows the radar observation reflectivity at 2 km, whereas the bottom panel shows the model simulated reflectivity at 2 km. Here, we can see the scenes of convection shows a notable similarity and differences, and spatial extent of convective activity is an indication of organization. This slide explains the time evolution of rain types during heavy events for radar observation and WRF model. On the left panel, we can see the rain types of radar observation, whereas on the right panel, we can see the radar types in WRF simulations. There are 2 distinct phases of observed, which each phase 24 hours before peak rainfall and 24 hours after peak rainfall. The temporal evolution of rain types between observation and models are noted with similarities and differences. For both observation and model, the increase and decrease amounts of all rain types are seen in phase 1 and phase 2. In the model, stratiform occurrence are underestimated, whereas the convective occurrence are overestimated. We can also see the broadside areas are often, they are also often are a signature of organized convection. This slide explains the time evolution of organized metrics during heavy rain events for observation, radar observation, and WRF model. Here, we have considered the organization index SCI. It represents when there is a small value of SCI, that means more convective clustering, and large value of SCI means high convective of clustering. So in phase 1, we can see that increase in N this behavior is inferred as more convective cells. That means less convective organization, which is favorable for condition of convection. Whereas phase 2, a convection becomes more aggregated, that is less number of convective objects and less SCI. That means it is more aggregated, which resembles to the cloud elements merge into fewer elements. That is the signature of bright side stratform. We can also see there is a lag of 5 hours in model and observation. This is the phasor diagram of convective elements and the index of organization, where we can see WRF, the convective objects are more overestimated, and observation there are less. We can also see there is a resemblance in the scatter plot, where we can see the blue indicates phase 1 and phase 2. In phase 1, we can see there is an increase in convective organization, but a decrease in IORG. Same with the increase in convective objects and decrease in IORG. Whereas in phase 2, there is an increase in IORG, which indicates there is a convective organization, and decrease in N. This is the composite CFATs of reflectivity, relieving the depth and internal vertical structures of rain types for radar observations and model. Here, vertical structures are resolved. The model reflectivities, which is in the bottom panel, of all rain types below 5 kilometers are the similar observations with the radar observed reflectivity. While above 5 kilometers, they exhibit a greater range, which is over predicted by model. Summary: the degree of convective aggregation and spatial arrangement during heavy rain events are studied using organization indices for convective clustering based on convective objects. Matrices measures the degree of organization for each snapshot of radar volume and different parameters of clouds presenting the radar domain. Study provides the nature of precipitating clouds of their internal vertical structures based on the polarimetric data and qualified convective clustering over monsoon zone. This radar-based observation clustering has potential for assessing the degree of convective organization in high-resolution NWP models. Thank you.
Thank you, Arshad. We can take up some questions.
Nice talk.
Thank you.
The stratiform and convective range.
Yes.
How you calculate it based on that SCAI index?
So this
before
rain type classification
from the radar. The
Okay.
radar you showed.
So it's the algorithm that depends on the radar reflectivity. Based on the radar reflectivity threshold,
But you also showed that SCAI some index, no?
that is SCI index.
So was that so your algorithm is based on that?
That algorithm is based on convective objects, the distance between convective objects, and the radar domain distance. So that we have formula, and in that we incorporated and calculated it.
So it's a very good talk again. Do you have any data associated with surface conditions like soil moisture state, which show as precursors for the convection?
No, sir.
Okay.
Yeah.
And I also wanted to ask you about the other thing. You mentioned you are underestimating stratiform and overestimating convective. Is it other way around that you're probably over? I mean, the cause and relation, because it's the same set of population. When you're underestimating one, you're overestimating the other.
Yeah.
Seems to me because you're using some of the controls, you may be getting more. So it's a convective cases, which are probably more of a control than the stratiform.
Yeah.
So you may want to look at that logic.
Yes.
Okay, thanks.
Hi, Anand.
Yes.
So yeah, good talk. So a few suggestions. So when you plot the figures, make the y-axis similar. Otherwise, we can't compare. Okay, one is going out to 14, another 10, 150, 40. So okay, and keep plot the model observation the same figure. That's better. Number one. Number two is what you said, that is generic. All model, irrespective of regional or global, they produce convective more, stratiform less. Okay. Yeah. So you should work on that. How to improve the stratiform using the Bhopal art data, etc., etc. The third suggestion is you said the model stratiform, right? Somewhere you showed. So that is basically the rain from model microphysics. Correct. So it is not exactly apple to apple of your radar derived stratiform and model stratiform. Yes.
So sorry to say, but
Have you made the model large scale rainfall?
Yeah.
The rainfall that is coming from model microphysics.
Yeah.
Have you made it equivalent to radar derived?
Yes, sir.
How did you do that? Can you explain?
Yes, sir. Here, that my third domain has a. This is my third domain, which is which resembles the same area that the radar domain is, where my radar actual observations are there.
Fine.
There I the horizontal resolution in the model is 1 kilometer by 1 kilometer with a run of I getting output files per 6 minutes, which are like apple to apple comparison with observation.
No, it's not. No. So point is, your radar is computing stratiform rainfall, radar or satellite. They have a different algorithm. Model computes stratiform, not stratiform, actually large scale rainfall, which is not, you get a total rainfall, you get a convective rainfall in model, right? Convective rainfall comes from convective parameterization. It's not convective rainfall like radar computes. Okay. So when we compare model with the radar or satellite, either we have to use some simulator to make the model output equivalent to radar and satellite. Otherwise, we have to say it is radar derived convective and stratiform. This is model produced convective and large scale.
Okay.
Okay. Yeah.
Okay. Sachin, want to
clarify, in this work, we have not compared the radar rain versus the model rain. It is actually the reflectivity based estimation where we are comparing the stratiform and convective rain types based on the reflectivity. So the baseline is common. So we are taking radar observed reflectivity versus model simulated reflectivity. So we are not comparing, what you are claiming is that we are not comparing the rain from the model and comparing rain with the observation. So what he has presented is absolutely correct.
Yeah, myself is Babu from NARL Gadanki. So can you go to last slide? Yeah, say these parameters, we can get it from WAR. So using open source. So that the differential reflectivity, RKDP, all these. So that we can compare directly with the WAR fund, the dual pole. That will be a interesting exercise.
Sure.
Thank you.
Yeah.
one last question. Yeah. Very nice talk, Harshad.
Thank you.
I'm just curious whether you looked at overshooting material from this MCS.
Okay.
Did you see anything overshooting the tropopause in this case?
With this, as this is the initial run, we are like progressing, but we'll get to it. As still now, we are not seeing those things.
Okay.
But yeah, we'll definitely do those.
Yeah, these are very nice observations.
Okay.
Thank you.
Thank you.
Harshad, here. Yeah. Very nice talk. I just have one suggestion that you also do an prior comparison of the thermodynamics from the model and observations, because you have a lot of, I think somebody was asking about other data sets available. So you'll have more confidence in what you're actually presenting, and also try to find some faults where exactly you're getting the disparity, right?
Sure.
Okay, thank you.
Thank you.
Thank you very much. I think this is now we have come to the end of this session. And we would like to thank all 4 speakers. And it was an excellent session with a lot of questions also, a lot of interest. Thank you all. I think I will now hand it over to the organizers. Suvarna.
For chairing session. So now we will go for mementos to the speakers. So I'll request both of you to be on the stage.
Yeah, that's okay. I would like to request chair and co-chair to come up to the stage to present the mementos to the speaker. And first, I would like to request Professor Zubin Zhang, University of Arizona. Sir, kindly come up to the stage to receive the mementos. I would like to request Professor Toru Terao, Kagawa University, Japan. I would like to request Mr. Harsat S. Hanmante from Indian Institute of Tropical Meteorology, Pune. Thank you, ma'am and sir. I would like to request Professor Debni Yogi, University of Texas, Austin, USA, to come up to the stage to present the mementos to our co-chair and chair. Yeah. Thank you, sir. We'll be dispersing for tea break now for 15 minutes. The tea is prepared outside the auditorium. And before that, I have a few announcements. Those who have not collected your poster at the basement, kindly, you can take the posters back. And we will be back again in this at this place for this next session after 15 minutes of the tea break. Thank you.
I welcome you all to session 12 of STIPMEX, AI or ML in weather prediction. I request Dr. E.N. Rajagopal to chair this session and Dr. C. Ganshilan to co-chair this session. I now request the chair and co-chair of this session to lead the session. Thank you.
Thank you. Actually, Dr. Ganeshan is not available, so I have to chair the whole session. Before we start, Dr. Krishnan has got some announcements to make.
Maybe you can invite Professor Dev.
Yeah, Professor Dev, just go up.
Yeah. So I'll welcome on behalf of the co-chair. We now invite Professor Dev Niyogi from the University of Texas to give the talk on cities, urban digital twins, and weather and climate extremes. Before he does that, I also take this opportunity to announce on behalf of the IMS that Professor Dev Niyogi was conferred the IMS fellowship last year. And the certificate will be given very soon, the award certificate. Meanwhile, it's my great pleasure and honor to just read out the brief citation for Professor Dev Niyogi. Yeah. So I have also discussed this matter with the IMS president, and he said, please go ahead and announce. The IMS fellowship is bestowed to Professor Dev Niyogi of the University of Texas by the Indian Meteorological Society in recognition of his outstanding contributions to the meteorological sciences, including the work on the role of cities and land surface feedbacks on weather and climate extremes, which have influenced a generation of researchers and guided the knowledge transfer into community modeling systems, climate decision tools, and open data portals, as well as for many impactful global partnerships. So the IMS is privileged to confer upon Professor Dev Niyogi the fellowship of the Indian Meteorological Society. The actual certificate will be issued later at an appropriate occasion. Welcome, Professor Dev Niyogi. Yeah. So Dev can now go ahead with his
You can take your
regular
stage.
talk. Thank you.
Dave, you have 25 minutes, but 20 minutes we'll sound you so that we can finish in time. Yeah. So he'll be speaking on cities, urban digital twins, and weather and climate extremes.
Fit in though. The disadvantage of long hair, this can't fit in, I guess. Yeah. Okay. Put it here, sir. Okay. All right. Well, good morning, and I think this is going to be problematic with my hair. So good morning, and what I'm going to be doing is talking a bit about the work we have been doing with cities, urban digital twins, and extreme weather. And yesterday, those of you heard Kerry Manuel talk about some of the work associated with the land feedback and CAPE, made me think about some of the aspects about the roles of land feedback with regards to the convection and some of the extreme events that we could be starting to take a different look from, and particularly the role associated with urbanization is one of those distinct heterogeneities which don't go away normally, and they are always present. And so that's one of the things I'll be talking about. Shujin, we also had the conversation about the precipitation and so forth, and in the previous session, and there was a reference to the urban, the Digital Earth's lighthouse activity. And so this is also a part of the Digital Earth lighthouse activity, where there is an atmospheric urban digital twin initiative as part of that. And so some of the work that I'll be showing builds on the findings that we had from there. So before we go too far, what I want to highlight is that most of the research that we have is obviously very useful, but it is not right away usable because it needs to be converted into some sort of a process skill analysis with either data sets or some sort of a tools before it can be put in the context of usability. And the reason for that is we are considering multi-scale processes. These multi-scale processes could be in the context of, like, you have an El Nino or La Nina, you have a large-scale changes, and at the other extreme, you have the turbulence and other representation in the models. And each of these features can't necessarily parameterized efficiently, and we do a lot of approximations. So the scales that we have restrict the model in the manner in which they are particularly well suited for. But the way we experience is, of course, not restricted to the model, and we experience some of the impacts associated with all the scales. If you have not already had this feeling going through the horrendous hot summer in Pune, Delhi, and any other city that has been experiencing it right now, we have seen that weather and climate emergency across the cities. And part of that is because there has been an increase in the number of extremes. Cities have to have eventualities planned. Many cities are trying to come up with plans. Sachin was mentioning about how they're trying to do for air quality. I know cities are trying to come up with regards to heat plans and so forth. And there are tremendous infrastructure investments that the cities have to put in. And there are questions that are coming up. How much should they be investing? What should be the design criteria? Should it be the same on criteria that was used when the initial design came up? Or should there be a different criteria about the pipes, the culverts, and so on and so forth? And in fact, the next IPCC report, the only special report that will be associated with that assessment is going to be on cities. And so cities now are really becoming one of those important aspects that we need to start identifying. How do we model them? How do we start putting them into our assessments? We do know that cities are exposed to a variety of heat, flood, lightning, hail, you name it, and those sorts of extremes. And those impacts are perhaps disproportionately higher, and they're increasing at a disproportionately higher rate in the cities as compared to the non-cities or in the rural areas. And this is something that has been emerging over a period of time. But so the question comes, do cities contribute to create these weather extremes or climate extremes that they are impacted by? That's the first question. And we certainly know things like urban heat island, for instance, have been created by the cities. They're the urban heat island. This is a report, by the way, in 2014 saying that the future heat waves are going to get higher, hotter. So certainly it is ominous that it has been seeing that in the last 10 years. So heat island effect, as you see, urban areas and the surrounding regions have a differential. That temperature is higher over the urban area. And as a result of which, the impervious material and all the heat that is released from the urban sources stays in the atmosphere, and that increases the temperature. And so when you have a heat or a heat wave event, you also have the urban heating, and that's where people have a threshold that they cross in terms of the exposure and the heat that you have. And in fact, if you look at it in the context of why it is called the heat island, you just have to see the temperature contours. This is from the EcoStress data set and in and around the northern India, Delhi region. And you can see parts of those heat island very prominently into this particular map as to how those heat hotspots start emerging, and hence the name heat island. So have these heat islands been evolving? So on the left, what you see is a heat island that was actually observed for 1890 to 1894 for Paris, France. And you can see it was roughly about a 1 degree to 1.5 degree urban heat island, a kind of feedback. And more recently, it can be seen that it has gone to about 2.5 degree or so. So that has been reconstructed. So heat islands have always existed, except that they have now become bigger and more prominent because cities have themselves become bigger and more prominent. Now, as you know, heat temperature, high temperature is simply a symptom of an underlying condition. And this is something Pico has known. And so if those of you, by the way, who have not watched Bollywood movies while you're in India, this is one of the things you must actually experience. It's a thing to do. So what is the symptom that heat islands are actually holding? And the symptom that they are holding is that in addition to changes in the temperature, there is a direct feedback on the whole thermodynamic characteristics, which result in the change of the rainfall characteristics, and the whole humidity structure in the atmosphere. What happens is the city heats up, you have a zone of convergence that starts coming in. That zone of convergence also sometimes gets a moisture gradients coming up. And as a result of which, when you have a convection creation, yesterday, if you recall Kerry's talk, that convection initiation occurring because of some of the Cape values, and then that gets advected downwind of the city. So this feature that cities actually create some sort of the thunderstorms or clouds convection, and that gets advected downwind of the city, and then create zones where you have preferentially higher rainfall amounts relative to some other parts of the city, has been something people have been noticing. In fact, in the media, they also call it sometimes the Beltline effect, because Beltline is the highway around the city, and the storms seem to be much higher as against over the city and so forth. So why do we not talk about the rainfall effects or the rainfall extremes that come up from the cities and the changes that have been taking up in the context of the large-scale urban features? So the reason for that is that the thermal effects are much more straightforward. You change a city, you have a temperature, you change a grid, the change in temperature is noted over that grid. So it's a very linear change. But when you change a location and you make it more urbanized, the dynamics of that effect is where you're going to have to consider when you're trying to see the changes that are occurring with regards to the rainfall patterns. In other words, that a change can be at one location in terms of the local characteristics, but the rainfall change would be at some other location. And then understanding and tying those two together is where the challenge lies in the dynamical setup. There are other such factors that come up, that the storms can actually go intensify over the city, downwind of the city, around the city, and it is all based on the characteristics associated with how the city and other things are there. So there are a lot of non-linear features that come up into that setup. This feature that cities are actually changing the weather and climate, especially from the rainfall perspective, has been known from about 70s and even earlier perhaps. There have been field experiments that have been recorded for that. One of the well-known feature, there was a great debate in the magazine Science related to a rainfall anomaly from urban areas, so-called Laporte anomaly. And that has been something that was used in a field experiment called Microphysics. So Zubin, when you're looking at the field studies that you know to study, this could be one of the things to look for. So there's a large field experiment that was taken place called Microphysics, and then there has been subsequent work by a number of researchers. I'm just simply going to list them because I know there were some questions from the students yesterday about urban feedbacks and so forth. So there are these series of papers and studies that have occurred, which I would just leave it there, and I hope that in the subsequent time, you will go through the presentation and look at these papers. But what we have found is that changes in soil moisture, changes in cities, changes in vegetation, changes in the size of the city, changes in the height of the buildings, changes with regards to the shape of the city, all of these features, anytime there is a change, that change does not stay just over the city, it changes the environment around it, and as the environment is changed, with that, you have a change in with regards to what happens to the whole convective potential around that city. And that then eventually changes the rainfall in that feature. Now, there are two mechanisms by which this happens. One is with regards to the heating and the roughness, which creates that convergence zone that I mentioned. And the other is what Ram is an expert on, and things like related to radiation and aerosols and other features that are coming. And so those have a feedback with regards to how the cloud and other factors have a change with regards to the properties that come in. And so those are the two prominent pathways by which people have been thinking that there could be a landscape change occurring with regards to the feedback occurring with regards to the rainfall change. One just by the heating and other associated with aerosols and radiation changes. So those two are the features that to look for. Incidentally, a very nice field experiment is naturally occurring because of the Paris Olympics. And then there is a WCRP RDP, the research demonstration project, going on with regards to the Paris Olympic demonstration for forecast and other things. And a lot of that data are becoming available in terms of test cases and so forth. And we're trying to do some real-time simulations associated with that. So it's a beautiful data set that has been generated for the Paris Olympic. So what do we know? We know, looking at all the observations, that roughly about 18% of the rainfall increases downwind of the city. 16% over the city. It's not happening all at the same time. It depends on the conditions based on the heat island intensity, low versus high intensity. High intensity, it goes more downwind. Low intensity of urban heat, it is over the city. And then there are changes and so forth. Typically, this occurs 20 to 50 kilometers from the city. Typically, it also happens not only downwind, but sometimes upwind on the city. So in other words, there are changes occurring with regards to the whole rainfall characteristics. So what we have established is cities are changing their climate with regards to temperature. They're changing their climate with regards to the rainfall extremes. The question comes up, are these features interacting? And here's, by the way, an example of what we see with regards to that aerosol and radiation interacting and how nonlinear this is. That on weekdays, you can get some extreme rainfall downwind of Chicago. On non-weekdays, when you have a lack of aerosols, then you can have a different kind of spatial climatology of rainfall. And so if you don't disaggregate this kind of data set into aerosol, urban heat, and so forth, you get a very muddled signature, and you can't really come out with the processes in terms of the explainability of those results going forward. So that's the key point I want to say. I already mentioned that about the size, shape, and other factors that come in. So now the question comes, is this feature about urban areas changing rainfall, changing their temperatures and so forth, something that is happening with only few locations, or is this something that is happening globally? And so the question for that, the answer for that is that if you look at all the literature that is available on urban heat island, there is a very consistent signature no matter where that heat island exists. And in fact, this is a global study with about 400 cities. And you find that in Africa, it is about 1 degree. In Europe, it is about 2 degrees of a surface urban heat island intensity. And that is consistently noted in terms of the changes that you can see with regards to the global picture with regards to heat island. So irrespective of where you are, you have a presence of heat island. The same question we try to understand with regards to rainfall. And so for that, we took about 1,000 cities, 1,033 cities across the world, started putting all that information together. You clustered the data set with regards to different upwind, downwind condition. You analyze that information. And the picture you get is that you get a dramatic increase in terms of the rainfall patterns in Africa, in South America, North America, etc. And of course, Oceania, because there are very few cities, the percentage look large. But the point is, again, from cities, we are seeing a feedback on rainfall, which is much more global in nature. And it is not just because of one large city or one other city and so forth. Now, that brings us to three important questions. When we are trying to look at understanding that we want to finally use all the climate and weather information in places where we have largest number of people living, where we have largest of our investments going on, namely the cities, do we need to represent cities in these weather and climate models? If we have to do that, how much of a detail do we need to put? Can we just implicitly have it by representing the changes in albedo? Do we need to have some other features like the details associated with the dynamical features with regards to the aerosol emissions or the anthropogenic heat flux and so forth? What are the feedbacks that we absolutely must have? Is it just the roughness effect? Is it some other form of effect where we are creating a different boundary layer? What are the features that we need to have to be embedded when we are trying to represent cities in a weather and climate model? And the third part, which is actually an interesting question that comes up, is that many a time we always have been looking at when we're trying to say what is the future climate over a city, we have been downscaling that information, where you're taking the larger grid and then downscaling it by taking statistical or dynamical models over the city. However, if you look at it from the context of the greenhouse emissions, it is always the upscaling, that they are taking data in the street over the locations, identifying regions, and then they are upscaling that information. And so the question comes up, should we be downscaling or should we be upscaling from city scale or a street scale to building scale and zonal scale, and then come up with some sort of aggregation process rather than a disaggregation process that we are doing right now? Okay, so speaking of climate downscaling, we did this for our own city, the city of Austin. And the reason I show this is that this was done for all the CMIP6. We bring it down to the city level. We provide that information with all the CMIP6 output, downscale it, and so forth. And in fact, just yesterday, it was released to the council such that the city can then start creating some sort of infrastructure planning over the next 5 years in terms of what it does and so forth. The point I'm trying to make is this is a typical approach we use when we say we want to project climate over a city. Downscale it, use it, come up with some indices, use those indices such that somebody can start making information analysis about it. Now, what happens is when you start talking to users, those users say they need much more granularity of a data that is often at a hectometer level or even at a very hyperlocal level. If you're trying to do something with regards to the heat, say the heat and health impact, or if you're trying to understand the exposure levels, or if you're trying to do the energy the emission levels that would be estimated for a future climate, you require something which is at a much local, hyperlocal data resolution than what we have. So essentially what they go by is that they have the experiences that they have. Some parts of the city are warmer, some places that they have a problem and so forth. And so the question comes, how do we now create this hyperlocal data set? So this is where knowing that cities are impacted, knowing that cities are impacting, and then there is a need for something better than what we have been doing with statistical downscaling, brings us to the context of how can we now start using things like the emulators, digital twins, and dynamical models in terms of creating such hyperlocal data sets. And that's what I'm going to try and show in the next whatever few minutes I have. So recall that most places we have this scale interaction going on. Recall that there are many machine learning applications that are now coming up with regards to what is going on with regards to different climate aspects. There are different types of emulators, digital twins that have been coming up. Fortnite you hear of, Climax you hear of, you have the Pangu weather and so forth. Several of them use the same approach. You take the data, you train the data set, you then apply it, and for different cases. It's more of a data management and a data handling exercise, and then you use different transformers and different emulators in trying to come up with the analysis. If you go to an urban area and then say we want an urban digital twin, and the geographers have essentially been doing GIS-based analysis. You take different layers, put all of that information together, and they use that for the process of their own planning. Now, if you go to an atmospheric aspect of it, what we find that there is nothing available right now which considers the dynamics when you start to come up with this local scale information associated with urban digital twins. And this is where some of our exciting new work that has been going on. Now, what is an atmospheric digital twin? A digital twin, almost everything that people can think of, they have been trying it. I think even the dance yesterday was probably an example of a digital twin, that everything is trying to twin each other. But essentially, there are few things that need to be there in a modeling system before it gets termed as a digital twin in much of the literature. First and foremost, whatever you're creating has to be incredibly fast, almost 100,000 times or 10,000 times or whatever that may be. So it has to be incredibly fast. There has to be some element of AI/ML that is being embedded in terms of speeding that process. Otherwise, you're not going to get that feature. Very often, you have an end user or a decision that is coming through. That decision could almost be, I'm creating an input for another model, or I'm using something which could be for a stakeholder. So there is a stakeholder involved. And then there is an integration of different data sets. And the most important factor, scalability, that it is going very easily across the scales, which the dynamical models have not been able to do so. In fact, there is a archive paper in which, in fact, Ram was also involved, in terms of trying to define some of the aspects associated with the digital twins and how what could be the factors that we should be looking at, so forth. Very quickly, so what do these digital twins generally do? They rely on what has been happening in the vision community. The vision community has done an incredible job in developing their algorithms, the GPUs and so forth, where you take a coarse resolution image and you could run it into a series of processes and come up with a very high resolution output or a high resolution image out of that. So what we do is we take our data set, we generally contour it, then we make an image. And that image is our figure, rainfall, temperature, contour, or whatever that may be. Now imagine that you run that particular coarse resolution data set with some of the emulators that are available from the vision community, SRCNN or so whatever people talk about. And now you create a very high resolution image out of that using the algorithms that they have. Then you ask the question, what data would have created that high resolution image? And so you back calculate that data. And that is how you're actually going from a very coarse resolution data set to a very high resolution data set without having to go through any of the physics that we typically rely on, but simply relying on what has been done by the vision community. This is at core majority of what the downscaling algorithms have been doing, no matter what flavor they come in. So one of which we have been doing has been taking the station data, putting that station data with regards to the coarse resolution, then running it through an emulator, do some supervised learning, and then out of that, a 5-kilometer rainfall data product can become a 300-meter high resolution data product. This we have done for a 25-year period. And so now instead of a 5-kilometer resolution climatology, you have a 300-meter 25-year climatology, which the city finds much more useful because it starts giving you some information which is much more local than what could be over a block. Another one we have been doing is a Meteogan, where we have been, instead of a station point, looking at gridded data sets, where you have reanalysis and so forth. And then there are some of these results for the rain events over Delhi, in fact, where you take the 5-kilometer chirps data, and you can see the Meteogan creating some of the hyper-resolution output at 300 meter, how it has been providing some of the details and so forth. So you have this other cases going on. You can do these improvements associated with Meteogan, where you are actually using the physical changes that are taking place. And it is not, so there is a little bit of physics now that we add. You don't let just the vision community decide how the hyper-resolution should be done, but we know urban areas should be warmer, trees should be cooler, and those sorts of things. And then you go through something what is known as a belief network. And in that belief network, you start creating more of the physics-driven approaches and come up with this high-resolution data set. Now, when all of this starts coming together, you can have something which is guiding your actual data sets that go into your physics-based model. Because we have a good understanding. What we don't have is a locally representative high-resolution data sets for many of our problems. And so we are now starting to use, instead of creating just the output of a meteorological variable, actually creating the input that goes to the physics-driven model. One of which is this building data set. I'll quickly scan through this, saying that if you improve the urban representation, you are able to improve the variability that you see in rainfall because you are capturing the micro features within a city and the hotspots associated with hot and cold features. We can use computer vision like you do in a video game, and you create a city. And by deep learning, we created Chicago. And then that Chicago, which is a video-based Chicago, is input to the model, and you can run the model as if it's a real LiDAR data. And you can get a lot of these emulators with regards to the data sets and so forth. These are not just visual appealing. They actually have information. What is the street height? What is the thing? And use that information to update your tables that you can then locally update in a more dynamic manner. That becomes a feature. We have created new data sets for urban areas. We have created new urban fields, and we have now a global building height data sets, open source, available for WRF and other weather models, that which is the building height for all the buildings that you can put across the city. So that data set is available. You can take a look at it by going to UT Globus, download that, and you can use for your studies. I'll stop that here, saying that one of the things that then comes up is you can use this kind of information with regards to the changes that can be used. about how this information can be really used with regards to very local scale information that we typically won't have available. This is 2-meter in exposure over a 10-year period based on a very high emulator that can be used for all sort of applications. So again, I'll end up by saying that these are all tools and products available from what we can get. There's a fire and smoke, there are data quality, there is a digital twin for future energy use and so forth. But at the end, I want to say that this has been great for creating scenarios. This is great for creating local data sets. It is great for using emulators. But while we are all been so excited about it, I really again want to highlight that much of the progress we have had, much of the training that we are doing is only because we have had tremendous progress from physics-based model. So none of this should ever come on the cost of the progress we do with the physics-based models, but that we use this to supplement what we cannot do with the physics-based model. And with that, I'll end, and thank you very much, Chair, for extending. Thank you.
Thank you, Professor Dev Niyogi, for this interesting talk. The talk is open for questions.
Rama's question.
Thank you, Dev. That's a very stirring presentation of the urban weather climate problem. I have actually more than 2 questions, but I have just 2 questions. In the first part of the talk, you spoke of the disaggregation of the data to tease out what the factors are contributing to, I suppose, any phenomena like heat waves. Have you tried to see if disaggregation between coastal cities and those in the interior?
Yes.
Does it sort of add more, because the coastal influences can be different from the urban, from the central, sort of more inland cities?
Yes. So in fact, Florida is like a whole nation by itself because it's a double coastal. And so the PNAS one is more of a global one, which was done on a daily analysis, monthly analysis. And then there is a US-wide rainfall change for cities, which we have done on a diurnal basis. And in that, we had to cluster it with coastal, inland terrain and all that. So there is a local terrain effect of urbanization. So what was interesting, though, is that we thought when you have a complicated terrain, urban area may be a secondary factor. But even when you do apple-to-apple comparison, terrain, urbanized terrain, non-urbanized terrain, there is a signature associated with that urban feature.
If I may ask another question. The second one was that towards the end of your talk, and I really subscribe to your maxim at the end about the physical models being necessary, but the downscaled or any other version which gives more heightened information about cities being actually also necessary. I want to kind of refer to bias corrections that have to be made, especially when you make projections. Can you comment on what the degree of simplicity or difficulty there is in trying to do that to make good projections?
Yeah, so from the city perspective, when we did the SIMIP6, we had there were 2 options available, the quantile approach, which typically people use. But apparently now there are machine learning approaches where people are saying that can do better. The problem we had with that was explainability, because people are going to use that data for making some decisions, and it is not feasible to explain to them on a consistent manner and have that knowledge also transmitted to end users, secondary users. So that is a big challenge. And any guidance from IPCC or others, how it should be taken to the city level and how it can be used from the end user perspective, that we can always keep referencing, would be a good path for a better usability with minimal errors, I feel. But I think that's what you're already doing, hence the questions perhaps. Yeah.
One more question.
Just a very nice talk, Dev. I'm just thinking, how will you incorporate the uncertainty? Because any of this decision making also need to have a control on the uncertainty associated with that, especially for policy and various aspects.
So that's a good question. In fact, that climate projection report that we have for the city, if you look at the preface, I put that A, this is not a legal document. It is not a policy prescriptive document. This is really the first cut where you start having conversation about this particular issue. And when you're going to do something which is much more precise in terms of an infrastructure design and so forth, you use this, but really start doing a much more robust analysis just for that part. And so this, when you're trying to do projections or downscaling or so forth, these are really the first cut analysis, which are rather than just saying the city is warm. Now I tell Pashan is 2 degrees cooler than say university or something like that. So we have that very high granularity. Now, when you put that information with the heat and the health data, for instance, that people have, it makes sense to them that why are more people having, say, cardiac issues in a particular street and those sorts of things. And they can make interpretation. We don't have to, is what I would say.
Yeah, in this whole process, also the high resolution observations also should play a very important role, right?
Absolutely. So
we
the belief-based approach that I talked about, the belief-based approach is just another term where they're essentially taking the ad hoc data sets that are available, satellite or in situ, and they're finding it's a sort of like a conditional assimilation into the data set. So it is absolutely, the more observations you have, the more robust your local, hyperlocal downscaling will be.
Okay,
Thank you.
Yeah, thank you.
I mean, we'll take the question later because we're all running short of time. Thank you, Professor Dev Niyogi. We have the next talk, which is actually a recorded one from Dr. Ferren Genting from University of Columbia, US. Audio नहीं है.
So what I wanted to talk about today is talking about machine learning for climate sciences, and a lot of in my interest in the last couple of years, and thinking about how do we get from just emulation, which we've seen a lot, I would say exploding even in the last couple of years, to what I would call new discoveries. And I would like to acknowledge funding from the National Science Foundation, the Schmidt Futures, and also the European Research Council. So basically, this talk is going to be split into two parts. The first one will be to talk about climate uncertainties and the role of subgrid processes. And then we'll try to go that AI can be used to go beyond just climate process emulation, but can also be used to potentially make new discoveries. And that's, to me, the most exciting part, I would say. So the current gap we're actually trying to target, especially as part of our center here, LEAP, is to think about climate adaptation, right? So we are witnessing more and more flooding events, droughts, heat waves, and even new types of events, such as the smoke that we saw from wildfires back in New York last year. And to adapt, I would say that we need two components. The first one is we need to have accurate information about the future. And typically what we do is we use climate models, so physically based models, to actually do that into the future and to provide climate projections. And we also need to have data at scale, right? So we need to be able to put this data into the hand of the broadest range of stakeholders. That's something we've been doing actually as part of our center. If you're interested, so we've developed this new platform with a new data visualization platform. So you could think of that like Google Maps for climate data and climate adaptation. But if you're interested, feel free to reach out. I won't be talking about that today, but that's something I'm quite passionate about. The unfortunate truth is when we think about climate models is that there are still a lot of uncertainties across the different models. And this is here just a very simple example thinking of the CMIP6, so the latest generation of climate models, and looking at a very simple benchmark, which is the global surface air temperature and how it's actually predicted and projected to be changing with the warming climate. And even if we put aside the shared socioeconomic pathways, so the SSP, so the amount of greenhouse gas emissions and the concentrations that are being used in those models, you can see that this doesn't have a huge impact up to 2050, right? And in fact, a lot of the uncertainties still remain even when we fix those shared socioeconomic pathways. And a lot of the uncertainties are basically coming from physics, and the fact that we are making some assumptions in those models. And I'll get into that in two. But the main point is that even for a simple metric, the model spread is almost as large as the magnitude of the change we are actually trying to project. So that's really getting into a complicated projection setup. It's not just at the global scale. We could start zooming in, for instance, at the regional scale. So this is an example of the US in the summer, and thinking about extremes of precipitation. And you can see that a typical coarse model, the community atmospheric model, latest generation, it's actually struggling to really capture the extremes. And we know that the extremes of rainfall are so important from an impact perspective, because they lead to flooding and inundation. And when we compare that to the observation, again, those extremes are actually much higher. And typical climate models tend to what we call drizzle too much. They tend to have too weak precipitation, and that's coming in too frequent. One hopeful sign, though, is that when we get to high resolution simulations, they tend to do a better job, and we could argue the details. In fact, they can struggle at times as well, but overall, they do a better job. And one of the reasons is they can actually kind of capture thunderstorms, right, and big storms and organize like mesoscale convective systems. So for instance, in India, a lot of that creating the monsoon. So those things are better captured by models that can directly resolve. And it's not just on the physical side of things. We could actually think about the biogeochemical cycle, and on the land side and the ocean side, we actually have huge uncertainties when we think about projections of future carbon uptake. And this has dramatic implications when we think about mitigation strategies, because right now about 1/3 of carbon is being picked up by the land, maybe slightly less by the ocean, but roughly speaking, they do a great service in terms of removing a lot of carbon from the atmosphere. And so only a fraction of that stays in the atmosphere, the rest being picked up by the ocean and the land. And so those natural solutions and those natural carbon uptakes are actually extremely important for the pathway we are on. So why do we have all of those uncertainties? And we can actually get back to some of the specifics of that. And in fact, a lot of that is due to unknown or unresolved physics. For instance, if we think about clouds, even thunderstorms, they tend to be too small and much smaller than the typical grid size of a climate model, which tends to be on the order of hundreds of kilometers. Same goes for ocean eddies, and which tend to be much smaller than the grid size. And they are very important because they capture a lot of the heat and they control a lot of the heat being stored into the ocean. Clouds are, of course, very important for the temperature of the planet. They regulate a lot of the planet climate, and so they are also very important to capture. On the right-hand side, when we think about the biogeochemical cycle, especially over land, a lot of that is regulated by photosynthesis, which is the largest carbon sink. And the issue is that photosynthesis is quite well known at the leaf level, but it's very complicated even at the tree level, and forget about the ecosystem when you have a lot of diversity. So that makes things much more complicated. And so really a lot of those errors are really dominating the uncertainties I showed you earlier, especially at timescales up to 50 years. Beyond that, of course, the type of shared socioeconomic pathway we're on is going to be very quick. So how can we move beyond this kind of status quo and try to find strategies to improve climate modeling? One way around that is when we have unresolved process, we just need to resolve the process, right? That would be a straightforward way to do that. But of course, compute will come on the way and is going to be kind of the bottleneck there, right? So on the top right corner, we have kind of the objective, which is to have like global, long-term century scale simulation. So basically a climate model. And then you have those different buckets where you can actually resolve for like shorter time periods, but over a reduced domain with higher resolution simulations, such as cloud resolving models that are roughly on the order of kilometer scale, largely simulations on the orders of tens of meter scale, and direct numerical simulation that can go down to millimeter scale. And the main point is that there's always a trade-off between compute and how much we can resolve. So we need to define the domain, and the type of compute will actually limit for how long we can run those simulations and how big the domain can be, right? And the other concern is that as we move to the climate models, we tend to parameterize more and more, right? We have more and more of the scales that tend to be unresolved. And therefore, we need to rely on more and more empirical representation or phenological representation of those physical processes. And so one way to improve things would be the obvious thing is to just more compute, right? Just give us more computing power. But it's pretty obvious that we could check that very quickly, that there will be a limit to that in terms of how much we can resolve. Maybe we could have global cloud resolving models over a century timescale. But even then, it becomes tricky because we need to have multiple ensemble members. We actually need to tweak and tune those models, which is very, very computationally expensive. So it's beyond the scale of what we can do right now. So it's not trivial to actually make them realistic Earth system and climate models. And we could get down to direct numerical simulation, but again, I mean, the compute is going to be going on the way. There might be some breakthroughs, but at this stage, we are not there. Another strategy that's been kind of exploding over the last couple of years has been to use machine learning as an emulation. And here, the idea and the story is to think that we can run simulations at shorter timescales, over shorter timescales, and like lower domains, smaller domains. But we can actually learn from them, and we can really leap across scale, right? That's the idea, where you can learn from finer resolution simulation and then import that knowledge into the coarser scale simulation, so you can better represent the processes you're not resolving, right? So you're kind of bypassing that complexity, and we can really leverage pretty efficiently the type of simulations we have, which is a great way to actually get to the climate model scale. But I'd like to emphasize, and I think it's quite critical because that's oftentimes forgotten, is that we also have a lot of unknown processes, right? So for instance, if we think about something very important, microphysics, or liquid or ice microphysics is going to be very critical for cloud formation and also for the Earth, for the albedo of the clouds. And we just don't understand that. I mean, we have some understanding, some phenological models, but they tend to be very empirical. We can think about the landscape where we have so much diversity that it's beyond any type of capacity to actually try to do a good job there, right? So we need to be empirical there. And our best bet in that case is to use a combination of observations. Could be in situ, could be laboratory-based experiment, or even remote sensing to try and learn or improve the representation of those processes. It can be machine learning, but not just machine learning, right? It could be some physics-based type of approach. But we just need to keep in mind that there are still many, many processes that we don't understand and that we will never be able to resolve. So at this stage, we have a huge opportunity, I would argue, which is coming from the fact that we have a massive amount of data. For instance, we have many, many satellites observing the Earth every single day, spinning across the globe. We also have high resolution simulations. So I mentioned, for instance, those global cloud resolving models. They are great. They have also lots of deficiencies, but they can really be harvested to actually get a good sense of, for instance, the formation of deep clouds. And of course, what you need is once you have those data sets, and they are very big, terabytes or petabytes of data, you need to have an efficient way to actually harvest those data sets. And that's typically beyond traditional algorithms. And that's where AI and machine learning really can be transformative as a way to harvest and understand potentially some of those data sets. So I'll show you a couple of examples in terms of how we can use the AI for climate process emulation. And then we'll get into how that can be used for some other things. And Here, the strategy will be typically we'll take a high resolution simulation. So for instance, a global cloud resolving simulation could be some large simulation. And we're going to coarse grain the field so it looks like the coarse resolution model that's going to be the target, right? So think of that as the climate model on the order of hundreds of kilometers, and we want to be at the same scale. And then we are just going to use the high resolution model to define some what we call supervised learning experiment, where we know what we want to get, and we are going to make the prediction over that field, right? And then we're going to plug that back into the host model. So we are going to swap modules between a physics-based parameterization, and we are going to replace that by a neural network. And just to give you a little bit of a flair of some of the things my group and colleagues have been doing, as part of LEAP Center, we've been working on land-atmosphere interactions. So thinking about how stomata, for instance, are actually regulating the exchange of heat and moisture and carbon at the land surface. We can think about wildfires. So that's something we've been trying to work quite a bit on, because wildfires are very complicated, very difficult to put some physics onto that, and they tend to be very stochastic. So they are great methods to be using some sort of generative AI, for instance, for wildfires. Another example is snow water equivalent. So thinking about the amount of snow in especially high elevation regions, very important for water resources. And that's a place where models tend to be typically biased because the physics of snow is non-trivial, like how do you actually melt the snowpack, very complicated, like how do you condense it and compact it, and all sorts of evaporation processes. And that's a place where you can actually correct your model pretty well if you have observations. And that tends to work well and can generalize very well across different basins. So that's very helpful. Turbulence is another example where we've done quite a bit of work on trying to think about, for instance, how can we think about modes of variability and understanding of basics of turbulence, and having that not just as a parameterization, but also for understanding of basic turbulence in the atmosphere. Radiation is, of course, the obvious target, right? So thinking about radiation in terms of cloud cover and how that's actually regulating radiation. In fact, it was the first application of machine learning to the Earth side. And for today, we're going to be focusing mostly on clouds, and because clouds are actually very important. And I'd like to emphasize that a lot of the things we are going to be discussing might not even be resolved in some of the high resolution simulations. And so that's one thing to keep in mind, is that high resolution cloud resolving simulations are not a silver bullet. There are still a lot of issues that are coming in those simulations, and we'll try to allude to that in a minute. So just to get started, so this is some work we've been doing for now a couple of years, thinking about using global cloud resolving simulations, so kilometer scale type simulation that are being run over a couple of days. And then the idea is to actually coarse grain again that field. And once we have this coarse grain field, we actually know exactly what we need to predict. And in that case, it's basically the mesoscale effect due to convection. And what we've done in the past is thinking of that, we just want to predict the tendencies, so the heating and moistening tendencies, along with the fluxes, because we need to have energy and mass balance as well. And as input, we have the coarse scale state, so at 100 kilometer scale of temperature, moisture, wind, and also the surface fluxes in an atmospheric column. And we train all of those columns together. We don't really say where we are across the globe. And then basically, if you want the details, this is the best neural network we had. And we got pretty excited at the time because we managed to actually swap the original parameterization with that neural network. So instead of resolving convection and having a parameterized convection scheme, we try to actually mimic that, or mimic the high resolution field directly within the coarse resolution host model, which is the community atmospheric model CAT. And what you can see is on the left-hand side, this is kind of the high resolution version of the model, which is resolving those big thunderstorms and deep clouds and deep convection. And you can see that the neural network that is actually living its life in the host model is actually doing a great job in terms of trying to capture the mean temperature field. And this was, I should emphasize, over an aquaplanet, so where we prescribe sea surface temperature. But we were pretty happy with that and thought that this was really encouraging to actually see those results, especially when we compare to the regular control cam, which is here, which has this typical double ITCC type bias and tends to be very, very biased in terms of tropical circulation. So we thought that this was really encouraging, and we wanted to continue this type of effort. We can also think about, so we then moved a little bit further, trying to look at real geography, so including land and including topography. And here you could see like snapshot to snapshot comparison of the high resolution coarse grain field on the left-hand side, on the top, sorry, and then the neural network emulation at the bottom. And what you can see is that we can do a very good job, whether for the convective moistening in the column or for the precipitation rate at the bottom. So really there's some skillful emulation with continents, and we thought that was really, encouraging as a result. We then looked at some things that go beyond just like snapshot or spatial features, but thinking about a little bit more about extremes, right? Because that was a lot of my motivation thinking about precipitation. And here we could see that when we actually plug the neural network into the host model, we could do a much, much better job in terms of representing those extremes. And that's here an example where you can see that we can really capture the tails of the distribution much, much better when we plug a neural network compared to the regular convective parameterization in CAM. And those are some relatively recent results from Gunnar Barents, which was graduated. And thinking also about the diurnal cycle, where we know that we have substantial issues with typical convective parameterizations. The diurnal cycle tend to be off typically a little bit after noon, basically in phase with solar radiation. And that doesn't fit what we see, for instance, when we have mesoscale convective systems, such as over the United States. And here you could see that the neural network was really able to capture a lot of the details, and this double diurnal cycle, this is here over the US to those mesoscale organized systems. So this was really a great result. We thought, it's not perfect, but it's much, much closer to the truth than what we have in the standard community atmospheric model. So this is great. We could also look at some diagnostics that go beyond, just pixel-wise statistics or geographical statistics, but things that are definitely of interest, especially in terms of modes of variability. And what we could find is that, for instance, this neural network, once coupled with the host model, was successful actually at characterizing this Madden-Julian oscillation, right? So it really tells you that there's something fundamental that this neural network has captured in terms of scale interaction, right? How the small scale is actually feeding back into the large scale. And we thought that was really encouraging because it's much, much better in terms of the fidelity when we compare to the Kelvin waves, compared to the control CAM experiments, so the regular parameterization. So very encouraging results where we thought that, it's capturing also the scale interaction, right? So it's more than just replicating columns and columns, right? So this is great. But on the way, what we learned is that there are a lot of issues, right? Some of them, a lot of people are actually actively working on, for instance, stability issues that the model can blow up, or some generalization issues. But I would say to me, the main thing that's been really bothering me is generalization, right? The main goal we have is trying to have a parameterization that would be a fully hybrid model where we plug some machine learning into a physically based model. And what we want, of course, is to, or at least in my case, is to predict climate change or project climate change, right? But climate change, by definition, is a shift in distribution, right? The temperature is changing, the amount of moisture in the atmosphere will likely be increasing. And so the issue is that we don't really have the capacity when we look at some neural network, which is great at interpolating between tasks, even when you think about ChatGPT, but it can really not generalize, right? That's really an issue with machine learning type algorithm. And so what we thought is that maybe we can use this technique, which is called multi-fidelity type approach, right? And in that case, what we do is we combine the kind of the best of both worlds. We have a standard parameterization. So you could think of that, your regular convective parameterization. It's a model. It's not a great model, but it's an okay model, right? But then we are going to be correcting that with some sort of high fidelity correction. You could think of that it's a fancy bias correction because it also takes the input, the state as input to this second neural network. So it's state dependent, and that correction is actually correcting the structure of the first neural network. And the advantage is that we can learn that in the past, right? But the standard low fidelity parameterization most likely has some capacity to extrapolate into the future, right? And so when we use this technique, we look at the top, this single fidelity, high resolution historical emulation. What we can see is that this single fidelity is actually not doing such a great job in a very strong warming experiment, a plus 4K experiment, right? So that's the result we have at the top in terms of R square on the amount of moistening in the atmosphere. And when we look at the low fidelity, so the original CAM parameterization, it's actually doing a better job, you know? So it's actually going against what I told you earlier, is that when you think of a generalization and thinking about climate change, those models don't do a great job, those machine learning models, right? Because they really struggle. And you can see the places where they struggle are definitely regions of extrapolation. So basically the warmest regions of the world. And when we combine those two together, so this kind of multi-fidelity approach, so combining this low fidelity with high fidelity correction, you can see that we do a great job in terms of correcting that and actually getting a very, very accurate result even into the future, right? So this is very encouraging, and we believe that this is a way to go. We have some really advanced results now at Meteo France, and those are great collaborations. There might be some other strategies. So we have a few papers now thinking about, for instance, embedding physical invariants such as dimensionalization within the structure of the neural network. We can also merge causality and machine learning. So there are different techniques. Happy to take that offline if you're interested. But I would say, as part of trying to get back into my journey to the use of machine learning, climate science, for me, it's been kind of a roller coaster, I would say. The initial work was really, we thought, very successful. We could have correct emulation of convection. But then we realized that we had the struggles actually generalizing. Also, we had issues with stability numerically. We could get into that if you're interested. But also, more importantly, we were missing physical invariances. A lot of that has been corrected, I would say, right? But I would say the main point is that over the last couple of years, I got personally very, very interested in actually embedding physical invariances or physical laws or non-dimensionalization or equivariance within your networks and causality as well. So we go beyond correlation and we can better extrapolate in regimes we haven't seen. But I would say more importantly, my main interest, and that's why I actually got into this machine learning business early on for convection, is I really just wanted to understand convection, right? So, so that's really where machine learning can be used for what I would consider new discoveries, right? Can we use those tools as a way to understand things better? So that's going to be just the rest of my talk to try and explain how we can use those tools for new discovery. So you have different ways of doing that. So what you can do is you can use machine learning with interpretability. We call that explainable AI, XAI, which is shown here. This is a sharp value here, where you can actually start investigating what you have into the guts of your network or whatever model you have. You can use, and I'm a big fan of what we call latent spaces, so a latent low manifold representation of your data, and that's a great way to start getting some understanding or intuition about your data. And yeah, I could happy to talk about that online. And then another way is to actually use equation discovery, right? An interpretable equation that you can directly read, and that's something we just can make sense of, especially if you're trained as a physicist or mathematician, right? And that would actually improve trust, interpretability, and generalization in the meantime. So what we are going to do for the next few minutes is we are going to be looking at just one case, which is convective aggregation, right? And we know that whether in simulations or in observations, convection can aggregate. At times, it can be more like popcorn convection, but it can also aggregate, such as what you see at the bottom. And in fact, it's very important, right? Because it has a very strong impact in terms of the relative humidity profile in the atmosphere, and therefore on relative cooling back to space. So it potentially has a pretty strong impact on climate sensitivity. It could also have a lot of implication for precipitation because you can have a clustering at the bottom. So you can have a pretty strong increase in accumulated precipitation, right? So a lot of things are actually very connected to aggregation. And also when we think about it, we are not really resolving aggregation in a climate model at hundreds of kilometers scale, roughly, right? So it's basically something that should have a strong impact, whether on climate sensitivity or precipitation, but we are not directly solving that. So how is that possible then that the machine learning work I showed you earlier is actually doing such a great job? So we are going to get into that. So the science questions we are going to be addressing now are twofold, right? The first one is we want to say precipitation is a function of the core scale, right? That's what we've done for regular parameterization. But now we want to add one more component, which is, does it matter to have some information about the subgrid scale, right? What we will call subgrid scale stuff or the micro scale, however you want to name it, but some level of aggregation or organization. We want to have the sense of that. And in parallel, and you will see that those two are connected, we'd like potentially to explain some of the stochasticity of rainfall. If you remember in some of the videos I showed you between the neural network and the original high resolution simulation, in fact, there was a lot of difference between the two simulations in terms of the actual stochasticity. The original high resolution simulation was much, much more stochastic than the neural network emulation, right? And a lot of people have worked on that, on stochastic parameterization, such as my colleague Judith Berner, and it's supposed to be very important, right? Because it can actually increase the spread of Earth system models and weather forecast model in particular. So that's still, but it's still typically unclear how do we actually set that up, how do we crank the noise, and there are still a lot of open questions and getting the right color and spatial temporal structure. So what we are going to do again is we are going to take those high resolution simulations, the same as before, cause rain data, this is the diamond experiment, and we are going to be focusing just on precipitation data and trying to predict precipitation based on the core scale. So that's basically what we have. We have the high resolution field of precipitable water, sea surface temperature, 2 meter temperature, specific media 2 meter. We cause rain data, so we just get a scalar for each of those fields. And we plug that into a neural network exactly as we've done before, and we try to predict precipitation. So that's going to be our baseline benchmark type experiment. The second one that we are going to have is we are going to do a slight twist to that, and we are going to add one more input to the neural network, and we are going to call that the organization dimension. And it's going to be coming from the high resolution precipitable water, not precipitation, of course, because that's what we want to predict, but just the high resolution precipitable water field. And we're going to contract that dimension through what we call an encoding and decoding into just 2 dimensions, right, that are going to represent the organization. And what we are going to do is trying to reconstruct the precipitable water field just with this bottleneck of 2 dimensions, and at the same time trying to predict precipitation. So we do that in tandem, we do it together. And there are some tricks about equivariance. We want to be translation equivariant and also rotation equivariant. So we work on Lie groups, but those are details. And then what we are doing is we go from dimension 2 to the 10 to power 2, so just 2 dimensions, and that's what we want to use and add as a dimension to predict precipitation. So in the benchmark result, if you remember, I focused mostly on the top corner here, but if you start zooming in and looking at the very, very extreme rainfall events, what you will find is that the baseline neural network is really struggling in terms of predicting those extremes, right? It's actually much, much lower than what you would expect. And in fact, if we look at the autocorrelation, how much we can actually predict in the field, we would see that there's no correlation. So it has no predictive power in terms of R square, right? So that's really telling us. Now, if we add this organization, what we see is that we can really capture those extremes. So again, makes sense based on the picture we had earlier that aggregation organization is really critical for the extremes of rainfall, right? The more aggregated it is, and the more clustered, the more precipitation we have. But it's also very important because the field was very stochastic, but what we are showing is that the R square, so the temporal or spatial variation is actually very predictable. So it means that precipitation is likely not that stochastic in the end, if you can characterize and carry forward in time your aggregation, right? So that's just, you could think of that. You need to add 2 more dimensions that are characterizing this aggregation. And if you can have that in your climate model, then you can do a great job in terms of actually predicting in space and time your precipitation, right? So it's not really stochastic, but it's just, you could think of that, it's a truncation of a high dimensional system. When you truncate, it looks stochastic or chaotic, but it's not, right? It's just the fact that you truncated a dimension. So what did we learn in that case is we learned that organization regulates the extremes of precipitation and also affects their prediction, right? And that precipitation might not be as stochastic as we think if we can actually include some convective aggregation, right? So that's something maybe to do, like when we actually develop a convective scheme. Just in passing, if you're interested, I'll refer you to the paper. We don't have a whole lot of time. But I just wanted to mention that another way to actually interpret data is to get to this equation discovery. And this is an example here where we applied that to the ICON model. And what we train our model on the diamond experiment, which is at the bottom left here. And we compare that to the Shore and Randall type cloud cover scheme, which is here on the top left for the coarse resolution icon. Era 5, if you think of them as quasi observations, are here in terms of cloud cover, so much, much lower than the diamond high resolution simulation, which is again telling us something that there's, even those high resolution simulations are not perfect, right? They have pretty strong biases. And if you think about climate sensitivity here, you will see that there's a huge discrepancy in the high resolution icon. Now, if we look at this equation discovery, which is based on evolutionary or genetic algorithm, what we're doing is we first try to replicate the diamond experiment. And that will give us the equation that we have here at the top, where we have a few coefficients C1, C2, C3, and C4 that depend on the relative humidity gradient as well. But what we can do then is we can use transfer learning to crank those 4 only coefficients, so not the whole lot, just 4. And we crank that back to the AR5 data, and then we can get a very, very accurate cloud cover model, right? So really taking the benefit of both the high resolution simulations and the observations. And to my knowledge, this is one of the first.
What is the issue actually? I think we have some technical issue. We'll stop this presentation for the time being. And it's almost over here. 2 minutes more. So because he's not online for answering questions, any questions, you can contact Parent Gentin on his email address. Thank you. So we have next 3 oral presentations of 15 minutes each. So we'll overshoot the lunch by half an hour at least if you go by that. So I invite first Ayushi Tandon from University of Petroleum and Energy Studies, Dehradun, to speak on machine learning based approach to predict extreme rainfall events in India, Uttarakhand region. Try to complete it as early as possible by 12 minutes, then we have some time for questions.
Esteemed friends and distinguished colleagues, today I, Ayushi Tandon from University of Petroleum and Energy Studies, is going to present my work on the topic machine learning based approach to predict extreme precipitation events in India's Uttarakhand region. As we all know, we live in a world that is facing an issue of rise in extreme events and indirectly related to fatalities and heart-wrenching death tolls. So together with a sustained approach, we can use the power of machine learning to create a future that has a diminished impact of these events instead of simply accepting them as a new normal. So my outline for the presentation is I'll give a quick background of the state from where I belong and the region of study. There's some questions that I'll be addressing in this presentation: machine learning as a solution, data methodology, and so on. So rainfall plays a major role in most parts of India and is directly related to agriculture, water resource management, and climatic patterns. Uttarakhand being a region of northern India and has been accumulated by most of the Himalayan part, is most prone to climate change and thus alteration in the precipitation patterns. Here, machine learning is a boon to this field where we don't have as much high computation powers to predict the extreme rainfall events. So the questions that will be addressed in these studies is machine learning adept at identifying, classifying, and predicting extreme events? If yes, how reliable these models are, what factors are taken into consideration, and can this method be applied to any other extreme event? So here comes the machine learning as a solution. As we are focusing on this point from past few days, I won't be taking much time. Artificial intelligence is a system of creating intelligent machines that mimics the human intelligence and has been subcategorized into machine learning, neural networks, and deep learning, so on. By the time the machine learning has been integrated into climate for various researches that are available for climate predictions, assessing climate change impacts, deforestation tracking, biodiversity, and so on. So the data from a study that I have considered is IMDA reanalysis data. For this, I would take a pause and thank NCMRWF, UK Met Office, and Indian Monsoon Mission for creating this dataset, which is at a high resolution of 12 kilometers, specifically for Indian subcontinent, and is a boon to the Indian researchers if we want to track extreme events or any other climate-related events over the region. For my study, I have just taken into consideration the climatic parameters, as this is a base study which I am taking forward for my work. And for machine learning, I have used supervised machine learning algorithms, but I will only focus on random forest model and support vector machine. The IMDA data with machine learning have been used in the literature, not too much wide, for groundwater level variation forecasting, peak flow estimation, simulation of tropical cyclones, and much more. So before switching to machine learning part, I would discuss rainfall distribution over the region. We can see that the average rainfall from 2029 to 2023 ranges till a maximum limit of 10,000 mm. And the anomaly plot shows the southeastern part of the region is mostly affected. These are the seasonal variability, specifically for the JJAS months. For this, we have done seasonal average for the study period from 2029 to 23. And then we separated it for particularly 2023, where the WMO suggested more than 79 extreme related events causing casualties of more than 5,000 and a huge number of deaths. It's specifically for Asia region. I'm highlighting only for Uttarakhand. So also for the JJS part, we can see that mostly the southeastern part of the state is mostly affected. And as soon as the elevation is lower, the rainfall patterns is mostly shows an increased rate. So for this, we did a grid-based analysis, and we extracted the data for each grid over Uttarakhand from 2019 to 2024. And we found that the grid point 29.16 80.16 shows the maximum rain for the data set. And then we applied machine learning algorithm for this point, instead of quoting it as an outlier. So what we did, we have taken climatic variables and found the correlation of precipitation with all these variables. And we found dew point temperature, relative humidity to be the most strongly correlated functions, and surface pressures to be negatively correlated. We have used the machine learning algorithms at different train and test split scores, and found a competitive performance between the random forest and support vector machine. For further analysis, we have plotted the rock curves for this and found that the random forest model overpowering the support vector machine model, and also cross-checked it with the Brier scores, which was at a point of 0.32. Now for the prediction of these events, we took both these model forwards, and we have created a lagged feature. In this, we have taken the past value of precipitation as an input and allowing them to learn from the temporal characteristics of the data. In this, we found that the random forest model overpowers support vector machine in calculating normal and moderate events, but the issue occurred with the extreme events, which is the main focus of our study. So I would like to summarize my work. We have found a particular grid point on which we found that the maximum rainfall exceeds 10,000 mm annually. For the seasonal rainfall, we also saw that the most of the southeastern part of the state was mostly affected. The grid-based analysis gave us the point where we found the maximum values and also classified the machine learning programs and also used it for prediction. However, the work is not yet like I'm working on this point that why machine learning model is not working for extreme events. Rather, it is giving a good performance for moderate and low events. The factor might be that I haven't considered dynamics, which will be my future work. And upon a relevant gain of the accuracy from the model, we can go it for the automation process. That's all for my work. Thanks.
Thank you for finishing well in time. Are there any questions? Anyway, it's good to note that you used IMDA data. Thank you.
Thank you for your presentation. There are two questions from my side. First question is, which tool you use to run your model? And my second question is, in your training models or in your training data set, if the extreme values are unavailable, then definitely your result will be less. Then how you will address this point?
Okay, so first of all, yeah, when we are talking about the tools, we have various tools like MATLAB, RStudio that are that have pre-built functions. But I'm using Python for my code and using a open access available IDEs, that is a VSC code. And when we like ask about the extreme part, so as the IMDA data is available for 20 hours, it's an early data. We can resample it for the maximum thing, because when we are talking about extreme event, we need to be ready with the highest intensity. So for that, if the potential outlier is not available, you can sum that event to get a more highest threshold for that event.
Okay, if there are no more questions, let us thank Ayushi again. So our next speaker is Dr. Yashwa Babu Vishwanathapalli from NARL ISRO, who will speak on impact of Western Ghats orography on the simulation of extreme precipitation over Kerala during 14 to 17, 2008.
Yeah, it's good. It's not working, but it's okay. Okay. And thank you, sir. Okay. Hello. Yeah. So, good afternoon, all. And I myself, Yashwa Babu from NARL Gadanki, and I thank organizers for giving me this opportunity. My talk is on impact of Western Ghats orography, particularly mountain height variations and extreme rainfall events. And this is mainly based on physics-based model, and it is not relevant to anything related to AI or ML results. I'm not going to present anything on AML. And my co-authors are listed here. They are from IIT Delhi and Indira Gandhi Center for Atomic Research. And so I'll directly go to the results, motivation of this study mainly. So all we know, the mountains play a major role on monsoon circulation. However, there are major features of mountains like steepness of the mountain and height of the mountain, length and breadth. They play a distinct role on monsoon circulation as well as the rainfall, occurrence of the rainfall. There are studies based on mainly observation based or few numerical model, but they are not mainly focused on how the sensitivity will impact the monsoon circulation and rainfall. So we want to take a case study. We want to show one of the, say, we are conducting a series of experiments like how steepness is varying and how mountain height varying. Here we have shown results, how mountain height varying the mountain height, how it will impact the rainfall simulations. So we want to take a best case to show our this impact. So we thought this Kerala heavy rainfall occurred between this 14 to 15 August to 2018 is the best case study, as it is we can say it is widespread and for entire Kerala, and starting from northern part of Kerala, it occurred like 48 centimeters, and central and southern parts of Kerala, it occurred close to the 20 centimeters of rainfall in a day. So, and so coming to the model setup, what we use for this exercise. So it is a 931 kilometer domain over the 1 kilometer mainly focuses over Kerala, and the remaining the second domain it covers the southern the Indian Peninsula, so from starting from Madhya Pradesh to it covers the central part of the Indian Ocean. So we want to say we want to use baseline close to the reality, which represents the observations. So we have taken from the physics and initial conditions we have used as best as possible closer to the reality, so that it will represent the natural experiment control with the actual terrain. It represents the actual results. So we adapted based on the previous studies from from Thomas and the other studies. So we conducted primarily 4 experiments to test this exercise. The control with natural orography without any changing anything, and the second we removed mountains completely. And third, we limited mountains up to 600 meters. As 600 meters, it is close to the plateau height. So we want to test how this orography will impact this monsoon rainfall and circulation. So the fourth experiment, we limited the mountain height up to 1200 meters. And the other options for both for physics and the initial conditions we use same. And we started initially, we started model simulation at 13 August to the 2018, and we ended up to 17 August 2018. So we extracted hourly outputs and from the inner domain of the inner domain and presented the results. And first we started with the how of say this event particularly occurred. The previous studies says that it is mainly due to the occurrence of the intensified offshore trough closer to the close to the Kerala and the metropospheric cyclonic circulation. So we want to see how offshore trough is represented in these simulations. So here the background we represented terrain, how it is there in each simulation, along with the sea level pressure contours. So we can see clearly. So though the differences are not clearly visible, there is a the pressure contours almost like 1 degree to 1.5 degree differences in sea level pressure we can see from the experiments. So further we try to analyze the dynamical fields like winds and moisture, how it is affecting. Here we have tried to show the how the simulated wind field varies with if we change the mountain height. So here the top panel shows the winds at 850 hectopascal, and lower panel it shows the winds at upper troposphere close to the 100 hectopascal. So the monsoon low level jet. So though it is say from no mountain to the experiment with control, so there is a gradual decrease in the wind speed in the northern parts of the northern parts of the mountains, and there is an increased wind speeds closer to the central region. And coming to the upper troposphere, the opposite trend we notice. So controls with no mountain has weaker easterly jet indications, whereas the natural topography it has intensified features of easterly jet over Kerala region. So further, we have also seen how it is changing over the maximum heavy rainfall occurred over Kerala. It is close to the Pukot region. So it occurred almost like 48 centimeters in a day. So we have taken gridded this 1 degree by 1 degree average winds, and we presented here. And we can see clearly the low level winds there is a gradual decrease in the low level winds throughout the simulation. And we can see from no mountain to control, there is almost like more than 10 meters per second decrease is there. At the same time, easterly jet, there is an intensification of the easterly jet is noticed in the control simulation. Further, say apart from the horizontal winds, we also analyze the vertical winds, how it is modulating across the experiments, and we try to and we notice the no mountain and the plateau type of terrain doesn't produce much vertical velocities as compared to the moderate mountain and to the experiment with the control natural mountain. So we have seen intense vertical velocities closer to the mountain, close to the mountain boundary in the control experiment. So further, we have also analyzed the frost number, how it is varying at two locations where the maximum rainfall occurred. So frost number, it is famous in fluid dynamics and even in atmospheric science. When we talk about mountain sensitivity, it is well known, and it is actually the mean wind over, and it is a ratio of mean wind and bound by cell frequency in a height. Whenever as height is in the denominator, so if mountain height is 0 or 1, so the flow, it doesn't expect any blocking. So here so mountain height, the frost number exceeding 1, it means so the flow doesn't have experiences any blocking effect or mountain barrier effect. And if it is less than 1, flow experiences the blocking. So here we have taken two regions. One is close to the northern part of the Kerala, the other one in central part of the Kerala, and we plotted the frost number. And to carry out this, we have adapted the methodology given in the Pedretri et al. 2018. So we can clearly see the no mountain and mountain with 600 meters, close to the experiment with plateau terrain, doesn't experience much. We have taken mean flow at 1 kilometer height. So the mountain with 600 meters doesn't experience any flow mountain barrier effect. Only experiments with moderate and natural mountain experiment only has the mountain. We can see clearly the mountain blacking effect in these two simulations itself. So further, we have also analyzed the vorticity budget analysis and moisture transport analysis. But due to time limitation, I'm only presenting the moisture budget analysis of two parameters. One is the moisture transport, and the other one, the moisture convergence, where we can see the moisture transport and moisture convergence. The moisture transport, it is shown in the top panels, and the moisture convergence, it is shown in the bottom panels. And we can see clearly the transport, there is a clear decrease in the transport, and it is shifted slightly towards the central parts in the natural mountain experiments are controlled. And apart from this, even in moisture convergence also, the close to the mountain, so we can see clearly intensified convergence in the control experiment. Further, we have also analyzed the hydrometers, how it is affecting with the mountain, if we change the mountain terrain. So here we can clearly see the without any mountain, so reflected almost like there is no, so almost it is close to, it is not significant. And as we increase the mountain height, we can see clearly the development of convective, the clouds, along with the contours here we have shown is vertical velocities. So these two amplification we can clearly notice in mountain height 600 and 1200 meters experiments along with the control land. Further, we have also analyzed the hydrometeors, so which helps particularly the longevity of the system, like mixed phase hydrometeors, Q snow, Q global, or Q ice. So where we can see significant variations, if we see here, the almost like no without mountains, the hydrometeors, the Q snow, it is very less, and it is only confined to the central regions. Whereas in the control, it is as we see the rainfall pattern, it is elongated, it is spread over across the Kerala region. And apart from the ski snow, even rain concentration also, it follows the similar pattern. So apart from this, we have also analyzed the rainfall. So the experiment with natural, it almost represents the observed rainfall pattern as we see in the from GPM or from the graded station observations. But if you see the without any mountains, we see very less rainfall, and mainly it is confined to the central regions, and it is slowly shifted to northern parts as well as the southern parts when we increase the mountain height. And there is a clear difference from the no mountain to the mountain with natural topography. So we can say, coming to my summary, so even with any topography, there is a rainfall, but the amplification mainly when there are mountains. So with the experiment with natural topography, it represents more or less same, but the mountain height, even with 1200, we can get a better rainfall pattern. So both mountains and synoptic conditions, it will give you a better representation of the rainfall for Kerala region. Okay, thank you, sir.
Thank you. Mr. Babu, are there any questions? Yeah.
Okay. Thank you for the talk and the very interesting approach. I would like to know, have you looked at the other side of the peninsula? What was the influence of this change in the
So
system?
you say that results are already published. Say it is there due to time limitation. I didn't present all. So you can see in this divide.
Okay. One more question. Why did you choose this heavy flood event for this particular study?
So say my aim is mainly to see how the rainfall is varying. So,
but why specifically the heavy rainfall?
Spread across the Kerala. If you see the rainfall pattern, so I want to take a case study which is spread across the from starting from the north to the south region.
Okay, you want a case study, so you choose that.
Yes.
Thank you.
Thank you. Any other questions? I had one question to ask. The C plot, that is basically where you have 1200 meters of orography.
Yes, sir.
And the control has what?
It is up to the natural amount. With orography, it is close to the even 2,400 meters also it is there, sir.
So this 1200 is just like a rectangle, or how you done it?
No, we exceeding 1200, we made it as flat.
Okay. Okay. Thank you very much.
Okay. Thanks.
Let us thank Dr. Yasha Babu. Our next speaker is Dr. Ayantika from IITM. She will speak on understanding the extreme precipitation, monsoon rainstorms over Pakistan. And we have 15 minutes time.
Okay, so hello. So hello. So in this talk, we'll be taking a look at the heavy precipitating monsoon rainstorms over Pakistan. So this Meteosat image, which you can see here, we can see a very nice organized convective rainstorm, which is occurring over Pakistan. And this is not for the years that we hear of, that is 2010 or 22. This is from 2020, 25th July. So, and this resulted in very large rain accumulations over this region. So to give you a context of the study, the Pakistan region is a very dry region, which is in the northern side, we have the mountains, we have the deserts, and it is at the south, it is locked by the Arabian Sea. So what happens is this dry air descends from the mountains and it meets the moist air from the Arabian Sea. It gives rise to very buoyant cells, which gives very deep clouds and intense lightning. But these storms are very localized. They don't give high amounts of rain accumulations. So this dry region is not favorable for the development of broad stratiform rain accumulations, stratiform precipitating systems.
Now, in the morning, we had a bit of discussion about the stratiform and convective organization. So I'll just give you the overview of how this is characterized. It is characterized based on the radar reflectivity, wherein we have this very deep convective echoes and embedded within the organized system. This is basically the convective region is the young active portion of convection. We have very high vertical velocities. The growth of the particles occur by collision coalescence and rhyming accretion. And the most important feature is that due to these processes, the vertical variation of heating shows a single mid-tropospheric heating peak. Whereas the stratiform region, it has this broad radar echo and is characterized by a bright band due to the melting layer. This is a region where there is more gentler motions, the anvil spreads out, and it is basically the older, more mature convection. And due to these processes, the vertical variation of heating, it has a very high elevated heating peak at around 8 kilometers and a cooling peak from the evaporative processes down below. Now, why is this important? Because these two different types of heating peaks, it gives the response of the atmospheric circulation is very different. For this mid-tropospheric heating peak, we usually have the intensification in the lower levels, whereas this elevated heating peak, it has been shown that it intensifies the mid-level circulation, it intensifies the cyclonic vortices over the tropical regions. So usually this Pakistan region, since it's dry, we don't have stratiform type of precipitating system over this region. But when the 2010 floods occurred, Bob House and his group, they looked into the TRM passes. And this is a case from the 28th July. The maximum rainfall was around 30th July. They got a pass on 20th July. And we can see that there is a very broad stratiform convective system, organized convection occurring over this region during this day. So we have this broad stratiform rain echoes. So when the 22 floods occurred, we looked into the GPM data and we were trying to find whether we can see such type of systems in 22. So yes, in 11th August, the GPM captured a pass across this organized convective systems. And when we take a transect across this system, we see this is a radar reflectivity where we see a broad radar echo with this bright band. And the associated latent heating profile from the GPM, it shows a very high heating peak or around 8 kilometers with a cooling peak below. So yes, 22 also we had this broad stratiform raining type of systems over the region. So now this is a recent paper that was published by Nandita et al. In the 2022 floods. They looked into the heavy rainfall spell that occurred in August, and they showed that the moisture transport from Arabian Sea was very important. But in this table, we see they have documented the years where floods occurred over Pakistan. And obviously 22 stands out, 2010 stands out. But there are many other years when there were floods, loss of life, and people were displaced. And many of the cases were associated with monsoonal rains. So we were looking into GPM passes and were trying to see whether this type of broad stratiform raining systems are occurring in other years too. So this is some of the GPM passes that we looked into with the top one. Sorry, the top one is from 2015, and we can see the left panel here shows the surface rainfall and the associated stratiform rainfall from GPM. So yes, there are instances in other years too where we have this stratiform raining system. So when we average the heating over the stratiform area, raining area, we find the typical stratiform type of heating profile with a top heavy heating. So we wanted to understand how this different atmospheric circulation patterns can give rise to the organization of the system, helps in the development of the broad raining systems over this dry region. For this, we took the rainfall data and we identified the rainstorm events. So we took the rainfall at the center grid, which exceeded the 99th percentile. Then we added an additional criteria where we took the average rainfall across an area of around 18,000 kilometers, like a 4x4 grid. And we made sure that the rainfall over this area also exceeded 99th percentile. So basically that way we get a broad raining area. So the red curve here shows the count of rain heavy precipitating events for each year. And the blue curve shows the seasonal precipitation over this region. So we can see that the peaks in the rainstorm count, it's mostly coincides with the peaks in the seasonal precipitation. And some of the peaks stands out, like obviously 2022, we have a high peak in 2010, and we have also a high peak in 1981, which was associated with a negative IOD. These two were associated with La Niñas. We have peaks in 2006, 1994, and 93. Again, these were positive IOD events. So now to understand how the large-scale path circulation patterns influence this raining systems, what we did was we used a self-organizing map and clustered the precipitation, clustered these days into maps. We use the 500 millibar geopotential height and the wind anomaly because this is a region where we expect an interaction between the extratropics and tropics. So we considered this to be a good representative height. And we have clustered it into 4 patterns. So CP1, we see there is a trough extending from the higher latitudes towards the lower latitudes, as well as we have a flow from the Pacific across the Bay of Bengal into the subcontinent. In CP2, we have a more monsoonal feature where we have an extended trough from this Western India extending across Bay of Bengal to South China Sea. CP3, this is the most frequent occurrent pattern. We have a intense anticyclone over this Tibetan region, as well as we have a trough over North Arabian Sea and flow coming from this Arabian Sea into the southern Pakistan region. CP4 is the pattern which is least occurring. We have an again extending trough, but we have an intense circulation over the Western Pacific. This is the interannual variation of the frequency. So number of days where this patterns occurred. So we can see in cluster 1, we have peaks in 1983, 2010, and there are many peaks which shows occurrence more than 10 days. So we will be looking into this cluster and also for cluster 3, wherein we have this 22 peak. And also, again, 2010, we have a peak, and 83, we have a peak. So these two are the most frequently occurring clusters. So we are looking at the evolution of the circulation for these two clusters. Now, how do we look into that? We take day 0 as the day for this cluster when the extreme precipitation happened over the grid point, and we go backwards. So we look into the evolution of the upper level circulation, and we see at day -3, actually it was from day -4. So we see that extension of troughing from the high latitudes towards the lower latitudes. And we also see a blocking, which sits here for a few days, and it kind of locks this trough, which gets intensified in the as we move towards day 0. So this is very intense during the day 0. And when we go down to the 500 millibar, we again see the troughing, but in the 500 millibar, we also see a development of this flow across the Pacific towards Bay of Bengal into the landmass. And we have a geopotential low over this Indian region. And as we go towards day 0, this flow intensifies. Coming down to the lower troposphere, we see a nice enhanced trough over prior to the development of that event. And as we go from day -4 to day 0, this is basically a low which moves northwestward across the central India towards the Pakistan region, and it builds this flow from this Pacific Bay of Bengal into North Pakistan region. So this is also reflected in the moisture transport. The vertically integrated moisture transport shows intense moisture transport across this northern part of this Indian subcontinent towards North Pakistan, which is quite intense. The moisture transport happens across this Pacific Bay of Bengal and into northern Pakistan region. And associatedly, we have this enhanced rainfall anomaly, which happens over this northern Pakistan. So basically the CP1 pattern, it promotes rainfall over the northern Pakistan region. And so we can say this is a three-way interaction in the CP1 pattern, wherein we have a low which moves across this Indian landmass towards Pakistan, and it builds this deep inflow. So it is very deep, 500 millibar to lower troposphere. We can see this moisture coming in from this region. It encounters the mountains, and over the upper levels, we have a trough which descends. So basically there is a PV surfaces descend downwards, and it gives rise to this intense rainfall over the orographic regions of Pakistan. Now looking at the CP3 composites, so we find at the upper level, there is an intensification of the anticyclone, mostly in the north and eastern part of the anticyclone, which intensifies and sits over just northeast of Pakistan, and there is this outflow from this anticyclone. And interestingly, in the 500 pattern, we see in the lower level an intense monsoon circulation, where we have two vortices, one which propagates from the eastern region, and another mid-level vortice, which extends till around 800 millibars, which is in the northern Arabian Sea and joint Gujarat region. And as we move towards day one, we see that this system, it propagates westward again, while the mid-level anticyclone here, it is very deep. So this from 200 to 500, we have this deepening of this anticyclone, which mostly helps the movement of a low pressure system, which we see in the lower levels. So this is the 850 geopotential and circulation anomaly. So we have an intense circulation, intense troughing. We have a system which is sitting over here. Also, we have another system, a mid to low level system, which is over the head bay. And as these two systems interact and this system propagates westward, it enhances the flow, very intense flow across Arabian Sea, and converges over South Pakistan. So the moisture transport, we can see intense moisture transport happening from this Arabian Sea towards South Pakistan, and it gives rain over mostly over.
I think 2 minutes.
Yeah, done. Mostly over this South Pakistan region. So basically in this, we have an interaction between the two systems, one which is propagating westward from Bay of Bengal and another which is there in the North Arabian Sea, and it gives a deep moisture influx from the Arabian Sea region, and it organizes the system over South Pakistan region. And this anticyclone, this outflow helps in propagation, because we have seen in CP3, there were days 2022, 2020, wherein we have a very long westward path of the low pressure systems. So basically, I'd like to conclude by saying that these heavy flood-producing, heavy precipitating systems over India and Pakistan are increasing in the recent years. And but the thing is that over the Indian South Asian monsoon region, the increase in water vapor is not limited by the increase in the water vapor due to a warming climate. We have very high interannual variations of moisture over this region. So basically, the development of these extreme precipitating rainstorms, the genesis, organization, and movement, it is influenced by these large-scale circulation patterns, which are associated with tropical modes of variability. And the systems are embedded within the envelope of the monsoon. So there is interaction on different spatial and temporal scales, wherein the large scale, synoptic scale, and mesoscale interact with each other. And our understanding of this interaction is not complete. So we need to understand how these scale interactions happen. So this is very important for the accurate prediction and projections of these heavy precipitating events that are more frequently occurring over the South Asian monsoon region. Thank you.
Thank you, Ayantika. Are there any questions?
It's very well done. I'm really impressed. So in terms of long-term trend, your CP3 shows significant positive trend. So can you comment on that? Why only CP3 shows positive trend?
See, CP3, I don't know whether it's a positive trend, but in the recent years, we had this La Nina event. So I think it is influenced more by that. I don't know if we can call it a trend, because we had this 22 and 2010, and then we had this IOD. So it is mostly, if we go back to the So here, yeah, it is increasing after 2005, but we had some IOD La Nina years, which we have to see. This is very strong. This is strong. We have this 2006. So yeah, it's like, maybe we have to see, but the moisture content is not linearly increasing. Yeah.
We can talk about.
Any other questions? Any questions online? Okay. Thank you, Ayantika. Let us thank Ayantika again. So with this, we come to the conclusion of this session. We had talks by Professor Dev Niyogi, Pere Gentin, Ayushi Tandon, Yasha Babu, and Dr. Ayantika. Thank you very much.
I would like to thank the chair of the session, Dr. Ian Rajagopal, for chairing this session. I request you, sir, to please come up on stage and present the mementos to our speakers. I will now request Professor Dev Niyogi to please come up on stage to receive the memento. Miss Ayushi Tandon. Dr. Yesu Babu Viswandapalli. Dr. Ayantika De Chaudhary. I now request Dr. Partha Mukhopadhyay to please come up on stage and felicitate our chair. Sorry, chair of this session. Thank you, sir. A few announcements. All the participants are requested to collect their certificates from the reception. We can now depart for the lunch break. And I request all of you to please assemble back in the auditorium for the next session. All the speakers for the next session are requested to upload their presentations. Thank you. We head on to our next session, session 13 of STIPMEX, application of monsoon weather forecast for various sectors. I request Dr. Sushmita Joseph to please chair this session. Request you, ma'am, to please lead this session. Thank you.
Thank you. So good afternoon, everyone. We have 3 talks in this session. One is the keynote and the 2 others are invited. So I invite Professor Vimal Mishra from IIT Gandhinagar to give the keynote talk. So you have 25 minutes in total. So 20 plus 5. So after 20 minutes, I'll just give a indication. Yeah.
That's fine. Okay. So, good afternoon, everybody. And I would like to thank organizers for the invitation. And I will be talking about, early warning of hydrological extremes in India. So we have had a lot of discussion about rainfall extremes, temperature extremes. But the idea of this presentation is that how we can sort of translate the development that is happening in the meteorological community to sort of, better prepared or better developed systems that can give us information or early warning about hydrological extremes, and that include floods, droughts, and compound extremes like hot and dry extremes, etc. So I would start with why do we need early warning? We all know that, India is a country where, a significant population is dependent on agriculture, and agriculture is directly linked with monsoon variability or the temperature extremes. We are putting a lot of, lot of finances in terms of developing infrastructure, roadways, highways, and that has always risk to hydrological extremes like floods. Then also floods and heat waves, droughts directly or indirectly affect public health. And if we look at the projections for future, we will see that, there is going to be increase in rainfall and temperature in the future. Apart from that, India has a very high level of socioeconomic vulnerability and also very dense population. So if you combine all these factors, you will sort of find out that the risk of hydrological extremes is quite high. And because we have high vulnerability, high population exposure, and the changes past or the future projections suggest that both precipitation and temperature extremes are going to increase significantly in the coming decades or so. So what do we know about the extremes or their impacts or what is happening? So this slide would provide you sort of a summary that what is going on based on the past observations if you look at in terms of extremes in India. So if we talk about air temperature is increasing in the majority of the country except the northern belt that is highly irrigated or had the influence of aerosol loadings, especially the Indo-Gangetic Plain. Precipitation, of course, has a mixed trends. If you look at, there is a lot of spatial variability. Gangetic Plain or northern India has been experiencing declining trends in monsoon season's rainfall. On the other hand, western India, like Rajasthan and Gujarat, has experienced increase. So there is a more variability in terms of space and time when we talk about precipitation. And a lot of changes where precipitation is increasing,
that is because of increase in extreme precipitation event, and those are also linked with floods and flash floods. So what do we know about floods and flash floods? If you look at the past observations and trends, every monsoon season, there are a number of flood events that draw public attention, that cause enormous damage in terms of agriculture and infrastructure. So floods and flash floods are also on the rise with higher impacts in terms of, we can say, economic impacts. Droughts and flash droughts, of course, the intensity and frequency has reduced in the regions where precipitation has increased in the last 3 or 4 decades. But northern India, especially Indo-Gangetic Plain, is always at the risk of droughts. More flash droughts are occurring nowadays because of the combined impact of summer monsoon season variability, precipitation variability, and the high temperature. So combination of both will lead to flash droughts. So there is increase in intensity, but there is a lot of spatial and temporal variability involved when we talk about droughts and flash droughts. Compound extremes, hot and dry, at wet and humid, whatever you talk about, are also getting intensified, at least in some region, if not across the country. Dry and moist heat waves, I mean, you must have experienced some of these while coming over here. We can say these are certainly on the rise and with the larger extent. So now heat waves are occurring in a large part of a country. You must have noticed about recent heat wave over Delhi and in a majority of North India. And so as other parts of the country have also experienced these heat waves. So, I mean, this is the picture of monsoon rainfall in 2020, and it gives us a lot of insights. If you look at, this is, total precipitation or rainfall during the season. You see some dark red colors, those highlight where precipitation is more. Then there is, a lot of areas that experience less precipitation. So every monsoon season, we experience both extremes, drought as well as floods. And floods, of course, are relatively localized, and droughts can be, depending on the precipitation and its variability, drought can cover a large region. So what happened to changes in rainfall? And this is the, observations for the period of 1951 to 2015. Remarkably, if you can see that there has been a quite bit decrease in precipitation in this region, which is northern India or Gangetic Plain, northeastern part of the country, parts of Western Ghat. There has been an increase in Western India, Gujarat, Rajasthan, or this part. But what is more interesting or remarkable that the low intensity rainy days have gone down consistently across the country. And that has a lot of implications when we talk about groundwater recharge and other things. What happened to high intensity rainfall events? We see high intensity rainfall events has declined in the Gangetic Plain, where there is a decrease in overall or total precipitation, but a lot of these have increased, scattered over several different regions, especially in Western India, this part of Eastern India, and so on and so forth. So these events cause more floods. This cause more sort of reduction to groundwater recharge, and put these two changes together has a large implications economically, okay? And that's why it is significant. Now, let's think about what happens during monsoon droughts. So we all know that monsoon droughts, India is prone to a drought, and there is always a sort of risk or chance. Let me fix this. Yeah, there is always a chance that a certain part of country will experience a drought. Every year, almost you can think about 20% of the India or the country will witness drought. This is the historical drought extent. And this is basically the drought index called standardized precipitation evapotranspiration index. And what you can notice, this is 1965, that whenever drought happens, temperature goes up. And that is very consistent. And that putting these two together cause a lot of damage to sort of agriculture because of heat and also deficit in monsoon. Temperature has gone up, as I said already. We are witnessing hottest summers in many parts as we moving ahead in time. So this is not new, this is well known. But what happened with the recent changes in rainfall extremes and the other monsoon variability, that the flood risk has increased quite a bit in our country. So if you see India here, this each bullet or each blue color dot is basically more than 1,000 people displaced or more than 1 million people displaced. So you see a lot of big blue color circles here, and that tells us that flood risk has gone up, and almost entire part of the country is affected, especially leaving this central India, and there has been deadly floods like 2013. And we also looked at the last, millions of people displaced, area affected, mortality on floods. Of course, you will not find a very consistent monotonic trend in these things, but what it suggests that whenever floods happen, mortality, area affected, or the displacement of people could be significant. So these sort of give us a background that why we need to sort of prepare early warning, or these are some effects like hot and dry monsoon on the crop yields and so on and so forth. Given that the time, I would not go into too much of detail, but what we can know that whenever drought happens or heat happens, there is a significant reduction in food grown production. Whenever drought happens, there is a much lesser groundwater recharge. So water availability is also affected for the next season, post-monsoon season. So what I will talk about, like what our lab is working in terms of strengthening the early warning system for hydrological extremes. And we all know that early warning system is not just to give the warning, but it includes the dissemination, communication, disaster risk preparedness, which we don't do. We focus more on knowing from the event, modeling of the event, detection, and monitoring and forecasting. So if you, if we can summarize the hydrologic extremes in one sort of figure, so precipitation deficit and precipitation surplus are the two major driving factors. And then you can divide long duration, short duration. So if long duration precipitation deficit is, you can expect droughts, short duration flash droughts, because then temperature is high and there is a deficit. Long duration floods, riverine floods, river basin scale floods. Short duration precipitation surplus can cause flash floods. But what is more important is this time scale, which could go from sub-daily, daily, weekly, monthly, yearly, or multi-year. So droughts can go from anything monthly to multi-year, flash drought weekly to monthly, and flash floods are mostly sub-daily to weekly time scale. So what it tells us that we need, mid forecast at various time scales, and the good skill should be there that can capture the range of these time scales in order to develop something which is useful and usable in terms of giving the warning or reducing the impacts. I think you all know about this picture. You might have already seen, but what it tells that we have higher forecast scale at a shorter lead time. As we increase lead time, forecast skill goes down. For instance, sub-seasonal forecast will have much lesser skill than the weather forecast for 1 to 3 days lead time. Now, what is more important for hydrological prediction is basically the role of initial conditions. And I will show some examples like what does it mean. An initial condition means, let's say we are putting forecast today. So what is the condition if you take 1 week from today in the past? So that will have a very high impact when we predict droughts or even floods. And that the role of initial condition or the skill is dominated up to the week's lead time from the initial hydrological conditions or initial conditions. And then you can think about the forecast skill from meteorological forecast will have a greater role to play. So we develop hydrological ensemble prediction systems where we integrate meteorological forecasts from different models, having different ensemble members. Then we couple it with the hydrological model. We run bunch of different hydrological model to sort of have different ensemble hydrological forecast. And then putting together that can give us probabilistic forecast of hydrological extremes. So I will give you some examples like why initial condition role is very important. And we have, done very well in terms of doing the forecast of drought, especially soil moisture drought, agricultural drought. We say that hydrological drought based on runoff. But so here what we saw that this is the forecast started on 15 July 2009. And then lead time is 7-day, 15-day, 30-day, and 40-day. And this is the ensemble, bias corrected ensemble from IITM ERFS forecast. And this is the observed condition at different lead times. This is for temperature, this is for rainfall. These are standardized anomalies. So if you see precipitation forecast skill and compare with the observations is much, much lesser at the lead time when increases from 15 days to 20 or 30 days or 45 days. Here you can see the comparison between observations and forecast. And same is true probably for temperature. But when we convert this to hydrological forecast, you see skill is quite good. And why is so? Because hydrological variables such as soil moisture has a lot of memory. And that memory gives a lot of skill. So majority of skill comes from the initial hydrological conditions here. So we can very well, at 30-day lead time also, we can very well give the soil moisture drought conditions or rainfall-based, runoff-based drought conditions. And that similar skill doesn't exist when we talk about only meteorological forecast. Let me know how much time do I have. Okay, so we did this experiment for two other very, very prominent droughts that happened recently in India. So one is 2015 drought in North India, Indo-Gangetic Plain. And the other one was the South India drought of 2016. And we sort of evaluated the onset, peak, progression, termination of the entire drought and try to understand that how well we can give the forecast. And so here what we say that, that on your sort of left, observed conditions, then raw forecast. So when we don't use any bias correction in the meteorological forecast, when we do bias correct meteorological forecast, even at longer lead times and from different models, this is extended range forecast from IITM. These are other sub-seasonal forecast models. Gives us a lot of better or good skills to predict drought ahead of time. Same for South India. And that skill, initial hydrological conditions, we can use to develop hydrological outlook. So this is 28-day lead, different variables, precipitation, temperature, runoff, soil moisture, and stream flow. So this gives us a very good skill in predicting these anomalies or the variables. But the challenge becomes when we go to floods. Floods are much more complicated, not because, we have a much lesser skill in terms of extreme precipitation forecast, but also the space-time distribution of extreme precipitation. Also, what is the initial hydrological conditions in the basin? So we are testing this in the Narmada River Basin at different gauge stations here you can see. And I'll quickly show that how we integrated different hydrological models. So these are 5 different hydrological models. Then we also used machine learning. And we sort of question that whether machine learning can give us better skills than hydrological models alone. Okay, and what we find here, these are the sort of skills for calibration and validation at different locations in the basin. So you see that models, this is the multi-model ensemble mean from different hydrological models perform very well at most of the locations. But why floods are more complicated? Because human influence, such as the role of reservoirs, comes into picture for which we don't have data of long term. And you see the skills when we include these effect of reservoirs into models is much, much higher than when we don't include the reservoirs influence. Okay, what is the good news? That when we use machine learning and combination of hydrological models, we can get the correction in terms of flood peaks, timing of flood peaks, as well as the magnitude of flood peaks. So you can think of this as a hybrid model where multiple hydrological models combined with machine learning models. And when we have ensemble hydrological model-based forecast, that improves for timing error as well as the peak magnitude error, which is quite important when we do the flood early warning system. This is the same thing showing different ensemble members. So now when we do flood forecast, we also need flood inundation forecast. So the question is whether machine learning based models are combined with hydrological models can improve flood inundation or not. So what we see here that flood inundation is skilled. So this is the lead time 1 day, 2 day, 3 day. This is the bias. And these are the different hydrological models, ensemble mean. And if you combine them with machine learning, there is an improvement because of the timing and the peak magnitude errors are corrected by machine learning models in post-processing of the output from the hydrological models. Now, this is the last slide of my talk. So what we need, and that I'm putting like as a hydrologist, what we require from the meteorological community if we really want to do well to solve the flood problem, or the even bigger problem is of flash floods. Because for flash floods, you don't have the lead time very high. So you have to sort of give the sub-daily forecast and at a very short probably lead time. So certainly we need high resolution, reliable precipitation temperature forecast at various lead times, starting from sub-daily, daily, short-term, extended range, or sub-seasonal. We also need a sub-spatial and temporal resolution, but high resolution helps, but accuracy is more important. So even if you have high resolution, that may not solve the problem if there is a problem of a space-time distribution is of extreme rainfall event. Okay, then also we need near real-time monitoring and availability of observations. What our experience suggests that if we have extreme flow observations of past few days, that improves forecast by a great deal. But unfortunately, these observations are not available in near real time. Now, other important aspect is that models should have proper representation of human interventions. So many times we use models considering that our basins are natural and they don't have influence. So irrigation, reservoirs, groundwater pumping, if you don't represent these properly into models, even if you have a very good models, but machine learning doesn't help until unless we have the models with proper process representation and the data that is observed for those variables or conditions. So AI/ML can help, but AI/ML cannot provide all the solutions, I would say. We still need a lot of good observations related to reservoir release and also the real-time flood conditions. So then only we can think of that there will be an improvement from the models. Need to move from deterministic to multi-model based probabilistic forecast. So what we learned from or learning from the experiment that using single hydrological model may not give you very good skills, but if we have more hydrological models combined with the several ensemble members from different forecast, math forecast, this entire combination coupled with the machine learning models could help in terms of further improving the forecast. So thank you very much. I'll stop here.
Thank you, Professor Mishra. So it was very good talk. So we have time for 2-3 questions. Yeah.
Thank you, Dr. Bhimati. Very nice talk. So several messages came out. One, you said the prediction of droughts is that's much more confidence you are having. But flood forecasting, stream flow is more challenging. But if you are having, it can be affected by your precipitation input which you are giving to the hydrology model. And also there could be problems with the processes in the hydrological model, how well they are represented.
Yeah.
And you also mentioned that representation of human interventions. for the irrigation, some changes in the reservoir, somebody has measured with something.
Yeah.
So, because generally the blame is precipitation is not good, rainfall is precipitation as a major. They understand.
Yeah.
So, but if you improve the precipitation, how much improvement can we get in the stream?
That is a good question. It depends, I would say it depends on the river basin. If your river basin is heavily dammed, which is the case for most of river basins in India, then certainly even if you have a very good extreme precipitation forecast, let's say reservoir release or the reservoir management was not proper. So then there would be a mismatch, right? And that's why it's very important that not only extreme precipitation forecast we also need data from reservoir release. What is the storage in the reservoir before extreme precipitation happened?
What about the processes that are happening in the land surface?
Yeah, so land surface.
So how good, how reliable are they?
So land surface processes, see, that's why I said, if you have near real-time observations of flow, we can very well fix most of the errors, because that is extremely important. Soil moisture data assimilation doesn't provide that kind of a skill when it comes to stream flow, because most of the satellite observations are very thin and that memory is not there. So stream flow observations, if we have for past week, let's say, that help us to correct the initial conditions in the models. And then the process, most important combination is how well your model captures the initial state. Okay, so initial soil moisture before extreme rainfall event occurred.
So the base flow and other things.
Base flow, soil moisture, and then if you, let's say, if your model has bias in initial state, it will give you a very high peak and probably before the actual flood. Right? So if that is corrected through data assimilation or machine learning, and if you have accurate precip forecast, then ideally we can say that we will have a very good skill in forecast in natural condition. If you have a lot of human influence, then we need other inputs. And that's why I am saying that only machine learning cannot correct. For instance, downstream reservoir, if you don't give machine learning model input of what is happening to reservoirs, it will not correct your forecast.
One more question.
Yeah.
So you showed one slide, this much migration is happening. Where you get that information?
So that is information. So this was a global paper by Bruno Mersch, I think, published in Nature Reviews of Earth and Environment recently or last year. Yeah. But this information is available. So there are sources like DFO Flood Observatory from Colorado State.
Yeah, human migration and other things.
And then there is also EMDAT database. They record for every major event that what is the mortality, what could be the potential migration because of these events. I know there could be a lot of uncertainty in these numbers, but these are the only numbers available in the market or in the public.
Thank you.
So any other question? Yeah.
So it's thank you for the talk. It's very nice to learn about kind of where the strengths are and where the limitation is, particularly with regards to, for example, the stream flow. So in looking at your conclusions or the summary slide, are there some hindcasting cases that you have, which will form, let's say, the metrics of how well AI/ML is able to do that? So are there, of course, one would perhaps read observations, but one could probably draw upon other reanalysis or something like that. But are there cases that you can actually draw upon which would set metrics?
Yeah. So for instance, in our recent work that we are doing, we are using handcast from Dr. Mukhopadhyay. But the problem with that handcast is it's available only for 2 years. And as you know, major floods don't occur every year, right? So we need at least 30, 40 years handcast to see that how well models do for the 20-year return period floods versus 150-year or 100-year return period floods. But what our experience is with machine learning so far, I mean, we are learning, by the way. I mean, I'm not a machine learning person, to be honest. So we are trying to learn what we can do. So what we figured out so far is that the good news is that machine learning, if you do the post-processing from our process-based models, hydrological models, it corrects for a very important aspect, which is for flood forecasting, is the timing error. So if you have a timing error, models generally, no matter how well you calibrate models, that timing error, fixing timing error is a big deal. And why is so? Because that is directly related with the initial state of models before the forecast you started. Now, why initial state has? Because model have inherent biases based on parameterization, representation of soil, land use, etc. So with machine learning, what we learned that if we do post-processing, that corrects for that timing error and also the error for magnitude. So the underestimation, which most of the time we get when we run the models for extreme events, that is somehow corrected and the timing is corrected. And that is quite encouraging, I would say, and interesting.
Thank you. If there are no other questions, let us thank Professor Mishra for a wonderful talk. So we will now move on to the next speaker, Mr. V.K. Kodaili from WRLDC, Mumbai.
Good afternoon, all. I am Vijay Kodali from Western Region Load Dispatch Center located in Mumbai. So today I am presenting about the impact of weather on power system operation. So in this, initially I will cover impact of two recent cyclones that affected the state of Gujarat and how the demand pattern and all and generation has changed. So this I will be covering. First one about cyclone Taukte. It affected the state of Gujarat, which is located in Western region. So this is how the demand pattern changed during the due to this cyclone Taukte. So initially in the normal days, that is before the cyclone, the demand of Gujarat, it is 16,295 megawatt, but during cyclone, the demand pattern got reduced a lot. Up to it decreased up to 5,560 megawatt. So we can see how the impact of Taukte is on Western region in Gujarat in Western region. Next, coming to how the generation, that is solar and wind generation, affected during this cyclone Taukte. So we can see how from 17th onwards, how the drop happened onto 18th and 19th. We can see the variation, how the wind and solar generation pattern in these days. In addition to this, there are a lot of power system, lot of transmission lines, substations are there. They are due to this cyclone, they have bad, very severe impact on these transmission lines. So we can see, if you are seeing on 17th May 2021, in 400 kV voltage level, there are 4 lines tripped, and on 18th, the number rose to up to 18. And 220 kV voltage level, we have tripping on 26 lines, and on 18th, that is on cyclone day, there is a lot of trippings happen. Similarly, there are even substations also partially are impacted during this cyclone. So these are the figures how the cyclone has impacted, and this is all the equipments got damaged, and transmission towers also they got collapsed. This is also how it impacted because of this cyclone. Next, coming to cyclone Biparjoy. It happened in 2023. So from IMD, we received this one, and you can see how that impacted the Gujarat demand and the power system. So we can see this time also a lot of demand variation is there during this cyclone period. So similarly at different voltage levels, a lot of substations got affected. Almost 284 number of substations got affected due to this Biparjoy cyclone. So next, coming to our in Western Region Load Dispatch Center, we are separately monitoring all the wind and solar generation, renewable generation. We are separately monitoring the generation and how the pattern is there, how it is there. So this is the, at present up to March, this is the installed capacity of solar and wind generation state-wise like Gujarat, Madhya Pradesh, Maharashtra, and ISTS level. So in total, we have 35 gigawatt of RE generation in Western region. So while doing forecasting for this renewable generation, we have different forecast service providers. So, and weather service providers. In particular, in this renewable generation, we are getting weather data from ECMWF, and we have forecast service providers like Enercast, LSoft, and REConnect. So from them, all these forecast providers, we are analyzing the how much the error is there in the wind and solar. This Renewable Energy Management Center, they have started from 2020. So previous 3 years, every year we have been monitoring. So in general, the error will be almost similar, but during particular days when sudden change in the weather pattern, so we will observe the lot of errors. Otherwise, it is forecasting is in more better way. This is for wind generation, and this is for solar generation. So similar pattern we can see in solar. The errors are a bit less, because the solar generation it can be predicted. Wind is very unpredictable. So now coming to, because I have mentioned how this weather is impacting our power system. So now I am coming to our organization, that is Grid India, and we are as an independent system operator. So we have 5 regional load dispatch centers. For northern region, we are having at Delhi. Western region, we have at Mumbai. Southern region, we have at Bangalore. Eastern region, Kolkata, and Northeast region, Shillong. Mainly, I want to focus that this is the power system operation. Main weather impact is we can see in real time, because we are monitoring the power system in real time through all the SCADA data. We can see what is the impact of the weather changes directly on the demand generation through the systems available with us. We are directly we are capturing the impact of this weather in normal events or extreme events. So we are doing all this work in the power system. And where we are in this hierarchy, in the top is the policy making and regulators. Third one is the system operators. There we are as a national load dispatch center, regional load dispatch center, and states they are having state load dispatch center. And regarding weather data, so all like national load dispatch centers, regional load dispatch centers, we are all utilizing the weather data. We have already existing MOU with IITM. They are providing the weather data on for our western region. Nearly they are covering almost 40 cities. They are providing the data on day-ahead basis. So in one forecasting, we are integrating the weather data into our demand forecasting. And for renewable energy also, recently we are in discussion with NCMRWF. So we have shared all our wind and solar generating plants with them, the location wise. So they are trying to map it how they can provide the weather data for the particular plant wise, so that we can integrate into our existing renewable energy management center, that forecasting system. And at national level also, we are always getting all alerts and information from IMD, and same we are taking very seriously, and we are directly, whenever any incident happened in weather or anything, so directly we are seeing the real time how impact is there. So this is how our power system works. So our the load generation balance is the only concept on how the power system works. So we are in India, the frequency is operating at 50 Hz. So whenever the load generation balance is there, it will be at 50 Hz. Whenever the generation is less, then frequency will be coming down. So this is how the load and generation is getting impacted. When during bad weather conditions and disturbances, there is a lot of change in the demand, and generation also due to variability in renewable energy like wind and solar. There is a quite significant change in the generation. So we have categorized the weather, how it is impacting power system season wise, like summer, how it is impacting in monsoon and winter. So month wise, we are trying to see how it is impacting our power system. So in summer, we are having high temperature, and due to this, there is high increase in demand. And also there are, due to low reservoir levels in summer, there will be hydro generation will be less. Similarly, in monsoon period, there is widespread rains, sudden load crash, and frequency issues are there, and sudden hydro generation outage due to high silt content. And due to rains, the coal also getting affected, like wet coal, flooded mines, low mining activities, submerged substations. So these are impacting our power systems. Next, coming to the western region, just I am giving the overview of western region. In western region, we are having the states like Maharashtra, Gujarat, Madhya Pradesh, Chhattisgarh, Goa, and DDDNH. So this is our typical demand pattern for 2 years, 22-23 and 23-24. How our demand is keep on varying, and also our solar and wind generation, how they are varying, it is shown here. State-wise also, we are first we will observe regional-wise how it is impacting, and then we come to state-wise also how the demand pattern over the years have gone change. So we can see how because of the weather and economic activity also, the demand, there is a lot of variation is there. And each event you can observe, see heavy rain, like we can see heavy rain. So everything, a festival, whenever any demand drop is there, everything we are marking. May Day, Independence Day, so heavy rain, all events we are capturing. Biparjoy cyclone, Dasara, so kite festival. So these all activities, whether or any festival, all we are capturing, and we can see sudden change in the demand pattern. So in state-wise also, it is reflecting. In each state, we can see how it is impacting. So this is already I mentioned. So there is a lot of change in the demand pattern. This is regional wise. Previously I shown for Gujarat, and this is also this is for total western region, how the demand got varied during these 2 cyclone events. And solar eclipse also we captured, that is on 21st June 2020. So we can see how that all India solar generation, how it got this reduced, and all India demand also that day, how the pattern got. So all this in real time we can observe, and this is captured here. And this is for Western region. We have observed in Western region also a lot of variation during this solar eclipse. Impact of rains, that is also a lot of 7,000 megawatt drop is observed in Western region in 2022. So whenever there are heavy rains, it is directly impacting our demand. So these are the patterns for the on rains, on generation also. So these are the weather parameters we are using in our power system. Like in demand forecast, we are using temperature, rainfall, and relative humidity. In wind power forecast, we are using wind speed, wind direction, and pressure. And solar power forecast, we are using solar irradiance, relative humidity, and temperature. And why we are using, why it is mandatory to use weather forecasts in our systems? This is mandated by in Indian Electricity Grid Code 2023. So we have to do forecasts on day-ahead basis, a week ahead, month ahead, and also year ahead. So we have to in all these time horizons, we have to forecast the demand pattern. So we have to incorporate weather parameters also into our system. So at present, we are doing at regional load dispatch center RLDC level. And when we are discussing with our states, they are also asking how you are getting the weather data, which source, how that can be captured in state-wise, because at present we are doing regional-wise. So how that can be done at state-wise, each state. So there is a requirement at as per Indian Electricity Grid Code also. So everyone is working on this. And renewable energy forecasting, it is also mandated. So all RLDCs shall forecast generation from wind, solar, ESS, and renewable energy hybrid generating stations that are regional entities and states. They shall forecast further intrastate entities. And coming to this one, these parameters we are receiving from our from at WRLDC, from all these wind and solar stations that are connected at ISTS level. So these all parameters we are receiving from renewable energy plants directly on our SCADA systems. So this is the weather, I mentioned weather data requirement. We have day ahead weather requirement is there, week ahead and month ahead forecast data is required. And intraday weather forecast data with resolution of 15 minutes. So in our power system operation at RLDC or SLDC level, we are not doing it hourly basis. We are doing it 15-minute basis. So this resolution, so in for generation, planning, demand, everything, or we are incorporating into 15 minutes. So because there is sudden change in hourly also, previously there will be hourly. Now they have shifted to 15 minutes because there is a lot of change and lot of revisions are there. In a day, we can do revisions up to 16 revisions. So every 1.5 hours, there is chance to revise our forecast, demand forecast and weather forecast. And actual data of weather after completion of day with resolution. So because now we are getting forecasted data, but actual data we are not getting. So if we get the actual, we can see and we can tune our systems. And more weather accurate weather forecast data for special events like cyclone, so that impact on power system like transmission system can be predicted. So these are the requirements of weather. Thank you.
So we can have 1 or 2 questions.
Yeah, so a nice presentation. So this year ahead forecast, is it a new addition? It was there earlier, or it is a
In 2023 Indian Electricity Grid Code they mentioned, sir. Previously it is not there. Previously we used to do for week ahead and day ahead.
okay, but in year ahead, what type of forecast? Is it just a, you need a broad projection? What
projection? Yes, sir.
Not exact, right?
Exactly, we cannot predict. Even demand also we cannot predict, because rainfall, that period also we cannot clearly, it will not be there. Sometime it will be shifting. So in prediction only we are giving, sir, just to get idea, because they have to plan the generation and all.
Okay, that's a big challenge.
Outages, yes, sir.
Year ahead forecast
Yes, sir.
is a real challenge.
For us also it is challenging, sir.
Yeah. Okay.
Because it is very big span.
Thank you.
Anyone has any other question?
Very interesting talk. Why the load is coming down during the passage of cyclone?
Because outages now, all transmission lines got tripped. So there won't.
No, that is the generation is reduced, not the demand, no?
Demand also will reduce now, where they will get power. Because see, you can see how many substations got affected, you see.
No, that is true. Because power is not there, demand is low, what you are telling?
No, power is there, no. This is only for Gujarat. All over India, we are interconnected, no. Power is there. Generation, there is no shortage. Only because of this.
I'm not getting that.
Yes.
Fine.
You can see how many, so 284 substations got affected, partially or totally.
Any other question? If not, let us thank Mr. Kodali for highlighting the importance of weather forecast in power sector. Thank you. Now we have the last talk in this session by Dr. Shishir Kedar from NCCR.
This folder yourself. No. Folder is this folder copy. Okay. I think it's audible. Okay. First of all, thank you for organizing this wonderful workshop. Actually, I supposed to come yesterday, but there was some prior commitment was there. So today I supposed to late, but finally I was thinking I may not reach. The flight actually gone to Hyderabad, then finally I came here just now. So just I want to tell the audience, August audience, that we are actually National Center for Coastal Research. It is an attached office of Ministry of Earth Sciences. We are located in Chennai. We mostly do the coastal hazard and vulnerability.
And one of the things I think on my topic is that what I want to talk today, that integrated flood warning system for coastal megapolis. So when coastal megapolis we are considering, actually we started this integrated flood warning system in Chennai since 2015. Then after that we extended services to Bombay, and after that now this year we completed for Calcutta. I think there are, this is the one of the best example, particularly for Ministry of Health Sciences is given. And I think one of the best product, I think I can say that it is a G2G for G2G achievement for that government to, from the central government to the all the state governments. And this particularly flood warning system is actually required for mitigation purposes. And also this is the product actually where we have developed. It is actually a requirement of IMDs, that is called impact-based forecast. I think all these things I just want to tell you that at present 2019 actually we started Chennai in operational basis, though it was started in 2017. Then after that 2020, with a span of 6 months during the lockdown period, we have developed for Mumbai, which is still every monsoon it is actually giving operational. Calcutta is already developed this year, and this monsoon onwards, I think we will go and give the advisories for testing purpose. Then Delhi is also in pipeline. So the major thing is that this is one of the state-of-the-art real-time operational and flood warning system. When I'm talking about real time, that means what? When we started, actually it was not real time. It was actually based on the scenario based on all the things. But later, when the demand was actually, when the user community, they want actually it is not like that what you predict, what the weather will be. It should be what is weather now. So when that type of things, when people are asking, then so we thought of nowcasting, and after that we change our strategies and everything. Actually, we started with actually one abbreviation called Chennai Flood Warning System, CFLOS. But later, when we extended into different metropolitan cities, that's why we changed into Integrated Flood Warning System. When 2015, why we did actually, though, because as I want to tell you, the National Center for Coastal Research actually was pioneer in doing all the field data collection during tsunami period. So whenever the coastal inundation is happening, that is actually our core area. So similarly, like 2015, when flood happened, with our own interest, we try to collect the lot of the inundation areas. But during that time, when we came to know that there was no data on vulnerable areas, particularly as per the storm surge and as well as the cyclone is concerned, and then extent of flooding was not known. Low-lying areas was not identified, though it was only limited to the state government on a smaller pocket area, and there was no warning system. So for that purpose, these are the lacunas we have taken, and then we thought it will be developed. But there was actually one group, they were approaching through Principal Secretary of the Government of India. So PSA office. So from there, they got a project, IIT Bombay, IIT Chennai, and as Anna University, IISc Bangalore, INCOIS, and IITM. So they were actually conceptualized one program for developing a flood warning system for Chennai. So in the last minute, when everything was going in a smoother way, but the last minute we take it into that because it need to be operationalized. So it is not like one-time product and you can develop. So every time you have to do. So for that purpose, they have given this task to NCCR, and after that we are working since last 7 to 8 years. So as I told you that this is one of the first operational system in urban flooding in the country, which would immense due to the state government for relief and mitigation purposes. So Chennai, as we all know that there was actually, maybe many people might have thinking that why flood warning system Ministry of MOES is doing. Actually, it is supposed to be mandate of the CWC of the Ministry of Water Resources. But however, when we saw that the entire business rule, that actually the Ministry of Health Sciences has a very clear-cut mandate, whether it is IITM or IIT or IMD or NCMRW, weather forecast is one of our core areas. When we saw that in particularly riverine flooding is what is happening, that is actually mandate of CWC. However, coastal flooding nobody was actually addressing. So this flows actually we have developed for the coastal regions, particularly storm surge and as well as the whatever the flooding is happening due to the precipitation. So for that purpose, we have taken many things into account. We try to understand actually what is the terrain should be. So in Chennai, if you see, there are actually three basins are there. One is river, there are two river basins and there are three river basins actually. One is south is Adyar River Basin, which is in the south. Then after that, in the central part, you will find the Kuvam River Basin. Then in the northern side is Kusastela River Basin. And entire city was actually going by the massive Bunkimam Canal. So these are the actually low-lying areas mostly. And when the 2015 flood happened, because of a sudden release of the dam, but there was a dam was actually here this is Chambrambakam Lake. So because of the release of the dam, that causes flooding. Even 2023, the same thing happened. But the situation was different what 2015 was and 2023, that I will tell you in my subsequent slides. So Chennai is not new to the actually heavy rainfall activity because it is in the east coast of India, and as well as there are a lot of cyclones comes periodically. So every 5 years actually Chennai city experiences flood. So these things, though we know that, but however the warning system was not in place. So as I told you that we are with our curiosity, we just try to collect the whatever the inundation point for the immediate after the flood. Then after that we try to actually map them. So when we put in the map, and after that when we saw that actually how the rainfall, when we overlay on the rainfall, then we found that there is actually very good correlation between the precipitation and as well as the inundations. So then after that we try to deal a little bit science behind that. Actually we try to know actually what is the carrying capacity of the Chennai and how actually the water bodies, because Chennai particularly is a city where you will find a lot of water bodies. So that type of water bodies actually gradually it was because of a rapid urbanization, it becomes shrinking. So that analysis actually we did, and after that we saw that that is the actually root cause for flooding. So wherever there is a low-lying areas, wherever there is a water bodies actually encroached because of the rapid urbanization. So that's why this causes flooding when the thunderstorm happen, or even a huge amount of rain actually will occur in the city. So we started actually the modeling, little bit modeling. Actually, we did not touch anything about the weather modeling, because we have taken as a plugin type. Simply whatever rainfall will come, that rainfall we can use it. And after that, but we have to understand actually how the hydrology is working and how is the hydrodynamics is actually working, and how actually this hydraulic system, particularly in the urban city, it consists of all the drainage network, all these things actually, how it actually was in place, that actually we studied. So hydrological model, hydraulic model, and hydrodynamic model, these three models actually we have integrated. We started with 1D, then after that 2D we have integrated into that, and after that then we have created different type of scenarios. Because we did not know that actually there was no much rain gauge, there was no much observation network was established in Chennai. Only one radar system was there, particularly which is maintained by IMD. So during that time we thought nowcasting is quite difficult. So we thought how best, this was actually proposal was given by the IIT Bombay, and they also suggested us let us go for the scenario based, because at least if you know the if there are 4 type of rainfall is happening, whether it is as per the IMD's forecast, like whether it's a green or yellow, otherwise orange or red color. So based on that, at least you can create the scenario, and based on that, at least you can give the warning. So that was actually our first approach, but later we switched over to the real-time forecasting system and everything. I think so. So it was actually, this is actually flow chart where the rainfall, sea state, hydrologic condition, terrain condition, everything was integrated into that. But the most important part is, if you see that, the terrain. Because Chennai was a place, though it is a low-lying area, it is just the terrain was not so high, and it was just along with the mean sea level. So some places even below the mean sea level. So these are the things when we try to find out a very good high resolution DEM, that is called digital elevation model. It was not available. But fortunately, actually, during tsunami time, I think many of you might be knowing that the Ministry of Earth Sciences INCOIS has done 2 kilometers from the coast. There was actually LIDAR observations was there. And also Chennai is a city. During that time, they also collected only for Chennai, whatever 600 square kilometer area, that LIDAR data was available, which was 2009. So 2009 data was actually integrated into the system. Then from that, actually, we started working on that. Though satellite DEM was not accurate, so we have not considered any satellite derived DEM. So we have depending on always the LIDAR-based digital elevation model. So after that, now this is one. The second one is that one of the crucial thing which was actually was a point of discussion is that what type of rainfall actually we want to plug in. So during when we started, actually we have taken 23 ensemble of which was given by the NCMRWF. So then that 23 ensemble we have taken because that was only during that time it was there. And we are looking for a high resolution model. It was not like that coarse resolution, it was a very high resolution model because the study area was very small. So whatever precipitation we are targeting, that should not be uniform in overall particularly city. So we want as much as pockets actually if you get the rain, I think that will be better. But during that time 23, but right now we are not using this 23 ensemble. Nowadays we are using actually ENCOM model. But that is also again, sometimes it works, sometimes it did not work. I think we are now very recently we have a discussion with IMD and as well as the NCMRWF. I think we are now coming with the new strategies that how best rainfall you can plug into your flood model. So based on that, we have gone to the that is the what about weather model. Then after that hydrodynamic modeling part, which is our domain, where we have taken that how much actually your tide, wave, and everything is coming into picture. So these things actually we have integrated into that. Then hydrology model anyway, because the catchment there are 3 catchments only. Only the biggest catchment is the northern part of Kosastella River. So that Kosastella River catchment we have integrated into that. Soil moisture data was also integrated into the system. Then in these 3 river basins, particularly in Chennai, Hadiyar, in Bombay also when we did it, we found 4 rivers. So any river basin when we found that the more important is that to understand the bathymetry of your water bodies or whatever your river system is there. So for that purpose, many places we try to collect the data by ourselves. Otherwise, we have taken, local government's assistance to get this type of data. And as well as we also were integrated into this, the total drainage pattern, how actually drainage pattern, stormwater drains are there, that also we try to integrate it into the system. So this is all about my topography. This is actually LIDAR-based topography. Then after that, we saw that in a single gridded way we combined both 1D and 2D, and we given all the forcing into the study area. Then after that, when we run the simulation, we found this is the first inundation maps. So these inundation maps if you see that in 2015, mostly because of the Chembrambakkam Lake, which was just in the Adyar Basin, which is in the down south. So there, because of the release of this water, that entire flooding was happened. So that area, actually, if you see that more inundations were also predicted. And after that, we also tried to validate this product, how is actually we have collected almost 1,000 data sets during that time. Now, of course, our database was strengthening day by day. So this is the way actually we validate. One of the just outputs, I just want to show that. Yeah. So this is actually Minambakkam, where the airport is actually located. So this area, because this down south is actually your Chembrambakkam Lake, and when the water released, that entire area, that entire water things has came to the Adyar river basin, and during that time, this is the flow actually was actually monitored. So from this, as I told you that we started working with all this scenario based. So we taken water level, different type, and discharge different type of return periods we have taken, duration also we have taken. So like that, with the permutation combination, we have chosen almost 792 scenario. Earlier, actually, when they started walking, it was actually some 5,000 scenario was there, where Dr. Partho was also involved here. I think he might be tell many things on that. But later, you know, because of the computation facility and everything, we try to minimize as much as possible. So finally, 792 scenario, we try to generate the product. But right now, this scenario based is actually we are not doing right now. So then after that, we have shown that, you know, how actually your best warning system should be look like. So we have created different type of module, like your data assimilation module, flood module. Then we have put inundation module, but inundation itself is not sufficient because the state government want how actually the vulnerability and as well as the risk, because risk is the only thing which ultimately the end product. So that so for that purpose, mostly these all are GIS modeling and everything. So that we have taken into that. Now, in nutshell, I will tell that sea flows, when we started, it was actually scenario based, but I flows right now is real time. That real time, some cases also I will show you. Similarly, in Bombay also, we have taken almost 4 major rivers, that is Daisar, Mithi, Osiara, Poisara, Ullas River, and many lakes also we have done a lot of river sampling and everything we did. So, and this is actually the rainfall. The difference between Chennai's system and Bombay system is that, you know, it is actually data. There are a lot of data sets available. I think IITM is I think I will tell that they are the biggest contributor, because IITM during that time was involved all these both the systems, and many places we found the in situ observations. Of course, besides, apart from the whatever the observations was given by the IITM, the whether it is automatic weather stations, the Municipal Corporation of Greater Mumbai, MCGM, they have also contributed a lot of data sets, particularly regarding AWS and ARGs. So that all the data sets was integrated into that. I think the right side is screen you might see that is actually data from the IITM, and these are actually my WRF model also we have tested during that time. GFS model also we tried many times. But NCMR 4 kilometer by 4 kilometer model, actually we have adapted that one, and it was continuing, I think, 3 to 4 years. 1 or 2 incidents it did not work, but whenever it did not work, we try to switch over between GFS and as well as WRF. But that decision actually switching over is a very crucial thing. I think that based on the people's involvement like IITM or IMD. So based on the forecasting, what is IMD is giving, based on that we have incorporated into the model. So I will show you that one thing, that what is actually present now. What is happening when the rainfall is actually happening? Suddenly, what is happening? We are observing, we are taking NCOM rainfall. NCOM rainfall is nothing but it is a 72 hours rainfall. Though it is a 3 days, 2.5 days rainfall, but we generally, we decided that the inundation cannot be given 3 days before. Rainfall may be given, but inundation cannot be given 3 days before, or flooding cannot be given 3 days before. So, because it will depend upon whether last 5 days or last 1 week, what is the actually soil conditions. So we are thinking that how best the rainfall can be improved. So we always take the whatever immediate 24 hours rainfall, and then after that, the last rainfall 24 hours, we will put it into the model. And as well as also, suppose during that time, whatever rainfall forecast model says that, but still we thought that IMD, because sometimes the duration of the rain is more important. Because sometimes we found that there is a heavy rainfall will be there, though prediction will be, though whole day cloudy will be there, but there will be no rain. So what we did that, you know, whatever IMD is giving, whenever IMD is changing the color coding or whatever advisory they giving, based on that we switched over our inundations also. Now these things is very, very simple. When we switching over whatever based on the IMD, it is based on the scenario, because you cannot run. But for Mumbai purpose, what we did, they have a real time, they push the data to us. So they said that up to 9 o'clock, suppose up to 8:30, whatever rainfall you are getting, that based on that, suppose today up to yesterday for 8:30 to till today 8:30, you are getting some accumulated rainfall. Now you tell that after next 3 hours or next 6 hours, how actually your rainfall will be. So we have taken the entire accumulated rainfall of the last 24 hours, and that one we put it into the model, and we run our flood model. When we run the flood model, then we got a different type of output, and that output actually Bombay was interested. So we generated that one, because this model computation is not so much time. It takes only 40 to 50 minutes based on the data, whatever you are putting into the system.
Dr. Das, 3 months.
Yeah. So this is the way actually our entire infographics works. It is taking weather model, weather forecast, tide, storm, automatic weather stations, flow. For field data verification purpose, we have taken different type of apps also. So like this, it will go to our NCCR server. Then after that, we will make our model. Then after that, we will generate different type of modules. And this type of output we are actually giving in a streetwise, because the inundation cannot be located in a particular area. So they streetwise, building wise, actually we are giving this type of flooding. Wherever there is a water logging was there, that also we have given. I think this is actually 23 last cyclone, last year flooding. Same things we continued here also. But the problem was the scenario, what I said, different. In 2023, what happened? The rainfall was not much, because in our campus itself there was a rain gauge where almost 19 to 21 centimeter rain was happened, which 2015 it was 40 centimeter rain was happened. So 19 centimeter rain but causes flooding, because the entire water bodies, as I told you, in the Chennai, wherever the training walls were there, that walls was collapsed. So because of that, the rainfall was there. That's why that causes flooding for 3 to 4 days, where NCCR, NIOT, both the campuses was also flooding during that time. And then after that, this year, last year, actually, the Calcutta Municipal Corporation, they approached us after hearing the success story of this IFLOS. Then after that, we did for Calcutta. So now Calcutta module is almost ready, and now this year, this monsoon onwards, we were going for the testing forecast. We are actually planning. I think this is all about Calcutta. Also, we are trying to go for, as per the IMD, like different type of rainfall, different type of color coding, how my inundation will be heavy to your extremely heavy rainfall. So how the inundation will be. So like that, scenario based only now we are planning, because there was no much data sets particularly is available in Calcutta compared to Bombay. So we are again, depending upon the based on your system. And Calcutta is very interesting, because Calcutta is actually not in the coast, and there was the Calcutta region is like a social region, and there was no influence of the Hooghly also. So whatever rainfall is actually happening, your water will not go. So it will be like a water logging. So in the definition of flooding, actually, over the time we learned, when we came to Chennai, they asked us what is the definition of flood. We said wherever there is a feet in water, that will be causes flooding. When we came to Bombay, they told the flooding definition is completely different. We want centimeter level. I said centimeter level flooding? Yes, because 60 centimeter, if you take into account your railway track will be flooding. So that means the lifeline will be stopped. When we came to the Calcutta, I think the scenario was completely different. They said that it was not flooding, it is water logging, because social type. And now everywhere because it was a British time they know that the topography of the Calcutta. So there was a beautiful pumping systems are there. So every time whatever water will be accumulated, you have to physically pump. So that things actually should be integrated into this model. So that actually we are right now working on that. I think that is one of the best new thing. So wherever we do the different type of cities, we are experiencing, I think, new things. I think this is all about my thing. And the last thing I just want to tell you one. one thing that we are, we over the time, actually, we are also improving, how best, because everybody was talking about the real time. We are trying to bring how the radar data sets are available. That can be translated into the rainfall, and as well as how best, when you are talking about the validation, how AI and ML techniques you can adapt that things also we have done, and the time to time we are validating these products also, and this is actually our dashboard looks like. And the yeah, so far the lesson is that when we started with the C flows, it is version 1.0. Then after that, I flows 2.0. Then now we are thinking about the future is 3.0. And 3.0, if you see the comparison, because it was library case, then real time. Whereas in the nowcasting, whatever 3 hours you are doing, we are trying to include actually radar and AI ML based things. So that is actually our target, and like that we are expanding our services. If I can give me 1 minute, because this is one interesting thing. People might be asking many questions. So before asking any questions, I just want to clarify myself. I want to tell the case study of my my office. So this is one actually where actually we are sitting. You can see the red color, that yellow color line, that is NIOT, where actually we are sitting. How your model actually works. How that rain is happening, but how actually when you are talking validation, do you think it is simple comparison? We got these things. Just to tell you that there is actually 2 buildings I am marking. One is Chennai 1 building, and there is NIOT. Chennai 1 building is a corporate building, which is a Singapore-based company, and they came and approached us that you tell us that how 100 years this area will not be flooded. So we thought that how best my topography is all about. When we try to compare these things, I will tell you that in a very fast. So this is actually 2015 in my campus. You can see the water is actually completely, all the cars were submerged, including even I also lost my car. So, but in the Chennai 1 building, you can see the water is only reached up to tire level. Then these things So then after that, what happened? We try to run different types of scenarios. You see that as long as we are increasing the rainfall, you see that entire NIOT is flooded, even after 40 centimeters. Whereas Chennai 1 building was not. That means it is already high elevated area. The construction, what is happening is high elevated area. So that type of scenario, we are giving services. Recently, CPCL, one of the biggest oil corporation, they also flooded like this. I think this type of services we are also giving. I think this is all about my presentation. The last slide is that way forward is that iFlows Delhi. We are thinking it should be extended in the many coastal urban cities. So iFlows megapolis, we are trying to expand because there are a lot of urban cities are there in the coastal areas. 40% population actually live into that. And many though life was saved, but there are a lot of properties actually we are losing. So this type of warning system, definitely it is a great success between the G2G services, and we are extending these things into interpreting the smart city modules also. Thank you.
Thank you, Dr. Das. It was a very interesting talk. So we can take one quick question.
Yeah.
Hello.
Yeah.
With due respect, while modeling, are you considering the encroachment causing encroachment which leads to the course of the river? That is one thing. And second one is the siltation of that reservoir, whatever it is, causing it also may cause a flood.
Yes, that's why every time when we came to, I'll tell you this example of Bombay. Bombay Mithi River, I think many people might have known about Matta. 2004, I did not know that there was no Mithi River in Bombay. But over the time, 2004 after, the Mumbai was actually, Mithi was a small canal. Now you can go and see the river, and there are a lot of slums are there. and lot of WCS are there. When we run this, when we try to develop that, the accurate bathymetry is actually very much important. So based on the hydrography of the state government, whatever they given, their data and our data always mismatch. Because so that shows your first question, that siltation. So we advise that one also. Encroachment, as I showed you one of my slides, that all the water bodies was mapped. And we try to tell that, these are this much percentage of the water body was encroached. That is the reason it may be causing flooding. But question is that it is a very, I will say, I cannot say that it is a political actually, because there are a lot of slums are there. In Dharavi, when we went to Dharavi slums also we saw, Dharavi slums was very nice actually, because there is a high elevated area. Though that whatever debris you are getting into the Mithi river, that may be a biggest problem. But that we cannot consider. Even one of the, I think I will tell you one nice thing. One administrator told, sir, that though your warning system works nice, but suppose a water bottle in a stormwater drain, if a water bottle of 2-liter water bottle, it will fill in the water and it will choke. How you can tell that whether your model will capture that inundations? He's not talking about the rainfall, he's talking about inundation. Because I'm talking about the only inundation. He's talking that if a small drainage network, which was choked by a 2-liter water bottle with the garbages, whether can your model will predict? I said yes. Now the question is, you may ask that how you can, yes. When you do that, Bombay, the same thing happened. Bombay, they asked us, you put the Google traffic images. So traffic layer, when you superimpose into that, then you know that where there is a traffic on the street, there is suppose causing flooding, you know that there will be a red color line zone will be there. So at that time, you might be experiencing why particular area is actually waterlogging. Okay, whereas the rest of area is completely free. So that type of level also you can take from this model. I think encroachment part we have taken, but we never given to the public that how much encroachment has been made. It is only confined to the state governments.
Thank all the speakers.
Thank you.
Thank you.
I thank Dr. Shushmita Joseph for chairing this session. I request you, ma'am, to please come up on stage and present the mementos to our speakers. I request Professor Vimal Mishra to please come up on stage and receive the memento. Dr. Shishir K. Dash. Mr. V.K. Kodali. I now request Dr. Ian Rajagopal to please come up on stage and felicitate the chair of this session, Dr. Shushmita Joseph. Thank you, sir. Thank you, ma'am. Before moving to the next session, we would like to take a few moments to felicitate Dr. Parthasarathi Mukhopadhyay as he is retiring on superannuation. I would like to briefly share his achievements and contributions throughout his scientific career. Dr. Parthasarathi Mukhopadhyay is a distinguished scientist in the field of atmospheric sciences at the Indian Institute of Tropical Meteorology in Pune. With over 30 years of experience, Dr. Mukhopadhyay has made significant contributions to numerical weather prediction, cloud and convection parameterization, and the development of dynamical cores in general circulation and mesoscale models. Currently, he is Scientist F and Project Director for the Monsoon mission at IITM, where he leads the efforts to enhance the accuracy of monsoon forecasting. His work has earned him several accolades, including the Ministry of Earth Sciences Certificate of Merit in 2015 and the IITM Golden Jubilee Award in 2020. Additionally, Dr. Mukhopadhyay is a fellow of the Indian Academy of Sciences and is a serving member of the WWRP Working Group on Tropical Meteorology Research. His contributions to short-range forecasting of the monsoon at IITM are significant. He has been a key figure in developing and refining the short-range ensemble prediction system, which aims to enhance the accuracy and reliability of short-term weather predictions in India. With numerous publications in reputed journals, he has been an inspiring guide and mentor to many of us. He is retiring on superannuation on July 31st, and it is our absolute honor to felicitate him on behalf of STIPMEX. I request Dr. Krishnan, Director IITM, to come up on the stage to present Dr. Mukhopadhyay a token of our gratitude. Sir, please. Just a little surprise.
Great honor.
Thank you, sir. Now we'll quickly move on to the next session, that is the stakeholders discussion on renewable energy and weather forecasts. I invite Professor Vimal Mishra to chair the session and Dr. Mukhopadhyay to co-chair the session. Sir, over to you.
Yeah, so we are really running short of time. So, actually, let me tell you, this stakeholder session, what just now finished, I think you must have realized it's a very interesting session. And the another one, which is following, these two sessions actually were suggested by WM. Okay, so they said that you guys will discuss a lot about science, and you all will be very proud of your own model and accuracy, etc., etc. but you please invite stakeholders who actually use your model, prediction, and get some feedback from them. How good actually. So you have just now heard Dr. Das, okay, and Mr. Kodali earlier. He said how the substations get disturbed and so on. So this actually it was not initially in our agenda. So WMO insisted that you have to conduct a training. So we started last Sunday. The suggestion by WMO we followed. And WMO means WWRP, WCRP, WGTMR, and so on. And these stakeholders. So we invited few people. So two organizations are joining online. Okay, one is can we see who are online available? One is Mr. Biren Vaishya from Assam State Disaster Management Authority, SDMA. Yeah, Mr. Biren, are you there?
Yes, sir. Good afternoon, sir. This is Viren from Assam State Disaster Management Authority.
So SDMA is one, and they will join online. And there is just now we heard Mr. Kodali who was talking about Western Regional Load Dispatch Center. There and he mentioned about one Northeast Regional Load Dispatch Center, which is called NERLDC, who are controlling the whole grid in the northeastern region, and so they will join online. And Mr. Kodali is there, WRLDC. And there is anyone from Renew Power, Mr. Dr. Sagar. Sagar is there. Oh, he's our IITM PhD alumni. Yeah, he has joined Renew Power. So I will request all of them to basically focus. Yeah, few points. Yeah, no problem. So a few points that currently what forecast guidance you are getting. Yeah, so what are the guidance you are getting right now? How useful it is, and what is your requirement? Okay, what is the future requirement you need from not just from IITM, from the whole global community sitting here. Okay, and also climate change is happening. So how you are planning, like Dr. Das showed in the last slide, possibly, what is your plan? What is your requirement from us in the backdrop of climate change and the changing of flood and all these things, and even power, etc. So I will request Professor Bimal also is there in this session. So Mr. Biren, are you there in online?
Yes, sir. Yes, sir. I am online. Can you hear?
SDMA, Assam.
Can you hear me, sir?
He has joined, right?
Sir, can you hear me?
Okay. He's Assam is having a lot of flooding. So yeah, we are not able to hear you.
So in that case, sir, let me.
Now you are audible. Can you please go ahead and put your point? Thank you.
Thank you very much, sir. Respected distinguished guests and participants from across the various states, and I am being told that it's in an international workshop. First of all, I would like to apologize for not making a presentation, because you are talking about flood, and Assam is still reeling under flood as of till today. So that is one of the reasons we are very busy, and Mukhabidya sir, in fact, he personally requested so that I told him that I'll be just speaking on a few points on the flood. So I'll be accompanied by my colleague, Dr. Kripal Majumdar. Dr. Kripal Majumdar, he is looking after the flood component out in Assam State Disaster Management Authority. So he's with me also. So I just like to brief you on about the flood. Flood, as you know, that it's a perennial problem in our state every year. Yeah, can you hear me, sir? Can you hear?
Yes, sir. Hello.
Am I audible?
Yes,
Yes,
audible,
sir.
audible, please.
Okay. So all of you must be aware about the floods in Assam. In fact, it's a perennial problem in our state. Every year, flood causes huge devastation across the state. In fact, you'll be surprised to know that since 2016 to 2024, almost more than 700 persons have lost their life due to flood in the state. And the peak flood was in the year 2017 with almost 160 persons who died because of the flood. And 2022, 181 persons lost their life due to flood. So we have got lots of systems in place. We take into consideration the preparedness, mitigation, even the response component also. So we have got the early warning systems also in place. But as a part of the preparedness measures, I would like to request Dr. Kripal Majumdar to speak on that. And after that, I'll come on the component which you are, which you told us to tell about basically on the warning systems that we have developed and the kind of warning that we receive, and that helps us in mitigating the flood problem. So I would like to request Dr. Kripal on the mitigation part.
Thank you, Biren Busha. In fact, good afternoon to all the respected colleagues who have joined for this international workshop. As far as the flooding is concerned, I think my colleague Biren has already spoke about the intensity and overview of the state of Assam and how like we have been reeling under floods and what are the various response mechanisms. As far as the response mechanism of the state of flood is concerned, we have a DM manual, which through which we govern by the DM manual of 2015. As per that manual, we do the preparedness, response, and rehabilitation activities and policies. And then also we have the state level incident response team that has been notified. Then we have flood and lightning early warning system in the state in place. We have collaboration with Northeast Space Application Center as far as the flood early warning. We call it FLEWS, FLEWS. FLEWS is concerned. We also have 24/7 state emergency operation centers and district level emergency operation centers where all the information pours in. We disseminate various kind of information to the ground level people, to the local authorities at the revenue circle level, which is the talukas in the sub-district level. Then we have a state level disaster management plan. We also have district level disaster management plan. We used to have kind of district level flood contingency plan also separately as part of the district level disaster management plans. Then we also have departmental level disaster management plan, which specifically focus on flood with 16 key departments, which include basically departments like Department of Water Resources, Department of Environment and Forest, Department of Soil Conservation. Then we have the Animal Husbandry Department. So and so forth. Actually, in some of the major 16 key departments with whom we we work very closely with them. And then we also raised around 5 companies of state disaster response forces in line with that of the national disaster response forces, so that we got timely, the people of Assam got timely response to any kind of flooding incidences in general, and then specifically to any kind of drowning and other incidences. Then we also, as far as the use of technology is concerned, we use various new technologies for effective response and rehabilitation, like that of, we have satellite phones which are available at State Disaster Management Authority, as well as all the district level disaster management authorities, and also the local magistrates which are there at the taluka level. So we have recently distributed all these more than 150 plus satellite phones to those talukas or revenue circles at the sub-district level. And then furthermore, we also have a very close association with Northeast Space Application Center in terms of using unmanned aerial vehicles for aerial surveys of the damages. In fact, in the year 2022, which during that year actually we face major damages and losses in our hill districts. We have 3 hill districts: Dima Hasao, Karbi Anglong, and West Karbi Anglong. So we have extensively used their services, their UAVs for mapping the various damages that has been caused by flood and landslide in the year 2022. Then we also have a very extensive reporting and information management system. In fact, as you know that mostly in many of the states, in fact, most of the states we used to have a manual kind of reporting of flood damages or any kind of disaster damages. So in Assam, we have introduced, in fact, in collaboration with UNICEF, we introduced a flood reporting and information management system. We call it FIMS, FRIMS. So in last 3 years, we have introduced that system through which actually all the manual system, which used to be very time intensive, and it compilation take place at revenue circle, district level, and state level. And also it used to have a very high probability of error since it is a manually compiled reports. Then we also require many manpowers to compile the same. And sometimes also this kind of manual reportings prove inadequate to support real-time decision makings and data sharing, which basically I mean to say that it basically lack the sex, age, or gender kind of related demographic details. Then as far as the flood governance is requires, it require a very robust kind of information and data system. And whenever we generate cumulative data, it always becomes a huge task. It's really to generate that kind of cumulative data from a huge set of daily flood reports that are being generated. So taking into that consideration, we introduced that reporting and information management system. Based on our learning on flood reporting through that system, it's a mobile and web-based reporting system. So from this year, actually, we have converted our FIMS into DREAMS, disaster reporting and information management system, and through which actually we have been collecting all kind of data related to damages in any sort of disaster, any sorts of hazards, like may it be flood, may it be storm or lightning or landslide or so and so forth other incidences. So at present we have 8 kind of hazards under DREAMS which can be reported at the sub-district level, at the district level, and at the state level actually. So these are few of the examples of using technology in disaster reporting for improving the information reporting and information management system. So this is all about
Actually, we are
I'm handing over to Biren.
Yeah, please. Mr. Biren, can you summarize?
Yeah. Yeah. So to sum up, actually, we have all the systems in place in our state, but what we need actually is a very hyper local weather forecast, because presently we are dependent on the rainfall parameter. We're dependent on the IMD. IMD issues us the alerts in advance in 3 different modes, maybe in watch or alert mode, and basically yellow, orange, and red. So that is at a district level. Now the problem what we have faced so far is that once we alert the entire districts, in many parts of the district, district is a big area, and in many places there is no rainfall at all, and that gives a wrong information to the public. So probably if we can get some hyperlocus weather forecast at the revenue circle level also, that will really help the administration in taking preparedness measures.
So what
we
is
have
the time dimension of hyperlocal forecast you are mentioning?
Pardon, sir?
What is the spatial and temporal dimension of the hyperlocal forecast you are mentioning?
Sir, right now we are getting we get nowcast at the city level 3 hours with a lead time of 3 hours. But in case of heavy rainfall alerts, we get 5-day warning in advance.
No,
District level one.
mention your requirement. You are saying you need a hyperlocal forecast. What is the
Yes.
dimension of that forecast you needed? Meter or within a kilometer or within every 30 minutes or 1 hour? What is that?
Sir, if we can get that one, maybe 6 hours also, or even 12 hours also, with a lead time of 12 hours also, that is fine for us also, sir. Because the administration will be made aware of that. Because right now we are getting 24 hours. On a 24-hour basis, we are getting district level focus, sir.
And can we get up to the revenue circle level or at least taluka level forecast so that the local administration can take note of that and can get that kind of hyper local kind of
Okay.
Another issue is that, sir, actually now we are using the CAP platform for dissemination of these alerts. So since the alert comes at a district level, we have disseminated almost around 12 crore SMS to the public. So in most of the areas that may not be there may not be any rainfall also, but still we are disseminating that to the public. So that is one challenge that we are facing.
Yeah. So thank you, Mr. Viren and your team. Yeah, thank you. Thanks a lot. So it would have been better if you could have come in person, but we are running out of time. But what I would suggest that there is a big community sitting here. Okay. From various, part. I mean, somebody is developing model, somebody is doing climate, weather, river forecast, Professor Bimal Mishra flood forecast. Everybody get in touch with this community and communicate your requirement. That's what the purpose WMO has suggested us, okay, to bridge this gap. You are sitting in Northeast, we are sitting across the world, so we are trying to bridge the gap, okay. So basically our research should reach you and your requirements should reach us, okay. Then only circle will be closed. So thank you very much. I am going to, we are running very short of time. I'm going to the online agency, NERLDC, Mr. Sahu. Are you there can you respond, Mr. Sahu?
Yes, I am there. Can you hear me?
Yes, sir. Yeah. Okay. So your WRLDC counterpart is here and he has already made a presentation about their requirement in the, so what I would suggest very briefly, if you can let us know what is your current weather forecast availability strategy you are getting, what is required, how you are managing the load during disaster, etc., etc. In 5 to 6 minutes.
Oh, that's very short time here given. We thought we will get more time. Anyway,
We are really running. Yeah,
okay,
please.
okay. Thank you for giving this opportunity and distinguished guest and chair Sri Bimal Mishra, Dr. Bimal Mishra, and co-chair Mr. Dr. Mukhopadhyay. Actually, I am joined by three of my colleagues. One is from Shillong and three of us are in Guwahati. The requirement basically actually what is happening, we have to forecast the load on daily basis, day ahead basis, and week ahead basis, and month ahead basis, and yearly basis, year ahead basis. That is basically our requirement. So what we are facing recently that we have a lot of renewable energy has come to the grid recently. So in NER, although we have less renewable, but the weather change is very fast in NER. So in recent cyclone Rimar, we have forecasted something, but at the end result was something. So there was a wide variation between what we have forecasted, even in day-ahead basis, and what actually the load was. So we have a short presentation. We'll just go through it, and we have put our requirement in that also, and what challenges we are facing. I'll just hand over to my colleague over here, Mr. Kishore, to present that presentation, and we'll try to finish it at the time allotted to us.
Okay, please.
Okay. Kishore, please present it.
Thank you, sir. I am audible. If I may, if someone may.
Yes, you're audible, please.
Thank you. Thank you. Is my screen visible? I'll just take 5 minutes.
Yes, yes, it is
Yes,
visible.
yes. Just for a starting, sir, we are as a power sector, Grid India, we are regulated by our CRC. So, and this Indian Electricity Grid Code tells us to demand, means forecast our demand daily, weekly, monthly, and yearly. And we have been doing so. So, I will just show some of the curves that Sahu sir has told. This is a forecast versus actual graph for 28th May to 26th May. Sir, actually, this week has been very good. We can tell this as a nice week where our forecast and actual based only on the demand data of previous 5 years. Means we are running one algorithm here, machine learning based algorithm, and that has given us very nice forecast versus actual. We can see here the error, that is the RMSE error is within the acceptable range. It is 6.6, 6.8. Obviously, the Sunday was a bit difficult. It was 16.6. But however, when we come to a Rimal impacted week, that is a cyclone impacted week, then we can see on from that the week from 27th May to 27th May to 2nd June. Sorry, this will be a typo mistake. So this week, our forecasts were not at all at acceptable ranges, sir. We can see that we had a error of up to 155 percentage, and also these are unacceptable. That 30 percentage and 35 percentages is a very high forecast. We are not able to meet properly plan our actions before. So actually, our way of doing forecast is only based on the demand data. We are not receiving any kind of weather data. Actually, weather data we are means we can obviously take from some of the websites, but as I have told that we have our in-house made machine learning algorithm for that training. We need around 5 to 6 years of old data, weather data, some of the which I have noted down here. As I have very shortage of time, I will just skip all this. I have made a very brief presentation here. Yes, sir. Here, the weather data that we will be requiring is the temperature, that is historical forecasted temperature, humidity, wind speed, solar radiation, precipitation, and weather events. The weather events like heat waves and storms, cyclones. If this would have been present with us, then I believe we could have more perfectly trained our model, and this gap of such huge errors can be minimized. Also, we are always very free-minded for other statistical or machine learning based algorithms. I believe there are many spectators and shareholders in this meeting, so we can discuss among many of these algorithms. Further, we have very limited knowledge of how to uh, collaborate this forecast with our electricity prices, fuel prices, availability, market data, outage data, transmission and generation availability, transmission constraints, generation constraints. So we would like a solution to all these things, and the solutions also in a more practical manner, such that we can move forward and reduce this gap of huge errors. Sir, in this short time, that will be all from my side, sir.
Just I want to add, actually we forecast every 15 minutes, we have to give a particular demand. So if you can that in that granular, if you get that weather data and the various part, particularly where the industrial areas are there and where the, I mean, population density is more, that will help us, sir. If you can give some suggestion or some site or some way to get the data, so that we can integrate to our this algorithms, these weather data, so that we get a better forecasted result. This was our requirement. Thank you.
Okay, thank you. Thank you, Mr. Sahu and your team. So we are going to write a recommendation. So we will note down some of your points. Okay. And I will see you maybe on 14th. I'm coming there. So thank you. Thank you so much. So I go to next, Dr. Sagar, you are here, Renew Power. Can you please quickly come and give your views about in 5 to 6 minutes? So Renew Power is a company who is dedicated in the wind and solar, right? You can go there and go to the stage and yeah, please.
First, I would like to thank STIPMEX and IITM for giving me opportunity here. To begin with, we are using reanalysis product at the same time, short range forecast and the seasonal forecast. Now coming down to the challenges that we are facing at this moment, we are seeing systematic trends in wind, then even the climate variabilities are not very clear. When we see for the monsoon, it's very well established for the how the teleconnections are observed for different years. But when we come for a wind, it's still missing. So I think there should be a in-depth study how the climate variability is impacting to the wind. To set an example, second, there are temperature gradients which we are observing for last 4 months. When I'm seeing it from January, February, March, we are able to see a negative trend over the entire India while a positive trend over the ocean basins, while it has changed in the May. So as a result, we are having uncertainties where which is directly impacting the wind farm performance and giving an uncertainty again for the financial risk, how the investments has to be done. Then if we could get a better predictions of western disturbances or subtropical jets, it will be again an additional thing. Then coming to the challenges, another that we are facing from the forecasting or the data qualities. We are still not able to exactly say what should be the climatology time step we should be considering, because what are the data sets that we are having prior to 2000 is not it's not meeting the standards that are required from the renewable energy industry. So if we could look into that and see how we could improve the reanalysis product prior to 2000 will be an helpful thing. Then trends in wind patterns, as I said, if we could able to establish, it will be again a good good direction. Then coming, there are really limited providers when it comes to subseasonal to seasonal forecasts, particularly which are working in the renewable energy sectors. So even there, we are able to see a significant variations among the providers for different locations, and then even the deviations between actual versus what we are getting as a forecast is huge. So it's not really where we can match. Then there is a huge inaccuracies whenever there is a complex or a complex topography or a coastal regions, which again gives issues when we are doing some forecasting thing or suggesting some locations. Then most of the reanalysis products or forecasts are available either at 2-meter height or 50-meter height, 100-meter height, and directly to some hectopascals like 975 or 950. But as per the renewable energy, we are more concerned if we could get wind data from 0 to 300 meter. And secondly, whatever forecast or the reanalysis product is again at average of 1 hour. If that can be diluted to 10 minutes, it will be useful, because as someone has suggested in the previous session, 15 minutes grid points are needed in the renewable energy sector. So that would be again a helpful thing. Now coming what we are looking forward from the Met Society, if we could get a higher resolution model outputs, particularly targeting renewable energy, where we could solve the subgrid scale parameterizations, where it could solve both for wind energy as well as the hybrid systems that we are working on. Then better representation of the lower levels, like from 0 to 300 meters, it will help us, or at least to the height where we are having the rotor planes will be an helpful thing. At this moment where we are standing, India has best understanding when it comes to monsoon and its teleconnections with the best, what I would say, Met Society. We are one of the best people in renewable energy sectors. But, and again, as our Honorable Prime Minister has said, we have to achieve a target of net zero by 2070. The critical way where we can achieve this is a renewable energy. So I would request all of us to come together, bring forth the best knowledge that we are having both from renewable energy as well as the Met Society, and overcome the challenges for the greater adoption of renewable energy and harness the scientific and technological advancements. That's it from my side.
Okay, thank you, Sagar. So just one question before you finish. From where you are currently taking the seasonal and S2S forecast for your purpose?
So I'm taking from C3S.
Okay, so you are not using any of our Indian products so far?
So I'm using short range production.
Short range is fine.
From NCMRWF, but
yeah,
we are still
so,
under.
MOU. Yeah, that's correct. Okay. Okay, thank you. So lastly, I will request again WRLDC Grid India Mumbai, Mr. Kodali, you can very briefly say that although we have already heard from many, but if you have anything remaining to say, then we'll close the session. I will request Professor Bimal to thank everyone and summarize.
Thank you. I thank IITM for since 2020 onwards, they are continuously providing the weather data to WRLDC and helping us to see the demand and generation, how they are varying, and that has been very helpful to us. Particularly, I just want to cover in 2 minutes regarding renewable energy. So in renewable energy, the main challenging will be the cloud cover in western region and also in Rajasthan, some areas. The solar energy is concentrated at some locations. So whenever there is a cloud cover, we are not able to forecast, or we cannot include that model into our system. So it leads to a lot of disturbances in the system. So that is the requirement. And also at present, we are getting day-ahead forecast, weather forecast, and also intraday forecast. If we are able to get at least 2 or 3 regions, that we can incorporate on our intraday demand forecasting so that it can be improved a bit. That's all from our side. Thank you.
Okay, thank you, Mr. Kodali. So before we end, thanks a lot. Before we end the session, I have been told that so there are some stakeholders who have actually actively supported this STIPMEX workshop. It's already written there, Agista, MNG, and TESCON. So we wholeheartedly acknowledge their support for this STIPMEX workshop. It's a huge one. And there's somebody, VJ Industries, Vinayak, Mr. Jiman. Is it here? Or you like to say something in very quickly? Yeah, please, you can come there and then we'll close the session. Yeah.
Good evening, everybody. And thank you, IITM, for giving me opportunity to express myself and about my company. Basically, we are dealing into the green hydrogen storage system. And everybody knows that IITM using hydrogen for various applications. So since 10 years, we are supplying hydrogen gas to IITM. Now we are making hydrogen storage systems also. So wherever the green hydrogen projects are going on, we are offering our services to store this hydrogen. So either it would be from solar energy to hydrogen, wind to hydrogen, and many other applications. Along with that, we are supplying many kind of gases and all the accessories also. Now we are authorized channel partner for Horiba gas analyzers also. So air quality measurement purposes, water quality analysis purposes, we are ready to supply all kind of services to you. So thank you.
Thank you. Thanks a lot. So Vimalji, please. Please, Professor Bimal Mishra. Yeah, you can go there and you can give your views and yeah, please. You have already heard everyone. Thank you. Thank you.
Okay, so first of all, many thanks to all the stakeholders for putting their views, their requirements, their challenges, limitations in the forecast. So what we understand basically that there is certainly a gap between the met forecast scales, both temporal and spatial, and at what scale stakeholders need forecast for proper decision making. So if we summarize based on the entire discussion, the common theme which is coming out is that stakeholders need high resolution weather forecast, which is, of course, had better forecast skill at different lead times. And also they need, higher temporal resolution. Like ASDMA, their challenge is they are getting district level forecast and they are giving entire district warning of heavy rainfall. And you can think of within the district how much variability will be there, and there will be significant number of false alarms, and people will lose confidence on such forecast very quickly. So I think this is a great sort of takeaway from this stakeholder, and the needs and requirements are same. You talk about hydrology community, you talk about people working in agricultural disaster areas, disaster management, energy, renewable energy production, or others. Their needs are quite similar. That forecast resolution need to be improved, accuracy need to be improved. Of course, there are challenges involved in doing so, but we have to think that how we can develop forecast that is not only useful but also usable, and that can be used for decision making and minimizing the losses because of different disasters or because of false alarms from the forecast. So with that, I would thank once again to everybody who participated in this discussion. Your suggestions were extremely important for us. And I think all the climate, weather, meteorological, scientific science community can basically understand that still there is a lot of progress need to be made to fill this very considerable or significant gap. Thank you very much.
With this, we come to the end of the stakeholders session. Thank you, Dr. Mukhopadhyay, for chairing this session. We'll now move on to distributing the best poster prize distribution, best poster awards in the two categories, one under stratosphere-troposphere exchange processes and another under prediction of monsoon weather extremes. For this, I would like to invite Dr. Partha Mukhopadhyay and Dr. Suvarna Fadnavis on the stage to kindly give out the awards. So I'll begin with the STI segment. The third prize in this segment goes to another party from IITM Pune. The title of our poster is Impact of Volatile Organic Compounds on Ozone and Secondary Organic Aerosol Distribution in Asian Summer Monsoon Anticyclone. Dr. Annada Pari is not here. So we'll move on to the second prize for the best poster goes to Dr. E. Ashutosh from IIT Bhubaneswar and NCAR USA. The title of his work is South Asian Summer Monsoon under Stratospheric Aerosol Intervention. The first prize goes to Athira KS from IISER Mohali. The title of our work is Impact of Sudden Stratospheric Warming on Extreme Winter Weather in North India. Dr. Athira. Okay. So we'll move on to the next segment, prediction of monsoon weather extreme. The third prize in this category goes to Tanu Sharma from IMD Pune. The title of our work is Indian Summer Monsoon Rainfall Response to Two District Features of La Nina and Performance of Seasonal Forecast Models. The second prize for this theme goes to Ms. Sakia Shabnam Kadir from Daffodil International University, Dhaka, Bangladesh. The title of our work is Transport of Water Vapor Associated with Monsoon Rainfall over Bangladesh. Dr. Sakia. And the first prize in the prediction of monsoon weather extreme goes to Dr. Sujatra Bhattacharya from ISC Bangalore. The title of our work is Mechanisms Governing Rainfall over India During Monsoon Onset and Post-Onset Phases. Dr. Sujatra. Okay. Dr. Anada Pari. She won the third prize in the Stratprop exchange category. Thank you, sir. Thank you, ma'am. So congratulations to all the winners again. And we'll quickly move on to the last and final session of our STIPMEX workshop, which is the panel discussion. I request Dr. Veenu Valsala to kindly coordinate the session.
Thank you, Chaitri, and very good evening to all the people part of STIPMEX. Again, I'm here. So while they're arranging the stage in the interest of time, and I will read out a quick summary of what we have listened to in the last 5 days of discussion, scientific presentations, and the first day of training. And so let me give a brief overview. So in the past 3 days, the exclusive sessions on the stratosphere-troposphere interaction have brought the following conclusions. Monitoring and modeling the atmospheric composition play a critical role in supporting social needs related to air pollution, ecosystems, human health, food, and climate change. However, the gaps in process understanding of several of the STI and atmospheric chemistry processes still looms in this area. For example, there are gaps in the understanding the processes in the CPT, the role of convection, wave, and wave breaking, leading to the UTLS phenomenon, water vapor distribution. Still, there are a lot of work to do. The many presentations illustrated that. UTLS regions are underrepresented in our observational networks, which is a huge gap. For that, location-specific measurements campaigns needs to be initiated, and dedicated instruments are the key in expanding the network, and they are discussed at the length during last five days. Observations leading to the specific understanding of the atmospheric chemistry phenomenon and distribution needs to be envisaged. One such example is the targeted observation for Atal to remove the impacts of volcanoes and wildfire episodes from satellite data. So innovative ideas has to come up. The methodology and innovations need to be brought out. The session also had presentations on strength and weakness in our understanding of radiative forcing, particularly related to aerosol and atmospheric chemistry within Atal. Although it's a very fundamental topic, they highlighted it is still lacking in our understanding. A need for the observations of sounding in Atal is stressed in particular, and some of the presentations discussed also the stratospheric tropospheric connections and their role in QBO, ENSO, and NAO, MJO, etc., which are most familiar to most of the tropical climate scientists. And relations between volcano activities and short and long-term climate variability such as ENSO were also discussed. Now coming to the PMEX section of the workshop, a few talks brought the notion that with improved model physics, models are indeed improving. However, An important question emerges whether we need a new different parameterization for the mid-latitude and the tropical regions, which has yet to be tackled. Looks like a fundamental problem, but still remains gap. Extremes are predicted in NWP, but accuracy is questionable, right? So even with the advent of data-driven methodologies and probability-driven numerical forecast, the accuracy is a daunting task even today. Is there a need for region-specific optimization in models? Is an open question, which came up in several of the previous talks. And improved data assimilation techniques along with AML and perhaps are the key to tackle some of these issues in predicting the extremes. And this leads to the need for lots of observational data. And therefore, worldwide wet agencies need strong collaboration and policies to share the data within themselves. Feasibility of prediction of extreme with precision in intensity, location, and time. How good are we standing today in the NWP community? What are the predictability limit of extremes itself? There are various kinds of extremes. They say it a lightning hazard or rain, flash flood, etc. Now, do we have a concurrence in it? Can the limit be pushed with the AML methodologies? Is unified model framework possible for weather prediction till climate projections? That is also some of the presentations were highlighting on that. Such questions turned out to be important. For example, how can we approach the events like Mumbai, Chennai, Kerala floods, which were around 10 sigma deviation and above? And how are we going to solve such predictions and provide services to the societies? With the known uncertainty of NWP models, one recommendation is that perhaps the ensemble prediction is a good way to go about. And however, how to effectively communicate ensemble forecast and its outcome in its last mile to the stakeholders and the beneficiaries is still a challenge, and this we have to figure out. Also, a worthwhile point is the whether the weather modification or management can be used to mitigate the extremes. Several interesting posters were also presented, and I cannot list it all here or summarize all here. There were very interesting and a lot of interactions were happening between the students, early career researchers, and the experts in the field, and that's I would say it's a success of this workshop. With this short summary, the chairs are all set for you. I will invite few key people to be the panelists in the panel discussion. There are a lot of expert people here, so we just pick some name, okay? So first I start with the component of STMI, Dr. Simon Tilmes. She has to leave early, so kindly please. Oh, okay, so and then Dr. Rolf Muller and Dr. Simon, but they have to leave early, so please kindly take the chair on the dais. And I would also request Professor Greg Carmichael, if he's around, please join us. And from the PMEX side, I request to join Dr. Vimal Mishra, please join here. And invite Dr. Estibalis Gascon, she around? Yeah, please join. And Dr. Subin Singh, is he around? Dr. Subin, please join us. And so there are a few people online. For example, Perry Gentine, Dr. Perry Gentine from University of Columbia, New York. Is that right, Parthoji? Kindly join online. Okay, so we have two more chair. I call Dr. Peter Hitchcock. My apologies. Dr. Peter Hitchcock, kindly join. Dr. Suvarna, anybody we in particularly want to invite? Okay, thank you very much. So with this, we are officially beginning our panel discussions. And so as I given you some introduction or some summary that what we have done in all these 6 days, especially 5 days of presentation, you have heard it. So if you have any points to add on to that, anything that is missed or some point to be stressed, you can start. I will pass the mic. So mic bearers, kindly come up stage and share the mics. And also the audience, please also kindly give your comments and recommendations. So I'll start with here. Please go.
Yeah, I would say a few words before I unfortunately have to rush to the plane, but I think it was a great workshop. And what I think, speaking for myself, I learned a lot about the achievements of the different weather models of the world that I'm perhaps a bit more familiar with, not only the Indian ones, of course, but also international in Europe and in the United States. So this was good. I learned a lot and heard a lot that high resolution models are important. I heard a lot about the combined use of artificial intelligence and the more classical physical models. And I think that this is a good development to combine these developments rather than saying either or. I was also pleased to see so many younger people here, also more established researchers, of course, but a lot of early career people. For me, it was very fruitful to work on ongoing collaborations, especially with my colleagues here in India at IITM and elsewhere, and also to discuss, for example, at the posters, some ideas of new developments of where there could be future collaborations, or at least ideas that could be further developed. So with that, I think it was a very successful workshop. Also, the second part, of course, where I learned a lot about extreme events that I did not know. And I am very happy to be here.
Okay, thank you. So I invite Dr. Simon to express her views and. Oh, okay, yes, please. I think all on dais is not linked.
Okay, yeah.
You can go ahead, yeah.
Okay, yeah, thank you very much. It was a very great workshop. I really thank the organizers for the hospitalities for the evening program. And I absolutely agree with Walls that the whole combined program was very insightful. I learned a lot in this conference, and talking also about observational analysis, what is available. There's a lot of observations that are provided in places also over India that I wasn't aware of, and then that can be distributed. One part that I'm also talked about, and I saw interest in, is the climate intervention part, really the part that we do need to look into what not only climate change is doing, but also what will potentially climate intervention have to do, and people here, and especially in the places that are most impacted, may actually benefit from those interventions the most, but they may also suffer the most. So there is really need for people in this country to look at the impacts themselves, to understand it, to have capacity building. And I see this here, we had great collaborations, Suvana and others to talk about this. And I think that's quite beneficial, including seeing all the other processes and events that contribute. So this is such a rich topic. So thank you very much.
Yeah, thank you. Thank you, Simon. Professor Greg.
Yes, I think congratulations to the organizers and to all the participants. I think it was a great workshop. I was very impressed by the community and how much it's grown in its capability, especially in the region and its interests. So I think it's brought a lot together. I think a couple of things came to mind. Certainly, the role of atmospheric composition was played out here, and there's the importance for the atmospheric composition observing system. We see the importance of these special experiments and how it stimulates process understanding and pushes models and understanding. But also, we also see that there's a need for the regular observations, how the surface-based observations are critical to understanding what gets lifted and how it gets distributed. So I think there is a general momentum in building that we need to enhance the observing system, both the special observations, but also the regular based, both surface based as well as, again, under the GALT program, the routine aircraft observations, balloon soundings, and all those sorts of things. And I think that this is a good example of moving that forward. I think the other thing that's needed, and we see a great movement in terms of building out the Earth system modeling frameworks. And there are many examples of that. And so we see that's moving forward. I think we need to enhance the atmospheric composition components of that. We heard many times today during the meetings about, well, what's the role of fires and other elements that we need to be building into that Earth system process on the the role of ammonia and the nitrate formation processes. And so we need their system framework to help reflect our process understanding and see that getting into our coupled models, because those applications cross the scales from short-term numerical weather prediction all the way to the seasonal, subseasonal perspective, and then the climate system. So we're moving more and more towards these integrated systems. So I think that's really important. I didn't get such a sense for the climate. I think the climate interventions are really important. The role of climate change in the whole process, I think, is still important. How that climate change and how it increases the monsoon system is interesting. I would like to point out that India is and will experience in the near term, whole of East Asia, South Asia, we'll be seeing strong climate intervention as sulfur gets eliminated from, reduced from the sulfur emissions from air pollutants. We're going to see a real transition from where we were from a heavy pollutant-laden environment of aerosols to one that's going to be driven less by anthropogenic, but more by wildfires and other components. So I think that's an interesting component. I think the other take-home message that I have here is from the WMO research programs. I think we see a lot of, I know a lot of activities from WCRP, WWRP, and GAO. So I think I'll be able to take back to the research board and talk about the opportunities to further enhance our collaborations among those research programs in this important area. Thank you.
Yeah, thank you. That's an excellent point that he raised. Before going to Peter, may I ask, there is also a request from, not request, a letter from David to you. He has mentioned how good are we in observing air pollutants over Indian. We are good, of course, we are doing, but the concern is that how are they able to access it? But that has some critical problems that we know internally. So do you want to comment on that? Because Dr. Greg also mentioned about the observations, especially on chemistry. And do you have any comment how we can, within the limits that permits us, but we can go ahead. So can somebody pass the mic to Dr. Sohan? How good are we and how are we able to tackle this problem of, sharing data?
Yeah, there are observations going around in India in different university at micro level and macro level both, and they are scattered. And there is efforts also going on to bring them together, but it will take time.
We
Momentum has
very well understand our limit.
initiated, and individual level, everybody is trying to do research and take more observations, and they're coming together. So we hope that it will happen very soon. And yes, that will be shared soon with the international community.
Yeah, I think we also have our own regulations and some of the regulations.
And yes, still we need more observations.
More observations. That's definitely a point. That of course.
Thank you.
Yeah. So now I ask Dr. Peter if you have some points to mention regarding this STI before I invite PMEX people.
This check. Okay. Well, I will echo what has been said before, which is that I've been really impressed by this workshop. I've learned a lot. And in particular, I've been really impressed by all of the early career scientists and all the work that they're doing. I think we've heard a lot of different components of the enterprise of connecting climate forcings of different types, air pollution, to extremes that are really directly affecting people both here and around the globe. We need all aspects that have been reflected here. So I'm impressed by this workshop in that we've brought people on the process side together with, well, the organizers brought people on the process side together with the forecasters, together with the modelers, together with stakeholders, and that conversation across that whole enterprise needs to continue. On the sort of stratosphere, troposphere coupling side of things, there's, I think, a big role there for understanding attribution of extreme events to both drivers in the climate system, and as well as internal variability. And so that's, I think that's a particular area of interest to me. I think that's understanding both when extreme events are happening and why they're happening is going to be very important, and communicating to stakeholders, but also understanding what policy interventions will help to address the extremes that are getting worse. So, there's a lot of work to do. So I kind of wanted to communicate directly to the early career researchers to say there's a real need for your expertise to solve these problems, to fill these gaps. And I'm encouraged by how much good work is being done here. And so thank you to the organizers, and I'll stop there.
Yeah, thank you, Peter. We'll come back to you. So now I ask our extreme precipitation experiments. Dr. Subin, you want to say some words? Begin with.
Oh, thank you. Thank you so much. Well, I think I agree with all of you that the workshop was fantastic. Thank you so much for all the organizers. The hospitality was great, was incredibly impressive from your side. So I wanted to say also that I had a chance to evaluate the posters, and I have to say that they were really impressive. I don't know if
we put her on task.
Yeah, difficult task indeed. But I have to say that I learned a lot from them. I asked a few questions after that, even if it takes me time to evaluate, because I was really interested in what it was been doing here. I think that I didn't know about all the progress, especially in tropical cyclones studies that have been developing here, teleconnections. I think that this is very valuable also for us to learn in ECMWF, to know what you need as well. And I would really be happy if you give feedback when you use our products, because it will be really useful for us to understand what are the deficiencies that we are experiencing in areas like India, that we don't really receive too much feedback. And they are the most challenging areas for us. So tropics, but especially in this area. And you have quite a lot of severe weather events that we can learn about. So if you have any issue or the forecast you think that is really wrong, please report it, because we analyze it deeper, and we can understand the processes that are not being resolved well, and we can move forward in the development. And finally, just to say, I was really happy to see the starting conversations of machine learning together with ensemble forecast, together with model development and improvement of the model physics. I think that we are in a point that all of this is mixing, and we are starting in a point that we have to decide and learn what we have to do with each one without messing up, let's say. So we cannot substitute any of the model physics clearly, but we can improve and help to produce better model physics with machine learning, of course. So thank you so much also to everyone that contributed to that, because I learned a lot. And yeah.
Thank you, Dr. Stibalis. Actually, this is a very good open invitation. You report your troubles when you use the analyze products of ECMWF. Then there is an invitation you can report back, so that they can understand what was not predicted or what was not analyzed well. So with this line, I will ask also Dr. Perry Gentain is online. Are you hearing us? So do you have any words to share on this? Dr. Gentain, are you there? Okay, and another Dr. Mark Hobe is there online. Are you hearing us? Do you have any? We have received a letter that you wrote to Dr. Suvarna regarding the recommendations in terms of collaboration, continuity, observations, etc. We have a long list. I'm not reading it out. Do you want to add on to that?
Well, I wrote most of my comments into that list, indeed. And yeah, I mean, I was really happy to be in Pune. I'm now back home, and I was impressed with the quality of science that was presented there. And I think it was so nice and so important to bring the different people from different communities together in one place to talk. I mean, we come from field campaigns where we naturally look more at chemistry and small to regional scale dynamics. And then you had people looking more at really large scale dynamics, teleconnections, and then the extreme event community and the stratospheric, tropospheric community. So everyone was together. And so you could really see how you could go roads where we join all our forces and put all our information together to understand the system as a whole better. And I think that in that respect, STIPMEX was really a an event that was unprecedented, in my opinion. So I hope that it's only a starting point for a long road. We'll go together, and at the end, we'll do good science. And I also want to just say that what Peter Hitchcock already said about the young scientist, I think it's so great to see so many very promising young scientists who are already doing science at a very high level, who will be the next generation and who will go further along this road when we are leaving or getting close to retirement or whatever. So they are the next decades and long-term commitment in science, and that's great to see. Yeah, that's all from my side. Thank you.
Thank you, thank you. So in response to that, thank you all the, all you delegates have contributed to the training program also on the day zero. We call it day zero, Sunday. That was excellent. It was excellently arranged, and without your help, and would not have been possible. Especially the lectures from this extreme event group. That was very helpful and really encouraging our young manpower to take up interesting problems. So with this, I request Dr. Subin to share your words on how do you feel and what is your recommendation. Can you please spell us?
Yeah, I have a few reflections. First, I truly enjoy all the presentations, the facility, and equally important, the hospitality of the hosts and the people. If I put on my hat of leading GPEX and GPEX, this is the first time to attend the troposphere-stratosphere interaction, and hence actually give me quite a few ideas for the further interaction between GPEX and the APAC, and now also GO. So that's really outstanding outcome for future collaborations between different programs. Then for the GPEX, I've had some very substantial conversation with quite a few people here in terms of anchor projects, field campaigns, and modeling. That's really pretty good progress. And I have had spent much time talking with students and early career scientists, really impressed by their talents and equally important, the passion. And finally, I feel I have gained something in terms of overall understanding of Indian culture and Indian way of doing science. This is very important because this is my first visit. We are going to have many more interactions. That understanding is as important as the science itself. Thank you.
Thank you, Dr. Subin. Thank you very much. So I now pass on the mic to Professor Vimal. So he's most known figure in India and abroad for the extreme weather, tackling it, last mile connectivity, stakeholder interaction. Professor Vimal.
Yeah, so I think I agree with everybody. A lot of positive outcomes, though I could only attend today. So I came yesterday evening. So I think what we can see as a challenge, like what we want to do in, let's say, coming years, I think one challenge I would think of is considering climate change, whether the predictability forecast skill will improve or go down. We need to sort of understand that how climate change is itself posing a challenge to sort of limiting the forecast skill of extreme weather events, considering that unprecedented events are occurring now, which we might have not seen in last 50 or 100 years. That is number one. Number two is we need to think about whatever progress being made in science, how that translates into filling the adaptation gap, because climate adaptation in a country like India is extremely important. And because of climate change, adaptation gap is increasing very rapidly. So first, what do I mean by that? Like whatever progress we make, climate change itself is putting bigger targets. So there is a gap, how much we can adopt and how much we cannot adopt. Now we need to understand that how early warning of extreme weather events can help in adaptation in different sectors, be it agriculture, water, energy, or others, disaster risk reduction. So I don't know whether we know fully that how effective is early warning system in climate adaptation and how often maladaptation happens because of, early warning. So, I mean, finally, I would say that there is a critical need to understand the impacts and also work with the stakeholders and get feedback from the stakeholders, because I think a lot of progress is there, but not everything is translating in terms of improving our ability to make decisions. Finally, I think we should do science for solutions, given that climate change is posing very significant risk to a country like India. So we should think how scientific development translate to solutions that can help and enable communities, society, and people of the country. Thank you.
Thank you, Vimal. That it's very powerful message. So now with this, I was already, or people on DICE already have spoken their views. I online, Dr. Piri Gentil is online, right? Partho, are you hearing us? Dr. Gentil, are you hearing us? Then can you speak up? I don't know whether he joined. Can somebody find out from the IT team, Dr. Piri Gentil has joined? Okay, while they find out. So as a scientific coordinator, Dr. Partho, so you have any invoking points for discussion to this? Yes, please help me to pass one to one. Oh, I can't see. I'm sorry. Okay, I invite Professor Ramaswamy. So can you please join us in the panel discussion and express your view?
Can I do it from here?
Yeah, please go ahead.
Yeah, so I don't really think I have much to add to whatever has been said by all the people on the stage, because they've captured very well all the high points and also maybe points which were implicit, but nevertheless were important enough in all the talks. And there were so many points. But I think I would sort of say in terms of the leading edge, it's probably got to be the emphasis on atmospheric composition, yes, but also the coupling of the various entities that we come to know of under the Earth system banner. And it takes different forms, but ultimately, as we realize the increasing intricacy of all the things that are conspiring to give us the climate and to give us the air quality, the oceans, the ocean system, the land system. And it's not just that these things force the climate, but also how climate forces changes in each one of these, which are of consequence for society. So some of these might be, not just temperature, but also other things like wind, for example. I mean, we talk about temperature and precipitation a lot, but I think in the talks today, later on in the afternoon, there was a talk of the wind energy, and how it plays a role in how power calculations are going to be made. So, you see increasingly the whole issue of weather, climate being intertwined with so many aspects of society, that the statement was just made by Professor Vimal about climate science providing solutions, or weather and climate science providing solutions, is going to be important, because it's inevitable that we have to be looking at a solution with a solution orientation, but rooted in science. And I think that was brought about in several of the talks, especially on the AI side, where AI progress is something that's going to happen, keep happening. It's moving forward at a very fast and furious pace. But how the science comes alongside it the physical science, chemical science, dynamical science comes alongside it, that is also going to be important. So, you know, again, we may all be accused of making the system too complex, but that's what it is. We are trying to understand it more, understand it deeper, and that's the penalty that we are living with. That as our understanding grows better and better, we start to realize there are so many other things that we may not have considered 10, 20 years ago, but are now nevertheless important. And also, I think as climate change, you know, is becoming, I would say, more accepted, and the causes of it are getting more accepted, you know, compared to maybe 2 decades ago. You know, it is really something that now we are going to understand for how to make things better in the future. And that's kind of, you know, really, I think that notion seeped through probably every talk or every session in at least an implicit manner, if not explicitly. And I think that's a pretty strong message that this workshop is giving out. And I would strongly really underscore points that have been made about a lot of the passion and enthusiasm shown by the more younger people in the crowd and in the early careers. I've been very impressed in, you know, talking with just a few of them that I had an opportunity to do so, but also in the room, a lot of really the energy. And I think that's really great for IITM, Indian science, but also the world community, because there's so much to learn from them. So I think I offer my congratulations to really everyone who participated in this workshop. And of course, a big thanks to the organizers for arranging really a very, very eminent set of talks to be given at this workshop, and for the very nice discussions that are flowing right now. I mean, it's really very captivating. So again, congratulations to everyone, and yeah, safe travels to all who traveled from distances here.
Thank you. Okay, so because of the recommendations of lot of measurements required in, for example, stratosphere, troposphere interaction. So I invite the comments of Dr. Venkatratnam. They are involved in a lot of measurements from ISRO, and so kindly please.
Thank you very much. Really, it's a great workshop, I could say. In the last 5 to 6 years, this is the best workshop I could attend. Now, coming to the observation, in fact, there are a couple of talks were there where they were showing that there are no observations over Indian region. In fact, if you start filling that the observations with the dots, India map would not be seen at all. So those many observations are available in India. But I must admit that they are not part of any global network. But there are many observations are available. Of course, as Dr. Suvarna has mentioned, it's scattered, but they are well maintained, well calibrated, following the standards of NOAA. And for example, from where I come, almost a decade of observations are available where well maintained and well calibrated data. Somehow it was not echoing in those kind of presentation, but we have a lot of data set. So my suggestion would be, of course, as Vinu was mentioning, there are some rules and regulations. Until that rules and regulations are formulated, my suggestion would be they can be created a metadata. Means you don't need to share the data, but the information that I have this data, somewhere if I mention, like-minded people can come together, they can start working while the rules and regulations are being made for to share the data, either in the network or in this one. So that is my first suggestion. Coming to the second, that stratospheric tropospheric interaction thing, there are several campaigns have been conducted in the last 5 years. And I could see that almost every representation was made. But I could see that there are several common objectives were there, but definitely there are some other objectives for each campaign. I would have suggested that if a common platform has been made, where that some of the resources can be reduced, because similar objectives are there, I could see among all the waves.
Right.
My third thing is that in India particularly, of course, elsewhere may be the same. Observations people will not look into the modeling people, and modeling people will not look to the observation people. And there should be some synergy. Both observations model, if they come together, I think we can do the wonders. And particularly for stratospheric tropospheric interaction, we can do the best, I think, That's all from my side. Thank you.
Thank you, Dr. Venkatratnam. But answering to that, at least in institutional level, the atmospheric observation people and modeling people are coming together. We have visible examples in IITM incorporating the parameterization from the observation into the model developed from our own observation. That's kind of encouraging points are there. But intra-institutional level, we need to still figure out perhaps mechanism and across the borders. That's another major issue to tackle. That's right. So with these short words, can I pass the mic to Therevasan? Can you please share a few words on what is your recommendation after seeing this effort of bringing people together under these two themes?
Thank you very much. So I also so much enjoyed this workshop.
How is your throat going on?
Very not so good. Maybe like
Sorry to hear
very
about
hard to avoid the voice.
Recover well, yeah.
Sorry. So maybe one of the reasons of this voice is the kind of energy I felt in that the poster session in this hall here down here. That maybe the day before yesterday. So I met many young researchers in the South Asia, especially Bangladesh, India. So and the many posters are very nice. Sometimes they have some limitation, but it's also very good when we discuss some response coming back. And so they also access to me to suggesting some other new projects or some new research collaborations. So that the whole is somewhat close, a very big voice is needed. So I have to shout there. And so I told them using the loud voice after that. And the next morning, I found this, my throat broken. and yesterday, I couldn't talk almost no talk yesterday. Today, free. And so accommodation is also very nice. So because people in IITM are treating me so nicely. And so they drive me to the hospital. So it's very nice. So yeah, such a international collaboration is important. So for each year we are hospitalized in each different countries. And so in this time, so Japanese people not so many. Another Japan, one couple Japan here, one, but Kawata-san is there. May not here. But so many limited person personally coming this time regularly. So we would like to increase such a collaboration with East Asia and South
probably
Asia.
GPEX is occupying them. It is coming after
GPEX. Yeah.
He was mentioning about that. Probably that keeping them busy. Yeah.
Okay.
Anyway, yeah.
So on the next 1 month, we had a GPEX conference in Sapporo. So many Japanese coming. And also we like to welcome all to this conference. And we may discuss about future projection. Also, this month also, there's AOGS in Korea.
Okay.
So we may collaboration much more in these over the Asian countries. And I enjoy so much. Thank you very much.
Thank you, Therevasan. So I invite the senior opinion of Dr. Rajagopal. He was very much in this workshop, framing this up. If I proportionate it in numbers, 33.3% Rajagopal, 33.3 Suvarna, 33.3 Partho. What is remaining? 0.001? That's me. So please, sir, your recommendation after seeing all this, about the science, what we discussed.
Thank you, Venu. And I was mostly doing some sort of a scientific administration only in this 33%. Chasing people, getting funding, writing mails,
Yes,
with
that's
many
the
people.
most important part of the.
We managed to get some eminent speakers to this conference after a lot of persuasion with WWRP. I think the quality of the workshop was great because I have never attended any stratosphere-related meetings before because I was a hardcore NWP person. I find there is a lot of activities which are going on in the stratosphere which are impacting normal weather prediction also. So I think the linkages have to improve more. And I think under the monsoon panel also we are trying to get involved with EPAC, who are basically the SPARC people who are doing stratosphere troposphere interactions. So we are trying to get some collaboration with APAC, ACAM, which is basically Asian monsoon related project. So I think it's going in a good way. So start more interaction. We were thinking that we can have a top at tropopause is enough. We have to go further above. Maybe the model levels, as Partha had shown, increase it up to 117 numbers, covering more of stratosphere. And because it's all interconnected, it's not, we were thinking initially all our things were limited with computing. So once you have more computing, we can think big. And I always say, everybody always think big. Even if you don't have computing, it will come through. But you do something very big, plan something very big, forget about that. It's going to be over-tiring for you. It will be always fruitful in the end. So that's my message to younger generation. So aim big. Don't complain about things are not there. They will all fall in place. Yeah. That's how even NCMRWF, where I was heading, evolved in this way. Thank you.
Thank you, Dr. Rajagopal. So now I invite Professor C. Wok Soon. Are you around? Dr. Soon, are you in the stage here? Okay, so now I will invoke some view of Dr. Partha himself, who was scientifically designing this part. While it was a challenge for him because stratosphere and troposphere interaction theme and this extreme weather theme has to come. So there are signs because it's all part of your system. So that itself became a challenge to begin the conference.
That was the first biggest challenge.
Yeah, challenge. So can you
couple the stratosphere, troposphere?
Yeah, please explain.
Realize it, first digest it. Because our model level doesn't reach stratosphere, troposphere. Yeah. And then we are dealing the processes, okay? So we had a lot of brainstorming internally. Yeah. So we first convinced each other, we understood. Director was happy. The point was very simple. We cannot tell WCRP and WWRP that we want to do two separate conferences. Here we ask your funding for stratosphere, and here we ask your funding for extreme wind troposphere. That's not, no funding agency will like it or recommend it. So we basically couple it with some confusion in my mind, but finally what came out is something really brilliant. I think I have never seen in my 30 years here a conference like this, where, I mean, upper troposphere, UTLS, and troposphere seamlessly getting coupled. And now we have learned from each other. That is more important. We have learned stratosphere, troposphere, and troposphere. STI people have learned a lot of things from extremes. So this is, I think, a big takeaway. Our recommendation also to MOES should go in this line, right? That all our model should have Earth system as well as include these important processes which are playing major roles in extremes in various ways, right? So this is one, and I think this is also then the last session of stakeholder that has given some flavor, right, to community, that there is a community waiting for us, and the gap needs to be bridged. Right. So we are doing a lot of research ourselves, but finally they are the last mile. Right. And many of them said that we need higher granules and so on and so forth. And I think someone showed the German flood. Paul, I think, I remember. So it is not only in India, it's happening globally. That higher granule with forecast with more confidence required. Ensemble is one way to go forward. Team was very critical about AIML, but here, right now he's online. Very good. So he put a very strong argument by saying that AIML can really take a leap. He's leading a program on leap. So that also is a very new, I think, takeaway from this workshop, that NWP and AI both will go hand in hand and will take a leap, right? So I'll stop here. And
I will continue this to Dr. Piri.
Pierre is already online.
Can you just take from that point, Dr. Piri? Can you unmute your mic and speak up?
Pierre, can you unmute?
Yeah, you were in the initial stages of planning. I know you couldn't come, so but we can have you through online here. So can you please share us a few words?
Thanks, and sorry because it's just early here. I mean, that's what I was trying to show in my presentation. The feeling I have is that machine learning can be really accelerating progress in terms of parameterizations, across the board. I was at a meeting yesterday on ocean coupling as well, sea atmosphere coupling. So those things are moving quite fast now, and it goes beyond proof of concept. Many of those are starting to be really implemented at scale, so whether in subseasonal to seasonal forecast or also for long-term climate projections. There are still some issues, right? I mean, what I mentioned in my talk, which is especially related to generalization, right? That's the main issue that we are facing, but I think we have a couple of tricks or ways around that at the moment.
Okay, good. So continuing on the same line, so we already heard from Professor Ramaswamy and Vimal Mishra, as well as so this the role of AI/ML in taking this extremes field in forward. So any opinion that how the audience, anybody sitting in audience also has to share on this. So I invite some opinion from the audience also, not calling by name by specific names, but do you have any input to give to this particular point?
I'm Dr. Sanjay Mehta. I was impressed with the one presentation from UK. Actually, he was showing the data and handed that one. So what I have suggestion that we have the data. We also publish the data, but data is not available to everyone and even to the modeler. Can it be possible to somewhere, maybe the MOES can think, putting some people together who can extract the data and keep together so that anybody can use without any permissions and all these things. And data, because already published, it can be given, because by rule we should give the data. Nowadays, all journals ask the data once you have published the results. So I think this is becoming, suppose I need some data, then what happened that I have to ask him, there are lots of restrictions. I cannot share data. This is the rule, this is that one. So many things are there. So somebody from the government side, if they can do that one, it will be useful for all the researchers. Yeah.
Yeah,
so
that's a good suggestion, but I don't know this forum can give you a promise or answer, but Dr. Partho.
You invite some other. See, Mr. Mehta, Dr. Mehta, the point is that if you, I don't know which data you are referring. If you refer to model data, if you refer to hindcast data, okay, those are absolutely free. For example, there is a IMDA reanalysis, Dr. Rajgopal is sitting here, absolutely free. If you want GFS 20 years reanalysis data, it is free. You want S2S, I mean, actually GFS, it is going in TIGI archive. Estivalis will agree.
I think the mention here is the observational data, I guess.
Are you mentioning observational data or model data? Yes, so model data. So, okay, observations, I have no
For that, observations, this may not be the right forum to make any comments, but we can forward always the recommendation.
Yes,
that is what the best we can do. Dr. Suvarna want to respond, I think. Yeah.
I think data and all that problem will be solved eventually.
All right.
So basically, this workshop for troposphere stratosphere exchange, and we learned a new see stratospheric community were understanding processes and impact on the troposphere, and we were not knowing about numerical. We know there were impact, but numerical weather prediction models, how to include them, and we have to put these things in the model and look forward the way for that this workshop is organized. That is the theme of this workshop. So many paper and research were presented that impacts of stratosphere, QBO, having connection with MJO, NAO, and extreme weather. So this research discussion were very important for this workshop, and we need to look further into STS, S2S predictions, and many important talks were there for this workshop. So I feel that way we should discuss on that line. So yes.
So are you, I mean, especially STA community, you have any other forum that this data sharing is discussed, or no, I'm not totally, I'm not aware of it. So do you have any other global forum or?
inform that getting measurement in the UTS region is very challenging.
All right.
High altitude and they're cost effective also. And there are efforts going on within India and abroad, like balloon, radar, lidars, satellites are there. There are many, multiple satellites are there. They are measuring. And surface data, yes, they are scattered. They are there.
Yeah.
Over the Indian region, and this community also looking their own measurements. So data sharing is first they want to evaluate themselves, and
Right.
So there are thoughts by the MOS on metadata sharing, and some efforts I suppose are going on.
Yeah.
So soon it will be available. So that is for Indian part only, but we need to move ahead and look globally. And since atmosphere is not restricted in the troposphere, stratosphere, similarly not restricted to region also.
Right.
That way I want to take this discussion ahead. So thank you.
Okay. Yeah, I mean, here itself is a recommendation is that the sharing the data or worldwide meta agencies need strong collaboration and policies to share the data within themselves. Is a recommendation arrived from this conference. That's what I asked Suvarna, what your take, call on that in the stratosphere, troposphere part. So I think, Doctor, can I hear from you? I think we were calling out your name, Dr. Soon. Can you comment on these workshops and this the extreme weather part? We were calling out your name, but you were not there earlier. How do you find this, the recommendation or the takeaway messages? How do you find? Can you summarize in your own view? So that's what we want to, for you to share.
Okay, yeah. I had meeting with some other people there, so I just came back. So my short comment is, I really enjoyed this meeting. So all the presentations are quite good, and more importantly, I can see many young people who are really enthusiastic in atmospheric science and climate sciences. So I see the future of atmospheric science in India, here in Pune. For the possible collaboration, this event shouldn't be just one-time event. This event should continue in future. So for possible collaboration, I really encourage all the people to join the APAC activities. So unfortunately, we don't have many people from South Asia. So even if we do have over 10 different projects, including like volcanic eruption, solar impact to the climate, subseasonal to seasonal prediction, decadal prediction, tropical convection, subseasonal to seasonal prediction, there are many different projects. But unfortunately, we don't have many people from South Asia. So presumably you see some of APAC activity from this workshop. So based on this one, I encourage you to contact someone in APAC that could make this meeting even stronger in the next few years.
That's very well taken. Very good recommendation and advice. Thank you. So saying for young people's presentation posters, we given the task to Professor Solo Freitas, is he here? How was your experience screening through those posters and the science you find? Are you here, Dr. Solo? Probably not. Okay. So there is a comment, any comment? Yes, please, please, madam.
I just want to comment about the observed data.
Yes.
And CDS, ECMWF, in the website, you can find many open access data, observed data, and also PSL NOAA site. If you go there, many gridded data, observed data, reanalysis data, all are freely available. I just want to mention that.
Yeah. So, right. So,
those are open access, all are open access, but you have to know the site, PSL NOAA, that is giving surface data, stratosphere data, every data. KNMI is another open source. From KNMI also, you can have more data. And CDS, ECM, and MWF, they are having lots of observed data available, freely.
Yeah, that's very good point, especially the gridded versus point data, because even if you may have difficulty sharing gridded data. For example, I come from the ocean community. We have same issue with the coastal data, but later on we come up with a policy that let us grid them, and then it becomes not anymore in situ point data, which has some provision we can publish and share. I don't know how atmosphere is, the observation in situ are able to be gridded because it's highly variable, not like oceans. But there can be such ways that people can share data, not as an in situ spot data, but gridded data, which will not have any implication which location that data come from. That's what the policymakers and the security are worried to share the data, because that information will get leaked. For every nation, that's the common policy, the issue. I think across the world, where people are here, I think they would agree with me. Gridding could be one possible, but you should know how the system also changes, because slowly variable system you can grid, but highly variable system, I don't know. That's up to the experts to make a comment. Very good comment. We have really taken it.
Doing very good job. If you go to the website and just register there, ECMWF CDS website,
right,
and they are doing all the data available, freely available. No one has to pay anything, nothing else.
Good. Thank you. There is a comment, Terosan, please.
Thank you about data. So data very important.
Data.
And so the data is sometimes very important source for our research anytime. But, so getting data also very difficult sometimes. They have very big hurdles there, so they try them. And so getting data from that activity. So in such a sense, so sometimes some limitation is there. It is inevitable. But some research framework like GPEX or GPEX may be very important role for this type of data exchange. So we should make up some science plan, some other things. Instead that, we should develop a very clear mention data sharing policy is the activity. So in this way, so we should try to exchange data as much as possible for that the people are included in our research community. And also, but at the same time, we should think about how it is very difficult to get the first data, raw data. So in this sense, we have to understand such a prioritize things is also important. So, but it should be included in some well discussed science plan. So it may be very good. And so sometimes much more transparently, the data can be go and back. So such a way we will develop this data exchange. It is my opinion. Thank you.
Yeah. So now we will come back to dais. Please pass the mic. Oh, you have.
Yeah, I mean, I think this discussion of data exchange and data discovery is extremely important. And I just want to point out that from a WMO perspective, there's a new data policy and it extends to atmospheric composition. And a lot of these issues that we're talking about in terms of protection of the data provider and recognition, there's a lot of work that's gone into this data policy. So I think before there's a lot of reference. It's a very tough problem, but there's a lot of international thought that's gone into this already, and the role of metadata and how to discover data. So I think it's important to make the recommendation, but I encourage people before they start to come up with a solution.
All right.
to understand this
already
on which
existing
groundwork
has been done. Yeah. Thank you for pointing it out. Yes, Dr. Sabi.
So I just try to add one more point about data. On the US side, there have been very substantial discussion as government policy, not only have open data, but open data as soon as possible, much sooner than required in the past. Why? So that's the part I want to share briefly. It would be helpful for all the other countries. It's about the return on investments. You spend so much money on in situ measurements. Now, most of the users just want to use gridded data, and the in situ data is not as highly used. So if you care about your money spent, you want to have more people. The truth is there are lots of data there. So even if you open your data, you may not find many people. And the point is not only you need to open the data, you also need to provide the metadata describing your data and data uncertainty so that you can encourage more people use your data. Once they begin to use your data, not only you get a higher profile, you get many other feedbacks to help you do a better job for the future. And that's why, again, at least from American experience, it's a policy now to provide the data and metadata much sooner than before. It's not just open data. It's data, metadata, and as soon as possible for your own benefits.
Okay, thank you. Yeah. So from the discussion, from the observation and data availability, let me jump to one particular event. For example, especially interest for this extreme prediction. So they said, how can we approach events like those exceeds 10 sigma deviation? So Dr. Partho, you have any recommendations how we should tackle this kind of problem? Because experts from AMLs are here. How do you even predict such events where extremes deviate?
This is my experience in India. I mean, whatever extreme. So if we start even from 26 July 2005 Mumbai event, and we come to 4th December 2023 Tamil Nadu event, okay, and including Kerala, everywhere, even Delhi. So all are 10 sigma.
Okay.
Yeah. This is a general, and see, we can argue my model has captured, your model has not captured. Okay, we can argue, we can feel happy momentarily, but that moment of happiness doesn't last long. The next event will not be captured. So it doesn't work in statistically significant sense. The answer is Pierre is sitting here, and team I think mentioned it. Downscaling. Okay. That, I mean, we have to generate very high density spatio-temporal observations. There is no other way. Okay. Now, say I have a 6 kilometer model, I have a 12 kilometer model. Okay. Now, if you generate a data set, very high quality, okay, which is every 1 kilometer and 30 minutes rainfall, or hyper local, Assam, flood prone, vulnerable, Bangalore, Hyderabad, anywhere, Delhi. NCCR scientist was sitting here, okay? He also blamed this thing, rainfall. Now, so Professor Ramaswamy was mentioning bias correction. So 12 kilometer model output should not be used directly to any hydrology model. Professor Bimal Mishra will agree. It is a foolishness, but that's what we are doing, okay? So we are passing on our errors to next wherever we are applying. That's not the way. So you have to bias correct, or we have to downscale. How do you do that? We don't have data. I told from the podium also, we don't have data, whether we want to use AIML or whether we want to use downscale, whether I want to use any regression, whatever it is. I don't have data to capture these 10 sigma events. If I don't have, then how do I do? Okay, so this is the challenge. So I think one area where we can bridge the, I mean, we have to extensively bridge the gap between observation and model is that the observational protocol, Jovin is sitting here, observational protocol should be decided based on what the modelers actually is planning. That's what in GPEX and everywhere they have kept a very strong bullet point for model. Okay, so that has to happen in practice. We are talking, it may be in theory, it has to happen in theory. If it happens, there are examples, you can actually. If my model can go to 3 sigma, okay, with downscale, you can reach to 6 sigma. That's enough. You don't have to tell me that 1 meter rain will fall on my head. Even if you tell me 50 centimeter, I will run away. Yeah, I don't need to wait for 1 meter rainfall to get, I mean, so that is enough. But that also we are not able to tell for these all the stakeholders, whether it is flood, whether it is power, anywhere.
So, Professor Vimal, if you're saying that unless and until we have observations at that scale, numerical weather prediction models are not able to help us in predicting extremes. So what is your answer in that? Do you have any comments to say on that?
I mean, observations are certainly needed, not only just to improve or bias correct the Met forecast, but also to, to compare or evaluate impact models, right? When we want to use, let's say, flood models or anything, we don't have observations, and you have to blindly trust models.
Yeah, we have
and
seen that in the last
which
presentation.
may be not a very good idea. But of course, we cannot have observations of every point. And but certain representative quality controlled observations can make a lot of difference. Nowadays satellite data is filling significantly the gap. For instance, GPM, 30-minute, 10 kilometer. I mean, making a lot of difference, whether we realize it or not. So, I mean, I would say, yes, we need observations, we need improved models, but I don't think we will soon reach to the desired state. So we have to make decisions under uncertainty, and we should not wait that we will make everything perfect. And until we make everything perfect, we will not make any progress. So that's how the system doesn't work.
Thank you. Yes, Stipalis.
Yeah, I wanted to comment on that aspect that it's difficult to calibrate a model when you don't have a good net of observations. There is some approach that they are, I think, an increasing in terms of post-processing, and we started to study it in this NWF as well, and is how you can learn from similar conditions that are giving you specific biases from all around the world or from many places. So you don't need to have observations everywhere. You need to know under which conditions the model is behaving worse. So this can be like creating weather types or similar aspects where you think, okay, under specific conditions like convective events, low wind in the surface, warm temperature specific thresholds, we know that our model has some specific biases. So let's train when in your country or in all the database you have, your model can learn to create the biases correction and then correct your specific points when this weather type is happening. So we started to develop a bit on that. For now, we have a product, for example, I didn't explain, but it's the easy point rainfall. So to understand the subgrid variability under specific weather conditions of the model. But I mean, with machine learning, I am sure that this could be even more developed. So yeah, it's difficult, but especially if you have to calibrate in only one specific country, but there are some approaches that probably we have to investigate more of how to learn, because in the end, your model is a model. And under specific circumstances, your model will behave in the same way. So you have to learn from these places where the data is available to apply in places where the data is not available. So yeah, I am happy to see if people just progress on that because we are still in early stage.
Okay. Thank you, Dr. Perry. Sir, you have any comments to add? Your rise is...
Yeah, actually very much on that point. So if I could just share my screen potentially. Can you see it full screen?
We are seeing it, yeah.
Yeah, so this is a paper we just got accepted at Nature Geoscience, but talking about how we see kind of the future of Earth system and climate modeling, and also the role of AI. So a lot of that is related to things I discussed in the talk. You can harvest high resolution data to leap across scale to improve the quality of the model. So grid scale, large scale average, for instance, precipitation, but it could be also even climate sensitivity, but also developing new type of algorithms for data assimilation. I think we are just in the very early stage. So people, for instance, a lot of data assimilation is very, very well developed at weather forecasting in the weather forecasting community. But a lot of the tools we have to acknowledge will not work for climate, right? Because we're looking at long-term processes, and it's not just about initial conditions. Actually, initial conditions become much less important. So that's actually very critical to reduce a lot of the biases. And then AI can also be extremely useful along the path of variability. So when we think about extremes, of course, we want to generate multiple ensemble members. So you can think about, for instance, generative AI. This is exactly what they do, right? I mean, they are trying to generate samples from a distribution. And then there's also what was just mentioned about downscaling, right? And we are starting to see really exciting work in the downscaling space and to do different things. It can be used to generate downscaled data using various streams of data. And that's actually kind of the power of AI, is that you can harvest, satellite observations and in situ a few points observations, and they can be in different locations of the globe, and you can transfer some of that knowledge potentially. But at the same time, you can also bias correct at the same time, right? So you can do all sorts of things. And you can also, for instance, using generative AI, you can actually include uncertainty quantification, which is very, very useful. And you can do that across the pipeline. And what we argued is that you can really use that. You can think of them as Legos, where AI can really improve the different pieces of the pipeline. It could be at once, it could be across different components. But it can really provide a lot of the tools that we need, including uncertainty quantification. And that should lead to better, for instance, hydrological models or impact models, we believe.
Okay, thank you. So, yes, Dr. Subin.
So suddenly, I just want to mention one new direction which has not been covered here, and involved at a small capacity. That's a quantum. Many of you have heard the term quantum. Now we are actually talking about quantum sensor and quantum computing. And then Earth system would be a good target for the upcoming quantum computers. And we need a new generation of students who actually understand the physics. I'm talking with my own students. Have you taken quantum mechanics class? If you haven't, then you may not be a good fit. But the point is the world is changing. Quantum computer for our fields provides a potential, not using Navier-Stokes equation for fluid mechanics. Instead, talk about Boltzmann equation. It's a completely different concept or not of other issues. And then many of the challenges we are facing for Earth observation from space, once we develop some of the new quantum sensors, situation will change. And this will happen in the next 10 to 15 years. So we can do some push from our generation, but the future will be the future of the younger generation, and paying some attention to the new fields would be beneficial.
Thank you. I call upon the views from Dr. Fang Lin from NSEP. Are you here, Dr. Fang Lin? Yeah, please, can you share how you respond to these discussions on especially this extreme and predictions?
Maybe I want to mention a little bit about machine learning and my feeling. I have a traditional numerical modeler. Now I'm confused, scared, or I don't know if other players share the same feeling. What's the future? I know everyone's talking about machine learning. Should we abandon traditional modeling? I know many of the researchers there are using a model as a tool to understand processes. If we don't have any next generation really understands the basic physics, we'll be able to improve our forecast accuracy. So that's a question I think needs more discussion. I still feel we need, at least from the educational point of view, we did the traditional modeling. In terms of service, I do think everyone is pushing forward, including our center, and makes the data not just useful and usable. There's really a social, economical, and psychology, and even included. We at our center, and we recently had a new branch actually, had many psychologists how to interact with the users, with how to teach them understand the forecast, or how to teach also our forecasters how to make the data usable for the users. That's probably I want to end for now.
Yeah, we in India, we do have such meetings to educate the disaster management department and stakeholders to interpret the forecasts. We do have, I mean, as a response to what you were saying. we do have to improve or increase such activities. I think that's what the message I'm getting from you.
Yes.
You correct me if I'm wrong.
Yes.
Yeah, sure. Okay, so we're really coming up the closing session and closing time. So Suvarna wants to say something. Then, if any students, we are all talking about early career scientists and students here, but I haven't seen any comments from them. So please prepare while Suvarna is speaking.
So no, generally I'm saying this meeting was targeted for troposphere stratosphere interaction extreme. So we have experts from extreme and we have experts from stratosphere. So we have seen many presentation posters that there is definite impact of stratosphere on extreme weather. So from these experts, what is our take-home message and what is way forward for this improving our what is the role of stratosphere on the extremes and what is way forward for extreme event? There are MIML, AIML people also, and so that message has not been so clear from the discussion.
Okay, so you're posing a question that how this stratosphere troposphere interaction and the extreme as such connected by science. That's what you're asking, right? And we haven't heard anything from the experts. So any way you want to respond?
So a lot of effort on the stratosphere troposphere interaction, stratosphere troposphere coupling community has focused on climatological analyses that show mean state shifts. And there's a real need to go past that perspective. I mean, this is really the same point that Tim Palmer was making. We need to move past ensemble means and look at ensemble distributions. I think there is a lot to learn about how stratosphere can affect the evolution, affect the probability of extremes, but we need, I think we need to be creative about how we use ensembles. I think we need to look at understanding tail distributions, understanding not just say the probability of the tails, but the dynamics that's going on in the tails. And I think there's a lot to learn in there. And I think there have been some specific ideas that have come up. This is very much, I guess, a particular set of conversations with Suvarna and some other scientists here. I've learned a bunch about possible pathways from the stratosphere to the monsoon, anticyclone, to surface extremes that really need to be explored. So I mean, maybe the main takeaways is that I think there's a lot of new ways of thinking about that problem that need to happen. We can't just look at climatological statistics. We need to look at ensembles in careful ways to identify those connections. I think there's similar messages, not just for sort of stratosphere troposphere coupling, but trying to understand predictability of extremes on S2S timescales have the same questions are there. We're never going to be able to predict extreme events past synoptic timescales or even 2 synoptic timescales at the level we might want, but we can understand something about how probability distributions shift. So we need both the techniques to think about extremes in a probabilistic way, and we need to understand how to communicate that to stakeholders that care about it. Those are more questions or areas that I think we need to work more on than answers. But
yeah, at least some of the presentation I can see from this report has addressed on tropical to polar stratospheric connection and their key role in QBO, strength of Hartley cells, ENSO, NAO, MJO, which coming very close to what you are trying to say as extremes, but as such may not be the word extreme can add here as of now because it is still evolving, I guess.
So I think it's a great platform where both experts are there. So we should think of way forward.
Yeah, some of the connections, at least in the long-term climate, I can see from the recommendation, okay, of the presentations made here. So students and early career scientists, are you ready with your question? Have you made any question? Yes, I can.
Hello,
yes.
So it's a suggestion rather than a question. So one, the data gap, which we all are worried of, like, improving the models and everything. So the low-cost sensors are actually that market is emerging, and I think a couple of groups, they have started putting low-cost sensors in the sensitive cities. But the problem is, I mean, there is a big gap between how they will reach to the concerned scientists, those are actually working on the problem from the modeling side, and someone has to fill the gap. Basically, I'm working with one of the sensor company, those are measuring urban flood, air quality monitoring, gases, GSG monitoring, and weather parameters. So there is always, I mean, they are quite a far away from the scientific organization, and there is, I mean, that gap is so huge that they are not even able to reach, and maybe can contribute to this bigger problem we are talking about, the data gap and model improvement. So in some way, if the scientific organization like IITM or the MOES can encourage those organizations to maybe help them fulfilling some of the data gaps, that would be really interesting to look forward in the future and go for a sustainable, I think, maybe better way to, encounter this problem and come up with a good solution.
Yeah. Any comment? Yeah, please.
Yeah, that's an excellent point in terms of, the technology of low-cost sensors is actually a very powerful and technology. I'd just like to point out that WMO, the Global Atmospheric Watch, has been studying the use of low-cost sensors and been working with manufacturers and trying to drive standards and other capabilities. And we have, if you talk with me, we have actually, we're going to launch the third update of that report next week. And so that's the sort of thing that we're trying to do organizationally, is to understand and promote, but also talk about best uses of low-cost sensors, and also the need for manufacturers and others to understand their role in the application space. So,
yeah. Any other response to that question?
Yeah.
Yes, Bhuven.
Yeah. So yeah, talking about monsoon on like monsoon forecasting on seasonal scales. So like Partha also mentioned that mostly we are interested in capturing the tropospheric processes and teleconnections, like from the Pacific and Indian Ocean and so on. So what do you think, like having better reproducibility of QBO, like stratospheric waves into the seasonal prediction models, or like at sub-seasonal scales, capturing the sudden stratospheric warmings are important, and or what? I mean, like Peter or yeah, those who are expert in stratospheric dynamics can comment on that.
It's a very specific scientific question to a particular problem. Yeah.
There are certainly particular configurations where it's very important, and we've shown that in a couple of case studies where we can really demonstrate that getting the stratosphere right makes differences to short-term forecasts, not just long-term ones, but even on a couple of days. But that's not true all the time. So this speaks again to the need to understand particular configurations. You can't just look at the statistics everywhere, but have to understand the role in particular events, which makes the problem hard, but it's very clear in particular configurations that the stratosphere does play a big role on both longer timescales and short timescales. The question of its relevance for all of the sort of tropospheric dynamics of the monsoon, that I can't speak to, but I saw a lot here that really suggests that we need to understand that more, and there's a lot of prospects for coupling there. But I think there's a lot of open questions that need to be explored.
So the workshop is opening up new questions, then concluding a theme. That's good. That's what we want. Thank you. Yeah, I mean, regarding the previous question that gentleman asked, actually, this the ministry is planning private-public partnership to benefit and improving the instrument developments and etc. So those all are in the pipeline. So it's all in the discussion. Yeah. Okay, so I can't see.
I think
yes, please. Yeah.
I want to add Peter's answer. So does the stratosphere important? Is the stratosphere important for prediction? The short answer is yes. In the southern hemisphere, Bureau of Meteorology, Australia is considering the ozone hole for the seasonal prediction. So as you may know, a couple of years ago, Australia had really strong wildfire. One of the reasons was anomalously strong ozone hole around that year. So Australia is trying to use that information to improve seasonal prediction. And as Peter showed us, and I mean, during stratospheric southern warming, we do have significant impact in the high latitude and some middle latitude regions. So that could be really useful for the sub-seasonal prediction. So moving to the tropics, it's really well recognized that QBO can control tropical cyclone track, especially over the western North Pacific. So if the model doesn't have realistic QBO, it's very high possibility to, to fail to predict a realistic typhoon track. So those informations are now integrated in the operational models. So even if it's not, even there are not many publications, the operational centers are already using stratospheric information to improve sub-seasonal to seasonal or even longer prediction.
Yeah, thank you. I think we should close this session. And now I invite a few words from our director. He has kindly joined us in the panel discussion. Sir, share a few words, your thoughts, your recommendations from all this.
Yeah, thank you. I have one suggestion.
Sure.
Because this is stratosphere, troposphere interaction, and also we are talking about extreme prediction of extreme. The International Monsoon Project Office here is a GPEX and Clavar GPEX office. I think it will be important to have the APARC also as part of that. So this is more of a policy, this we can recommend. This becomes very relevant. And perhaps the click also.
Okay.
So all the WCRPI core projects should be there.
Okay.
Because we are talking about atmospheric chemistry, monsoon, so it becomes very relevant. And also we are talking about teleconnections with the polar regions and melting of the snow and glaciers, and it's changing circulation patterns. It is influencing extremes in the low latitudes, monsoon areas. So this synergy, so at that level, so the IMPO has a very big role. So it should clearly reflect the APARC and the click activity should also be integrated into the IMPO. We can make that recommendation.
Yeah.
I think Siop was suggesting this.
Yeah, sir. Dr. Rajagopal, you want to respond to that? He's heading IMPO activities here.
Actually, for the international workshop on monsoons, we have already in contact with APARC co-chairs and CLIC co-chairs and many others to be part of the International Scientific Committee. And we have got positive response from both of them. It's good that, and I think some of the ocean panels also are interested in joining this one. So I think we will go take, because even we have been told by WCRP to have more cross-panel activities between monsoon panel and others. So we have been doing something, and now things have started falling into place. We have been identifying people and communicating, but then we need to identify some scientific problems on which they have to work on. So there are already some person-to-person level meetings with Surya attended GPEX meetings. He met some people there. So something is happening now. So it's going in a positive direction.
Okay, thank you. One more point, Dr. Krishnan, yeah.
We had a meeting recently for this, making this vision document of ministry for the next 25 years.
Yes, sir.
In 5 years and next 25 years. So one suggestion came out that we should have a big program like MONEX 2, because MONEX 79 was a big monsoon experiment, was a big program, very successful program. Now we will be completing 50 years in 2029. So it's very appropriate at this time. We have a major observational field campaign like MONEX 2, and I think involving all the regional monsoons of the world. That will be a very important. Also in light of what Professor Zubin was saying this morning. Years of precipitation. So that will be a very important.
Okay, thank you, sir. Okay, so with this, we will now close this session, conclude this session, and first of all, let me thank all the dignitaries on the dais and off the dais, our director, and our scientific conveners and all the team, all the participants came from all the way. Wish you a safe journey back home. Keep in touch. Keep this momentum go on. Contribute exciting research. We would like to see you growing up in excellent research arenas. Thank you very much. With this, I pass my mic to who is there? Snehilada or Chaitri? Yes. One more announcement. Dr. Suvarna will make on the special issue they are putting up in ACP. It's an exciting opportunity for youngsters.
SCP has agreed to have a special issue. Paper presented in this workshop will be published. And within 10 days, we'll mail you, all of you. We will open the SCP issue and you will receive the information on that. Okay, thank you.
Okay, so we are officially adjourning this workshop. Thank you very much. Tea served in the pandal. Okay. Yeah. Thank you. Thank you very much.
Thank you.
Thank you. Yeah.